My name is Juan Klopper and I'm really on a mission to teach deep learning, deep neural networks. I'm a surgeon. I'm involved in research using deep neural networks because I think the time has come for doctors, nurses, healthcare professionals, everyone involved in healthcare to start learning about deep learning. It's usually the space where we'll find mathematicians, computer scientists, but to solve problems, we must understand that the domain knowledge lies on our side, on the medical specialist side, and we can contribute to this. We can work together with our colleagues in mathematics and computer science just to improve the overall aims and what we can achieve with deep learning. So really, I think the time has come for everyone interested in healthcare to get involved in deep learning. Now, these videos are not only for those who are from the healthcare professional side. Anyone interested in deep learning should also find these videos helpful. Now, these videos are based on documents that were created in R and published here in RPubs. So they are available. The actual RMD RStudio files will be available on GitHub. You can view these on RPubs as we're going to do here. You can download the actual files on GitHub. I'll show you the links there. There'll be videos on YouTube. I'll talk about it on Twitter and also disseminate it on LinkedIn. So connect with me on LinkedIn, follow me on Twitter, sign up and subscribe on YouTube, and also view these files in RPubs and also download them from GitHub. So I'm really trying to put these everywhere just to sow this net as far and wide as possible, because I really want to get everyone involved in deep learning. So this is the document. I'm not going to read from the document with these RPubs, but I'm going to use it as a baseline just to discuss a few topics here on YouTube. Really, if you want a bit of extra information or you want to hear a bit of explanation instead of just reading the document. So let's carry on. We'll move down. And what I'm going to do really here is just use linear regression as a first step to understanding deep learning. There's a lot of concepts we can take from simple linear regression, and it'll teach us those concepts, and we're going to use them later when we develop deep neural networks. So imagine we are in a scenario where we want to use deep learning. What would such a scenario look like? Well, one of the first ones is actually an example that will refer to something that we will call supervised learning. In supervised learning, we have this single variable which we want to predict. Now, I've created a very simple example here. You see I've created a computer variable or an object called sales, and I've put these 10 values into this numerical vector here using C there. So I've got these 10 values. Now, they can represent anything. Just imagine they represent the sales in units of tons. So some medical company selling something that goes into the production of some medication, and they sell so many tons of each product, and there were 3 tons sold, then 4 tons, then 2 tons. It doesn't matter what these are, but they represent a variable called sales, and they are all these values. And I might have a lot of other variables associated with each of these that would predict that the sale was going to be 3 tons or 4 tons or 2 tons. So that makes this variable here something we call a target variable. I'm going to use the other words, the other terms for it, but I'm going to use target. So this becomes a target variable, and these values, these 10 values, I'm going to try and predict them. Now, without looking at all the other variables that might be there, that I might use to predict these, let's just consider a very simple model. A very simple model to predict that, and that is the mean of these 10 values. And we know how to calculate a mean. You sum over all the values. The x sub I, there's 10, so x will be 1, then the second one, then the third one. X sub 1 would be the 3, x sub 2 would be the 4, x sub 3 would be the 2 there, x sub 4 would be the 4. I hope I didn't get those mixed up. Anyway, 1, 2, 3, 4 until 10. That's what the summation sign means. And I'm going to go from 1 to n, and n is 10 here. Their sample size is 10. And then I'm going to divide by n, how many there are. And that's just the calculation for the arithmetic mean. So when we get this mean sales, I can just say mean here, mean Let's do that mean and sales as an argument. Save that in the mean.sales computer variable or object, and indeed the mean is 4.9. I can suggest that as a very baseline model, that no matter what my input variables are, I will always predict 4.9. So I will predict that all these values are 4.9, 4.9, 4.9, 4.9, 4.9, 4.9. I haven't really learned much. I'm just predicting that every output given any set of input, I will always sell 4.9. Now, of course, I'm making an error here, because if I predicted a sale of 4.9, the actual sale was 3. There's a difference between 4 and 9 and 3. And yeah, I sold 4. And again, there's a difference between 4.9 and 4. There's a difference between what my model predicts. It will always predict 4.9. This is a very simple model. But there's an error every time. And I can check what the differences are by just subtracting this one from that one in each instance. So I can say 3 minus 4.9 and 4 minus 4.9 and 2 minus 4.9. That difference is the error that I'm making. And I can sum over all these errors, but just have a look at one thing. I mean, 2 is less than 4.9, but 5 and 6 and 9 and 12, they're more than 4.9. So I'm going to get some negative numbers and some positive numbers. And lo and behold, if I'm just using rounding here, otherwise we're going to get something to the power negative 15, which is basically 0. I'm just subtracting all of those, and I'm adding all those subtractions. I'm going to end up with 0, because that is just what the mean is doing. Some values are below and some values are above, and this one sits in the middle. So if I sum up all the differences, I am going to end up with 0. So 0 is definitely not the error. I'm not making an error of 0. I'm definitely making an error. So a better way to do this is what we call the sum of squared errors. So I'm going to take every value again here, and I'm going to subtract that from the mean as we did before, but I'm going to square every value. Remember, if you square anything, the result is a positive number. So minus 3 times minus 3 is positive 9. So I'm always going to end up with a positive. And then I'm going to add all these squared values. So that's the sum of squared errors. And now that gives me, if I do that, the sum of sales minus 4.9 square. It's going to do a bit of broadcasting. In other words, element by element, it's going to subtract 4.9 from each one of these, square that, and then it'll have 10 of those squared differences, and then sum all of them, and I get 100.9. So that's closer to the fact that I am making an error here. There's one problem, though, is that that error is not in proper units. So say, for instance, those was how many pounds I sold. Now I have pounds squared. What is a pound squared? What kind of thing is that? So that doesn't work. Number 2 is, if I have more, I only have 10 here, but you can imagine if I added more, I'm just adding all my errors. So the errors are going to be related to how many variables I have. So again, I can't compare 2 errors with in 2 different scenarios, because it's just going to depend how many I have. I might be woefully wrong with something that just have 5 errors and be very close with something that has 1,000 of these values, 1,000 errors, but the 1,000 might be much more accurate one in the end, even though it has a bigger error. So we've got to do something, and we solve that problem, as we see down here, by dividing by the number of the sample size. Now, we don't do the sample size, we actually do n minus 1, and that has to do with the concept of degrees of freedom, which I don't want to get into here. So if I divide by how many there are, my sum of squared errors, which is still in the numerator there, divided by how many there are, now I'm stabilizing this thing. So it doesn't matter how many errors I have, how many elements I have in my target vector here, my target variable here. I'm dividing by how many there are, so it doesn't matter. Now I can compare 2 different scenarios with each other. And because I had pounds squared, remember, I'm just going to take the square root of that. And we call that the standard deviation, and of course, without taking the square root, we call that a variance. Now, that is a different way of looking at variance and standard deviation. We used to look at it in statistics just as a measure of dispersion. But we're not looking at it as a measure of dispersion here. What we are looking at it here is an indicator of how wrong my model is. If my model always predicts the mean, then I can use the standard deviation, or the variance is this without the square root, of how wrong my model is. So the variance in the error of my model, how bad my model is, that is what variance and standard deviation really is. And if I do that here, I'm dividing by 9, there's 10 minus 1 is 9, and the sum of squares. So I have a variance here of 11 that describes the error in my model. And this brings home a very important concept, that the actual target, now there's 10 of these, so y1, y2, y3, y4 are these numbers up here. My target, if I can represent them as a y, I, each of them, is going to be the mean plus some error. The difference between those two is some error. And so I can run through all 10 of those, and each will have its individual error. And if I add that error to the mean, I'm going to get the actual y. And now, and this is really important concept in supervised machine learning. I'm going to have some target variable, and I'm going to have some model. And if I add to that some error, I'm going to get to the target. And that's machine learning right there in equation 5 here. Now let's learn a few extra terms by just looking at improving our model. Now what I'm going to do here is to set the random seed, and so just if you run this, you get the same results. I'm going to create an input variable and an output variable. My input variable is going to be 100 values with a mean of 10, a standard deviation of 2, and 1 decimal place. And I'm just going to add some random noise to each of these to get my output variable. It's been as a contrived creation here of an input variable and a target variable. Sometimes it's also called an output. A target might also be called an output. I'm using Plotly here just to show you all these values. So I've got my input variable on the x-axis, and I'm predicting what the output variable is going to be. So in the end, this would have been my sales, my 10 sales values up here. And now we are putting an input. So this one, for an input of 7, I will have a result of 6.1. For this one, an input of 6.4 will give me an output, a target value of 7.4. And I'm asking the question, can I use this 6.4 or that 7 or this 6 or that 7.6 to predict what the second number, the output variable, the target variable is going to be? And you've seen this in linear regression. I can perhaps draw a straight line through here, and that straight line is going to represent my model. So that anywhere on that straight line, given whatever the value here is on the x-axis, I can read from the y-axis what the output, the predicted output is going to be, and that is going to be different from the real output. If the line goes, just imagine here, I didn't draw it in here, but imagine the line goes down here. And right about here, it's predicting just over, say, 8.1, 8.2, given a 7.5. Look, I'm in the line with a 7.5 here. So down there, maybe here, it would have been 8.2, but in reality, it was 8.8. So my model would be out by 0.6. If it was 8.2 minus 8.8, negative 0.6 would have been my error. And so if I draw a line in here, there'll be an error between each of these. And remember, I can square all of those, so that's the sum of squared errors, and I can divide that by n minus 1, which would be 99 in this case, and get the variance as to describe the error in my model. But what I'm going to try and predict here, my aim here is to predict this line. And remember a straight line from school algebra. A straight line will have a slope. This will be a positive slope going up. If the line went down, it'll be a negative slope. And remember, slope is this rise over run. So if I draw a line from here to there, it will be the difference in y divided by the difference in x. That gives me the slope. And when x is 0 here, it's going to cross through the y line somewhere, and that's the y-intercept. So if I have those two called parameters, the y-intercept and the slope, I'll be able to draw this line. So those are the two things I have to learn. And there's the learn in deep learning. We're trying to learn what those values would be, so that when I draw this line here, and the aim here is to minimize the error between what the predicted value is going to be on this line, my model, and the true value there. That is the aim, to learn the very two best values for that slope and that intercept to give me the best line to minimize my error. And again, I just show you another term here. It's called deviation. That's observed what is the real value minus what my model is going to suggest squared, and I sum over all of these, same story. Now if I were to run this over these 100 sample values that I did, the sum of squared differences, I get 681. That is really the variance in my model. Now let us just, through blind interpretation, and again, just to reiterate, I used the mean of these sales here, the output variable. I used the mean of that as my model. So I'm subtracting each one of these from the mean, squaring that, summing that. So the sum of squared errors and I haven't here divided it by 99, so this is not the variance. This is 681. Let's improve this by introducing just blindly a slope and an intercept. A slope of 0.8 and an intercept of 0.1. So if I plug it into that I, and then we put a hat on because this is now the predicted one. Remember, is beta 0, which is the 2 here, and beta 1, which is the 0.95. I'm just plugging those in. I should just change what I've written here because I've changed this to 0.95 and 2, so I'll just change that to 0.95 and 2 when I republish this. So there we go, 0.95 and 2. I'm plugging those in just as blind as I can, and I do the sum of squared errors, and I get 383. So that's an improvement on the 681. And I can actually just divide those two with each other just to get the r squared, which will give me an indication of the improvement in my model. And we call this ratio actually the systematic variance as relative to how much variance there was to begin with. That's the baseline model, the unsystemic variance. Statistical terms, we needn't care too much about that. Now I can abuse the system a little bit by cheating and using the linear model function in R, and I create this output variable is dependent on just a single input variable. If there were more, I would just plus the next one, plus the next one. And that gives me these two values right here, the best ones, an intercept of 1.94 and a slope here of 0.99. That's what these two values under the estimate was. So in actual fact, the prediction is going to be 0.9982 times my input variable plus 1.942. That's going to give me the predicted y. And those are the best values for beta 0 and beta 1 to take to give me the least number of errors. To get to the true value, you'll see there's no hat on this one. I have to add an error. That's the difference between each prediction and the actual value. And we can just expand this if I had more than one. If I had more than one input variable, or also called a feature variable, that would just expand to beta 1 x1 and beta 2 x2 and beta all the way to n, how many input variables I had, plus some error is going to give me the true y output. The concept here really is to learn the best parameters, beta 0 and beta 1, so that I can draw the best line here to have the least number of errors. Now, by the way, if you hear the banging outside, I've mentioned a couple of times, they're building a new neuroscience center right outside my office, and it doesn't matter that I come in early in the morning before work or leave after work, the banging continues and it's driving me nuts. So I do these recordings out of hours, but it doesn't matter, you're still going to hear this banging as they build the new center, and please just forgive that. I cannot run away from that here in my office at all. So a few basic concepts that we take away here, that there's something we can learn. Something we can learn, and one way to learn was to create this sum of squared errors, and in some way, which is going to come in the next section as we continue this look into linear regression to teach us the fundamentals of deep learning, we're going to learn, I'm going to show you how to learn what these parameters are by minimizing something. We're going to minimize the error, and I'm going to show you the concept behind minimizing the error so I can get the best line to fit through here, and that line is just a model. It predicts this target variable, and that's what we're going to do in deep learning. We're going to shove in a lot of data, and we want to learn, we're going to predict some outcome, and we want that outcome to be as close as possible to the truth. I might give a lot of images, some with a nodule in the lung that's cancerous and some are not. Imagine some CT scans. And I want the model to predict, if I give it an X-ray in the end, or CT scan in the end, is this a tumor or is it not a tumor? And I want that to be as accurate as possible. Same concept is going to apply. I'm going to create some error function, and I want to minimize as this deep learning network that we're going to develop, as it learns from the data, because every time I'm going to give it data to learn from first, which has the target variable known, and it's going to learn these parameters akin to the beta 0 and beta 1 here to predict the best possible accuracy. And it's going to change them and change them and change them until it gets the best values of something that is akin to this beta 0 and beta 1. To give the best prediction for that CT scan if this really is a tumor or not. So it makes the least amount of mistakes. That is what we are after, and you can see that these concepts, these basic concepts here that we're showing here in linear regression, is really the basis of what we need to develop our understanding of deep learning. So that's it for this video tutorial. I'm going to move on to the next one. I just want to warn you, there are going to be some additional videos on YouTube. Two of the concepts that we're going to come across are linear algebra and calculus, some derivatives, multivariable derivatives. Now, strictly speaking, you do not have to understand linear algebra or derivatives to be able to write code or to create a deep learning network. Don't run away from it because you don't understand linear algebra or derivatives. I'm going to make two separate extra little videos just to show the very basic concepts of the derivatives in a multivariable system and to the basics of linear algebra, just to remind you from stuff that you might have seen at school or you might have seen early on in your university career and you've just forgotten them, or you've never seen them before. It doesn't matter. I just show you the very basic concepts just to ease the understanding. But again, you don't need to know it. You're going to write a line of code and the computer's going to do this all for you. But I think it is nice if you have that understanding. If you want deeper understandings, I've got two massive playlists on YouTube, one on multivariable calculus and one on linear algebra. And if you really want to understand it, I think there's over 100 lectures in each of those two playlists that I've put out there. If you really want to understand linear algebra, you really want to understand multivariable calculus, you can watch those. But again, I reiterate, it's not necessary. We're going to write a line of code and the computer's going to do all this for us. But perhaps just watch those two very basic videos. It really is going to help you to understand how this deep learning, deep neural network that we are going to construct, what the basics of it really is, just to give you that intuitive understanding of what is happening here. Actually, without you knowing, you already have it just from this video. I look forward to speaking to you again. As I say, subscribe on YouTube, follow me on Twitter, connect with me on LinkedIn. These at least the format that you see is available on RPubs, and it's available on GitHub. I'll put all the links in the video. It'll all be written on LinkedIn, and I referred to it on Twitter, etc. As I said, I want to spread this word as far and wide as possible. I want as many people to get to grips with deep learning, and I want us to start using it in our research and answer some fundamental questions and solve some problems in healthcare. If we all come together and we make the effort to learn about a deep learning. Welcome back. We're going to continuing our look here into linear regression, really to cement our understanding of deep neural networks. I want to apologize again for all this banging that you're going to hear. They're building a neuroscience center outside out my door. They are here very early in the morning. They stay until very late. So even recording these before work, recording these after work, does not matter. The banging goes on every time I come to my office. If I have a free moment here, I almost have to bring earplugs. It's just become, it's just an absolute nightmare. So if you hear all the banging, nothing I can do about that. The reason behind these videos, remember, I want everyone to get involved with using deep neural networks to solve healthcare problems. I'm a surgeon, doesn't matter. I know about deep learning. I can use deep learning in my research, and I want everyone to be able to do that. I want people with domain knowledge in healthcare or those very interested in healthcare to reach out and work with people in computer science and mathematics who are already doing deep learning. I want us to work together, but it is us with the domain knowledge, with the interest that really we have to bridge that gap. We have to learn about deep learning. There is no excuse. The time is now to make the effort and to learn about this. Now, these videos are not only for healthcare professionals or those involved in healthcare. Even if your interest is well outside of that and you only want to learn about deep learning, these videos will serve you properly as well. Now, as I mentioned in the previous video, this is RPubs, an RStudio document using Markdown that I've published on RPubs. I will write about it on Twitter. I will mention it on LinkedIn. These videos on YouTube, they are available here on RPubs, and the actual files are available on GitHub. So subscribe on YouTube, follow me on Twitter, connect with me on LinkedIn, look at all my files here in RPubs, and also download the files for your own use on GitHub. I really want to spread the word about learning about deep neural networks. So in this video, I'm going to continue this looking at our at linear regression, just as an example of the basic concepts behind deep learning before we get into any models. I'm going to use linear algebra and multivariable derivatives in this video. Don't run away. I'm going to make 2 extra videos just on the very basics of linear algebra and the very basics of derivatives, calculus, just to show you what it's about. You needn't do that, or you really don't need to understand it, though. You're going to write a simple line of code and the computer's going to do that all for you. But I think it's worthwhile at least just to watch those two, just to remind yourself if you've seen it before, or just get behind, understanding it before you're using it. I think it's worth the effort, although I reiterate, it's not absolutely necessary. Now, if you really want to know about linear algebra and you really want to know about multivariable calculus, I have 2 playlists on YouTube. I'll link to them. They each have, I think, over 100 lectures in each of those playlists. If you want to know about linear algebra or multivariable calculus, watch my videos on that. Now, back to linear regression and how that is going to help us. I'm not going to read from this. You can read this all on your own. In case you don't want to read it and you want to hear my voice explain a few extra things, continue watching this video. Remember that we are trying to predict some outcome called a target variable. And we can also call those actual values the ground truth. We're going to try and predict those ground truth by creating some model. And when we have only a single input variable to predict the target variable, this is how we can predict it. This is a mathematical model of that. So given any of the input variables, if I multiply that by some unknown called beta sub 1 here, and I add to that some other unknown beta sub 0, it's going to give me a prediction of what it thinks the target value must be. And remember, if I added an error term here, I'm going to get the actual value. And this model is a model of a straight line. Remember from school, y equals minus a half x plus 2. That is the slope and that is the intercept, and that's exactly what this is. Beta 1 is a slope and beta 1 is a y-intercept. It is a model of a slope, it's a model of a straight line. My model in predicting an outcome variable, a target variable, the ground truth, if I only have a single variable, is the straight line. As simple as that. We've looked at this before, where we look at the error that I make every time. So if I, whatever predicted, this y hat sub 0, given any input value, minus the actual ground truth value, and I square that, we are now going to call this error, we're going to call it something else. We're going to call it a loss function. So if my target value is a number and my prediction is also a number, I can subtract those two. So my loss function is just the difference between 2. And remember, I square it because I don't want negatives, so they all cancel out if I sum over all of the errors. But I'm going to call that a loss function. If my prediction was something else, it was, is this a malignant nodule on a CT scan or is it not? My loss function would look different. This would not be the loss function for that. So every kind of problem that we are going to develop the deep neural network for will have a different loss function. It just depends on the very type of variables that we're dealing with. This is not a CT scan. These are 2 sets of numbers, a number I'm predicting and a real number, ground truth number. So this would be one loss function. Every problem will have its own type of loss function. Now, some people make this distinction between the two. Some say loss function, cost function is just the same. It's a new field. There's so many terms, and there's no real standardization of what these terms are. So I'm separating these 2 terms out just for clarity's sake. I'm saying this is my loss function. But remember, I have more than one sample. So I've got to somehow combine and express all the errors in one. And one way to do it is this. I'm going to sum up all my errors, so sum up each of these over each of the i's in the sample. I'm going to sum all of them and divide by how many there are, and I'm going to call this my cost function. So the cost combines all the individual losses. So what this is, what is it? Well, it's just the average of all the individual losses. And you get other cost functions. So this cost function is particular to this problem where I have a numerical output and a numerical predictor, a numerical target, which is predicted by a similarly numerical value. So this would be a cost function in this instance. Other loss functions will have other cost functions, and we can look at them. In the computer code, in the end, it's going to be very simple. They each have names, and you just type in the name, and the computer knows what to do, no problem. But I want you to understand the concept. Now, this L, remember, was this. So if I plugged in this into this equation, and the y hat was actually that, if I plug that into that and that into that, this is what I'm left with. This is the full thing. So the cost function, given these 2 unknowns, beta sub 0 and beta sub 1, is this thing. I'm going to do beta sub 0 plus beta sub 1. They're going to stay the same over all these I values, sample 1, sample 2, sample 3. But I do that multiplication, I do this addition, I subtract that from the real value, I square that, I sum over all of these, I divide by how many there are, and that's going to give me the cost. Now let's put this into action. What we're trying to do though here is we're trying to get values for beta sub 0 and beta sub 1, so we have this very best line to make the minimum error. My cost function has to be, the value of all of this has to be as small as possible. And if I pick the right value for beta sub 0 and beta sub 1, I'm going to have the smallest possible cost. That is my aim. And to put it that way makes it very easy to transform that into mathematical equations. And that is really what we want. So let's just create a contrived example. I'm going to have 5 values, 1.3, 2.1, 2.9, 3.1, 3.3. Those are my feature variables, and I'm going to just add some random noise to that. You can look at this line of code so that I have a target value based on the feature value. I know that there's some connection between the two. And right here is where we plot it. So here's my first one. The input variable was 3.9, and the output variable was 0.7. It was 2.1 for my feature variable, and my target value is 2.2. For this one, it's 2.9 feature, 3.4 target, 3.1 feature, 1.9 target, 3.3 feature, 3.5 target. And I can actually just write them here. You see the 1.3, I have to create something that will predict 0.7. I have a 2.1, it has to predict 2.2. Given 2.9, I want to predict 3.4. Given 3.1, I want to predict 1.9. Given 3.3, I want to predict 3.5. So let's plug that into this equation that we have here. This equation, it's just the sum over all of these pairs, that the xy pairs that we've got here, and we see them here. Each of these are xy pairs. There's the xy pair. So let's plug them all in. So there's the first one, the 1.3, and the 0.7 is the true value. 2.1, my predicted, 2.2, the true value, 2.9, 3.4. We subtract that, we square each of those, we sum, and we divide by how many there are. And there's my cost function now. You can do that all on paper, and you'll see it comes out to this. There's my equation. My cost is 6.55 minus 4.68 beta 0 plus beta 0 squared minus 13.1, etc., etc., etc. This is an equation in two unknowns, beta sub 0 and beta sub 1. And I can graph this, an equation in two unknowns. I can graph this, and this is going to be some shape in a two-dimensional space. Two-dimension because I have two unknowns, and this is what it actually looks like. This equation looks like this. And how can I minimize this cost function? C is here on my z-axis, my up and down axis. Well, it will be a minimum when these two values, beta sub 1 and beta sub 2, gives me the lowest value on my z-axis. My z-axis goes up and down here. And somewhere along this curve, you can see from left to right, it curves up and it curves a little bit there. Somewhere there's a value for beta 1 and beta 0 that will make C, here on my z-axis, the lowest possible. And those are the values I'm after. I'm trying to learn what these two values should be, beta sub 0 and beta sub 1, so that my cost function is at its lowest. That will give me the best lines, the best values for my parameters, beta sub 0 and beta sub 1. And remember, I can use those as slope and intercept, so I can draw a line through these points that will minimize the error. Because remember, if the line goes here for a given input here of 2.1, it might predict 1.75 right here. And there's a difference between 1.75 and the actual 2.2. But I want all of these errors along this line to be minimized. And the way to do that is to change it into a mathematical equation. Here we have two unknowns. It draws a shape for me in three-dimensional space, and I want where this value on this, what values for beta sub 0 here and beta sub 1 there will give me a little point here somewhere, and I want it so that it is the lowest point on the C, on the z-axis. How do I do that? We do that through taking what we call partial derivatives. Now I'm going to make that little video on partial derivatives for you, so that you can just, if you want to know where it is, if I take the partial derivative of C with respect to beta sub 0, I keep beta sub 1 as a constant. If I do the derivative with respect to beta 1, I keep beta sub 0 as a constant, and there I get the two derivatives. Now what is a derivative? It is a slope, and I'm very interested in those slopes, because at the minimum, my slopes are going to be 0. I'll show you down later on down, I'll give you a better explanation for that. But there are my two partial derivatives. And I want to set each of them equal to 0. So there's the first one, and there's the second one, and I'm just setting them to 0. I want where the first derivatives are 0. So what I can do is this minus 4.6, take that over to the other side. The negative 13, I can take that to the other side. So I'm left with these two equations. This one, it won't draw. This one here and this one here. So there's two equations and two unknowns. I can write that as an augmented matrix, and that's why we need linear algebra. So we need both derivative calculus of derivatives, multivariable derivatives, and we need linear algebra. I can do elementary row operations and reduce this to reduced row echelon form. And again, watch the video on that, which gives me a solution for beta sub 1, which is beta sub 0, which is negative 0.5, and beta sub 1, which is 1.1. And there we have beta sub 0 is negative 0.5, and beta sub 1 is 1.3. That's the intercept and the slope for the best possible line, because by putting the slopes to 0, don't worry about it, it'll give me the values for the best possible line. And let's cheat again using linear models here inside of R, and I give it the little formula for that, and we see the two values there as predicted, the minus 0.5 and the 1.13 for my intercept and my slope, no problem. That's the basics of it. How did it do that? Let's just reduce this instead of this three-dimensional space, because we have two unknowns. Let's reduce this to a single variable, so we have two-dimensional space and not three-dimensional space. And I want to make it so simple by this very simple equation that you must have seen at school, y equals x squared. There it is. For every x that I put in here, 1, I'm going to land at 1 there, because 1 squared is 1 and 2 squared is 4, so I'm going to land up with 4 there, etc. Very simple. Now don't get this x and y confused with what we had above, the y being the target and the x. No, no, no. I'm using something from school, x and y, but remember they represent on this just a beta 1. In fact, the x here is, I'm just going to use it to be beta 1, and I'm trying to find where on this beta 1 line, this x line, where must I go on this x line to get this curve that my model created, just as my model created this curve up here, this three-dimensional curve through my lost and cost functions. Imagine that my cost function is now just this thing. I want to know where on the x-axis is this thing at its minimum. Now it's very easy to see. The minimum is right down here where x is 0. But imagine, it's a convoluted shape as we had here. It's not easy just to see there where the minimum is going to be. And as we go with more and more and more predictor values, feature variables, it's going to be this convoluted shape and multi-dimensional space. You wouldn't know where to start to get to the minimum. And that's that minimum where we're after. Now, one way to go about it is what is called gradient descent here, as opposed to what I used up there to do it. And the gradient descent says, let me just blindly start anyway. Let's start here at negative 2. What is the slope here of negative 2? Well, I've got to take the derivative of x squared. The derivative of x squared is just 2x. Watch the video on derivatives if you can't remember. And at negative 2, 2 times negative 2 is minus 4. So if I draw a line that just touches this point here where x is negative 2, or I should say beta 1 in our analogy here is negative 2, it'll be the slope right here, and the slope is negative 4. You can see a line, a tangent line that just touches the minimum would be a slope of 0. So we're trying to get to a place where the slope is not negative 4, but 0. So how do we get from a point, now it's again, as I say, just looking at this is easy, but imagine in multi-million dimensional space, it's not that easy. But I can use this slope here to get closer to this idealized point where x is 0. And the way that I do that, I take this negative 4 and I multiply it by a tiny little step called what we call a learning rate. Say that's 0.01. So I'm going to take 0.01 minus the negative 4, and that gives me minus 0.04, but I subtract that, I add a negative to that, which gives me plus 0.04, and that is my step. So I'm going to go from negative 2, using my slope, which was negative 4 there, and I'm going to step to the right 0.04 places. That's going to bring me right about there to negative 1.96. At negative 1.96, I'm going to get the slope again. I'm going to plug that slope in here, multiply it by the learning rate, and subtract that from where I was before at negative 1.6, which is going to bring me closer down. And so I'm going to go closer down, closer down, closer down, closer down. And every time, I'm going to see my slope getting closer and closer to 0 until I approach this spot here where the slope is 0. I've used gradient descent by using the derivative of each point to get to a lower and lower and lower and lower point. And just look back, just think about it at the moment. I can construct a cost function, no matter in how many dimensional space. I can then use this idea of gradient descent to go down on this slope. As I say, as we go up and up in dimensional space, we have to use these partial derivatives, not just a single derivative. Here I said the derivative of y with respect to x is just 2x. I have to use partial derivatives. And I have to walk in each direction. So if I go back up here, oh, let's go. If I just randomly started at a point, and that's what we do, we randomly start at a point. I walk in this direction, and I walk in that direction. And if I combine these two separately, so I work from here to here, I hope you can see the cursor, and then I walk from there to there, that would have been the same as just walking straight, that's the same as walking straight down there, but I'm still walking straight downhill. But instead of one single step, I take two steps, one in this beta sub 0 direction and one in the beta 1 sub direction, and if I had multi-dimensional space, I would combine separately all of those, and all those steps together would eventually be somewhere lower down the slope. And I'll use through all the partial derivatives in all the directions, I will combine all of them and walk further down the slope and further down the slope and further down the slope until I get to a point where the slope is 0. So think about it. You're standing somewhere in a valley, close your eyes and you have to walk down the valley. What you need to do is to pick a direction, and just in that direction, just a straight line through your feet. Which way goes up and which way goes down, just through your feet. So you'll take a step in the direction across that line, straight down. You'll turn 90 degrees orthogonal and draw another line through your feet. And at that line, which is now perpendicular to the first one, just draw a line, that line, see which direction is up the slope and which is down. Just take a small step down. So combining those two little steps you took would have been just stepping across once. Now again, draw a line again, parallel to the very first line you had, and decide on that line which side is up, which side is down. Walk a little bit down. Turn that line 90 degrees. And again, which way is up and down? Let's take a little step down. Those two combines will be down. And so you can combine these steps at 90 degrees to each other. Say left, right, left, right, left, right. And so you can work your way blindfolded to the bottom of this valley. Just thinking where you're standing and which way is down, which way is up, but in two different ways. If you were a being that can live in multi-dimensional space, of course, you would have to do this for each dimension that you are. And that's what we're doing here with partial derivatives. We're just looking at a single direction, take a step for that one, take a single direction, take a step for that one. And for all of those combined would have been one huge leap. And that's what we're trying to do and simplifying it here by just showing you how we step down using the slope, the partial derivative on each of these, and eventually we're going to get to this bottom. And that minimum is where the values that we're after, the parameters that we're after, is at its best, where the prediction is going to be as close as possible to the ground truth. So that's it. We really looked deeply now into linear regression and how that fundamentally in our head makes us understand that we can create this cost function, and we can minimize this cost function in a way so that we walk down this slope of this cost function to get the very best values to minimize our error. And that is what we're going to do with deep learning. We're going to create this model, and we're going to have, in some of these, there are millions of parameters, not just beta sub 0 and beta sub 1. There are millions of them, and we call them weights in deep learning. Same thing, we're going to have millions of them, and we have to optimize them so that all of their values are at their very best, so that in the end, our cost function is at a minimum, and the error that we make in our prediction is as close to the ground truth as is possible. And there you have a deep learning. So from here, we're going to start looking at deep neural networks themselves, but hold on tight to these very basics. Watch the video on linear algebra and the video on derivatives. They will help you out. You don't have to, as I said, if you really want to get behind this, if you really want to get to doing some research really on deep learning itself, as opposed to applied deep learning, which we do in healthcare, we apply it to a problem, then you've got to understand multivariable calculus, you've got to understand linear algebra, and I've got those videos out. I've made plenty of those lectures. You can watch them, and I'll put the links down below. I'll speak to you again. Now, in my series on doing deep learning, specifically for people interested in healthcare-related problems, but for anyone who really is interested in deep learning and really struggling just to get to grips with what this is all about, what the mathematics is all about, I just want to make this video. I'm going to make another one as well. This one about let's just call it a video about tensors. Now, a tensor, we're going to build our framework of deep learning, or we're going to build our deep learning models on the framework called TensorFlow from Google. So what is this tensor? Now, tensors come in ranks, and you actually know quite a few tensors. So let's just start off with a rank 0 tensor. A rank 0 tensor. And that's nothing other than what we call a scalar. And a scalar, let's see, S-C-A-L-A-R, scalar, that's nothing other than a number, like 4 or 7 or -1. Those are all numbers. That's a rank 0 tensor. Now we move on to a rank 1 tensor. And a rank 1 tensor is nothing other than a vector. Now let's think about vectors just for a minute. So vectors can represent many things. One way to visualize this representation of a vector is to think of a plane. Most importantly, we have these two axes, and they are orthogonal. In other words, they're at a right angle to each other, and that can represent 2 dimensions. And I can have a point in 2 dimensions, and I can represent that by this arrow with its base here and its head there, representing a vector. And that vector in these 2 dimensions will have a very specific, you can say an address, for instance, and that would be this x-axis value and this y-axis value. In other words, this vector, let's call this vector v, and I put a little line under it to demonstrate that it's a vector. It has these values for x and y, and there's different ways that we can write this. For instance, I can write vector in this format, an x value and a y value, and this is called a column vector. And you know from spreadsheets, this is a column and those are rows. So this column vector will have a size. It has a size of 2 rows times 1 column. It's a 2 times 1, always row first, then column. So it's a 2 row, 1 column vector. Well, we'll call that a matrix, and we'll get to that now. But a column vector has size 2, 1. We could also just what we call transpose this, and if we transpose this, it becomes x and y, and that we call a row vector. Just for you to become slightly familiar with these terms, that will be 1 row and 2 columns wide. When we say we transpose, we just turn the rows into columns and the columns into rows. That's not what it's about. We're representing a vector as this point in here. It's 2-dimensional space. So a vector here, a rank 1 tensor, will be a vector, and that is a vector. And a vector, depending on how many elements there are, can represent points in space. If it's a 1-dimensional space, that will just be a point on a line. That's 2-dimensional space. In 3-dimensional space, which we usually draw like this, that's orthogonal. So for instance, that's on the floor, that's standing up. So we usually make that the z-axis, the x-axis, and the y-axis by convention. And any point in space here will have these values here and this value there. And remember, it stands out. It can be in the YZ plane there, but it can also stand out. In other words, it will be some point that stands up in inside of this three-dimensional space, and it'll have a z component too here, making it a 3 by 1 column vector. And depending on how many elements there are, we can represent multi-dimensional space much more than we can just perceive in our three-dimensional world by just adding more of those. Then we get a rank 2 tensor, and that's actually just a matrix. And that's a very interesting thing. We've seen matrices before. Just think of all the rows and columns in a spreadsheet. So I can have values 3, 2, minus 4, 1, 6, 7, 2, minus 3, 4. And I can put it like this, and that is a matrix. A matrix here of 3 columns. So I can see this as 3 column vectors combined. There's many ways these matrices are so useful. They can present so many things. Again, I count the rows and columns, which makes this a 3 by 3 matrix. And then we get a rank 3 tensor. Now it becomes really interesting, because all I do now is I add layers behind this one. So I would have this representing here, and then behind it another one, and behind that another one. This will make this, if that was 3 by 3 as well, a 3 by 3 by 3 rank 2 tensor is a matrix, and the rank 3 tensor is where I have these multiple layers of these matrices behind each other. And so I can go on to rank n tensors, and it becomes very complicated, but you can just add in more dimensions, more spaces. What I don't want you to get confused with, though, is how many elements here gives me how many dimensions in space. That is different from what we have here. Rank 2 tensor, rank 1 tensor is a vector that can live in multi-dimensional space. That doesn't mean that's one-dimensional. This is just the rank of the tensors. And that is what we're going to work with. Our data is going to be represented in the way that we manipulate values, the way that a deep learning network learns these parameters that we're going to look at. They are all going to be inside of some other rank of a tensor. I'm going to clean the board, and we're just going to do a few what we call linear algebra operations on specifically these two, rank 1 and rank 2 tensors, just so that you become familiar with it. Now, the first thing we're going to look at is the systems of linear equations. Let's put that here. Systems of linear equations. Not strictly necessary for deep learning, but it helps us to understand some of the concepts that we are going to deal with. Systems of linear equations. Now, linear equation, remember those are just very simple algebraic things. Let's construct our own one. Let's make it, let's make something like 1 and 4, let's put in minus 2 and 1 there, and let's make this 3 and 3, and so that's a plus, and we make this, let's make that 2 and 2 and 3 and 3. Let's see where that ends up. Let's say that is 2, so that's going to be 2 minus 6, that equals negative 4. And we're going to make this, that is 8 plus 3, and that's 11. So I'm just cheating here. I'm creating my own system of linear equations. Now let's imagine that these, that we know the answer for, we know that's 2 and that's 3. Let's change those into two unknowns. We'll call that unknown x and unknown y. So what we have there is 1x minus 2y, and that is minus 4. And we have here 4x plus y, and that's going to equal 11. And that's what I mean by a system of linear equations. A system, because there's more than one, and I can get a solution for both of these, and that solution, it will satisfy both of those. It will satisfy both of those. Now, how can we solve that we get values for x and y that solve both of these? By the way, this is linear because I don't have x squared or x times y. It is some constant multiple of x and some constant multiple of y. In this instance, 4 times x. In this instance, -2 times y. It's just constant multiples of that. And I know if I plug 2 in there, and if I plug 3 in there, it is correct. And if I plug 2 in here, and I plug 3 in there, it is correct. So, let's try and solve this. What are things we could do? Well, one of the first things we could do, we could just swap these two around. Let's have that. 4x plus y is 11, and I have x minus 2y equals minus 4. So I've swapped these two around. That's one thing I could do. I could multiply this throughout by a constant. So let's still have 4x plus y equals 11. And here I'm going to multiply this throughout by -4. So that gives me, if I multiply throughout, I'm not changing it. I'm multiplying this side by -4 and that side by -4. Nothing has changed. So I'm going to have -4x. I'm going to have positive 8y. And I'm going to have 16. So here I swapped out. Here I have a constant multiple of 1. And now what can we do? Remember, these are equations, meaning this side equals that side. So if I do something to this side, I must do exactly the same thing to that side. So let's do something to that. I'll stay with 4x plus y equals 11 in my first row. But in my this second bit, I'm going to add this to that. But this is also equal to this, so I can do this to that. That still means I did the same thing to either side, because these two things are equal. So if I were to do that, if I were to add this to that, that's going to cancel out. This is going to become, so that makes it 0x, and this makes it 9y, and on this side we're going to have 27. And I have these now. Let's carry them on here. So I have 4x plus y equals 11. And I have this, but I can simplify this one by just dividing throughout by 9. 0 divided by 9 is still going to be 0x. 9 divided by 9 is going to give me y. And 27 divided by 9 gives me 3. 9 times 3 is 27. And lo and behold, I have a solution for y. And we know we're right because we cheated in the beginning and we constructed it that way. So that gives us a solution for y, which I can now plug into that. So I have 4x, and I know y equals 3. So 4x plus 3 equals 11. So 4x equals 11 minus 3, which is 8, and x equals 2. Beautiful. But look at what we've done. There's 3 very elementary things. We call those elementary row operations that we did. We swapped things around. We multiplied throughout by constants. Here we multiplied throughout by 1 over 9. And we added this constant multiple of one row to another one. Remember, these two things are exactly the same. That's why there's an equation sign. So if I took this side and I added that, then I can take this side and add to that. Then I've done both things, the similar thing on both sides of the equation sign, because these two things are equal to each other. So let's clean the board, and let me just show you if we use rank 2 tensors, how we can also do that. So let's use this and write this as what we call an augmented matrix. So an augmented rank 2 tensor. So I'm going to just have x there, remember, and minus 2y. Let's write just the coefficients. So I'm going to have 1 and a minus 2, and that side a minus 4, and on this side I'm going to have a 4, and I'm going to have a 1, and I'm going to have 11. And that is an augmented matrix. So I'm just shorthand, I'm leaving out the x, and I'm leaving out the x, and I'm leaving out the y, and I'm leaving out the y. What can we do? One of the elementary row operations, we just swap these around. 4, 1, 11. Technically I didn't have to do this, but I just wanted to show you there are 3. And I'm going to write this one down below, but I'm also going to multiply it out by a constant, which was -4, which was 16. And it's just shorthand for what we did before. Those are the elementary row operations. So I can stick to the first one. And for the second one, I can add the first one, elements of the first one to the second one. So 4 plus -4 is 0, 1 plus 8 is 9, and that gives me 27. I can multiply this throughout by 1 over 9, which gives me 4, 1, 11, 0, 1, 3. And that's how we got to read off that the y value. Remember, this is x, this is y, so 1y equals 3, y equals 3. Now I can multiply this throughout by -1, so that will give me 0, -1, 3, and now I can add this to the first one. 4 plus 0 is 4, 1 plus -1 is 0, and 11 minus 3 is 8. And I can multiply through this throughout by -1 again, so I'm back with 0, 1, 3. And then I can multiply this first one throughout by a quarter. That'll give me 1, 0, 2, 0, 1, 3. And there's my solution. It is in what we call row-reduced echelon form. In other words, there's just leading ones, and below and above every leading one, there is a 0, so that I can finally get my solution. 1x equals 2, and 1y equals 3, exactly what we have there. So elementary row operations. So there I've shown you the system of linear equations. Let's just get back to some simple things. Let's just add rank 1 tensors. Rank 1 tensors. So to add rank 1 tensors, they must just be in a similar dimension. So I can have a 3-dimensional rank 1 tensor, 4, 3, minus 1. And I can add to that a second one, let's have a 0, 1, 4. And that's very simple. It's element-wise operation. So it's 3, 4 plus 1 is 5, -1 plus 4 is 3, and there I have my solution. Very easy to do rank 1 tensor, which are vectors, vector addition. They must just have similar dimensions. Now let's multiply a matrix times a vector. Now there's various reasons why you would do that. We can call this an operation on a vector. If we look at physics, it doesn't matter what we do, we just want to do. And I want to show you that there's just something that must be kept in mind, and this is very important when we get to TensorFlow and when we get to designing or thinking about at least our deep neural networks. If I have a matrix 3, 1, and let's make it 2, 2. So what size is that? That's 2 by 2 matrix, 2 by 2 rank 2 tensor. And I'm going to multiply that by a vector 2, 1. And I'm going to put that down there, and that is 2, 1. And the reason why I put that, because it makes the actual doing it on paper very easy. But what I'm doing here is I'm multiplying a matrix by a vector. Very important that this second value, the column number, and the row number of that one, they must be equal. If they're not equal, you cannot do that multiplication. These don't matter. It doesn't matter what these two values are. But if I have this matrix, and let's call this matrix A, and we call that vector V, if I'm doing A times V, the matrix comes first. The vector can technically also come first, but there's something else about that. But the second number here must equal the first number there. So the column number of this one and the row number of this one must be equal, otherwise you cannot. And the solution will be what is left. The solution will be a 2 times 1 tensor. And depending on what rank it is, all these things, from a single number till all these multi-dimensional things, here at the bottom, they're all tensors. So let's just call everything a tensor. So the result is going to be a 2 by 1 tensor. And what we do is very simply, I've written it like this because it makes it simple. I'm going to look for this space. We've already seen it's going to be 2 by 1. So those are the two values, and it's very simple because I can look along this one and along that one to get to this one. So it's going to be 3 times 2 is 6, plus 1 times 1 is 1, 6 plus 1 is 7. And 2 times 2 is 4, 2 times 1 is 2, 4 plus 2 is 6. And there's my solution, 7, 6. That is a matrix times a vector. Very important, and very important that you understand that that number and that number must be exactly the same, otherwise you cannot do this multiplication, and that is going to be a very important first step in a neural network. By the way, if it sounds like the world is coming down, right outside my office they're building a new neuroscience center, and it is very, very noisy and really driving me nuts. So a very important thing, this matrix times a vector. I can also have two matrices, and I can multiply them with each other. And as long as, say for instance, this one is of size 4 by 5, that means this one must be size 5 by whatever method. It makes that 7. It doesn't matter. Those two must be the same in that order. The result will be a 4 by 7 tensor. The result will be a 4 by 7 tensor. And as I say, those are very important things. So that's a brief recap of what we call linear algebra. So some very basic concepts in linear algebra. And we know that this is very important for us in designing neural networks. Now, you don't have to know more than that. If we write the lines of code using TensorFlow or Keras, as long as you have these basic concepts in the back of your head, you really don't need this full understanding of this. Just in case you have not done this before, you did it a long time ago, just a little bit of a refresher of what these things are all about. I'm going to make another short video just on partial derivatives, because it is linear algebra is the one important part of deep learning, and the other part is just derivatives. We've got to be able to do derivatives. Once again, we're just going to write a line of code, and the derivatives are going to happen automatically. But I think it's still important that you just have some basic concept of what happens with linear algebra, specifically this, and what derivatives are. So in this series of mine, just on deep learning for people who are interested in deep learning, perhaps more specifically for medical personnel, healthcare personnel, people involved in healthcare who want to solve problems in healthcare using deep learning, just making these couple of videos just to get behind some of the mathematics. Now I have a short video just on linear algebra, which is very important in deep learning, and this one is just going to be on derivatives. Derivatives. There we go. Now, if it sounds like the world is coming to an end, right outside my office here, they're building a new neuroscience center, and over the last couple of months now, it's already, well, it's driving me insane. There we go. So derivatives, very important. We're going to have this concept in deep learning called backpropagation, and that really depends on derivatives. I want you to relax, though. You don't actually have to do these derivatives. You're going to write a line of code, and the computer's going to do the derivatives for you. You should have some basic concept, and if you haven't done calculus in a long time, this is it. Now, I do have two very large playlists on YouTube, one on linear algebra and one on multivariable calculus, and I'll link them below. If you're really interested, you can have a look at those more than 100 videos. Really, if you want to get really deep into the topic, I've got those playlists for you. Let's do a few short minutes just on derivatives. Now let's imagine an equation. I have y equals x squared, and that's it. Or let's make it plus 4. X squared plus 4. So if we have this, it's going to be something like this, and that's going to be 4, and we have this nice x squared plus 4. Remember, behind the scenes, there's another x here, but it's to the power 0. Anything to the power 0 is just 1, and 4 times 1 is just 4. And remember how derivatives work. You must have seen derivatives at school. If I have x to the power n, this is just simple. And if I take dy dx, dy dx is one way to write it, or y prime you might have seen. I bring that n forward, and I take 1 away from the exponent. So if this was y is x squared, y prime is going to be bring that n, which is now 2, forward. That's x, and I'd subtract 1 from it. That means 1, that's 2x. And the same, this is exactly what we have here. Y prime is going to be 2 times x, and if I bring the 0 forward, That's 0 times 4 is 0, and 0 times anything is 0. So if we have a constant, the derivative of a constant is 0. It is gone. Okay, so if I have something like y equals 3x squared plus 2x plus 5, I have that dy dx is going to be equal, bring that forward, 2 times 3 is 6, subtract 1 from that, so there's just 1 left, bring the 1 forward, 2 times 1 is just 2, and there's a 1 there, 1 minus 1 is 0, so there's 0 left at the top. Anything to the power 0 is just 1, so 2 times 1 is just 1, so it's 6x plus 2 is that derivative. Now, let me just clean the board. Now, that's very simple if I have a single variable, but what if I have two variables? We usually write that as z, and let's have z equals 6x squared plus 4xy plus 3y squared. Now I have 2, and how am I going to take a derivative of this? If I look, this will be in 3 dimensions, and we usually have this as the xy plane, and that's orthogonal to each other, so you can think that's in the corner of the room, and here we have z. So we're going to have that. This thing, I can't draw that, but imagine it is just going to be this 3-dimensional thing, and space is not going to look like that, believe you me. But just imagine. Now what we need to do in linear algebra is we're going to, the system has to learn certain values. And it has to learn those values, and the way that it learns it is it writes a multivariable equation like this. Now, some neural networks we're going to write, and they're going to have more than 1 million parameters, more than 1 million of these, x, y, z, ABC, there's only 26, but imagine we carry on and there's over 1 million. So it's going to be this equation of over 1 million. And it's also going to eventually, you could, if we had access to so many dimensions, imagine 1 million dimensional space, but it will be some convoluted shape in this multi-dimensional space. And what we really want is the minimum. Where in this, now this is very easy in 2 dimensions, where is this whole multi-dimensional thing at its minimum? And then when it's at that minimum, that's the point we're after. All the values of x, y, z, blah, 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 all those millions of parameters, if I had a value for each of them, and so that that whole equation, which is some graph in multidimensional space, is at its lowest point, at its minimum, that is the value that a deep learning network is after. If it gets that, it has the best values to answer the question that we're trying to answer through deep learning. So how do we get a derivative? How do we get to the lowest point? Well, if we just have a 1-dimensional space, let's have that. We can start at any little point. The derivative, remember, is the tangent point, the point of a straight line that just touches that. In 3-dimensional space, it will be a flat plane. Imagine a piece of paper that is flat, and it just touches wherever the space, just in one little point, but that'll be a plane. In 4-dimensional space, it'll be a hyperplane. In multi-million dimensional space, it'll be a very convoluted hyperplane. But it touches our graph in one point, and I can use that slope to get to a point here. There's something I can do to get to this point here, and at this point the slope of that tangent line is going to be 0, and the plane that lies here that touches just there is going to have this slope of 0. So in 1 dimension, as I said here, in this dimensional space it's easy. I have a slope, and we use the slope to update to get to a new point, which will have its slope, which will have a new point, will have its slope, and we're going to change the slope, change the slope, change the slope until we get to a slope very close to 0, and then we know we're okay. We know that we are okay. Now this is easy to see, but imagine a multi-dimensional space which we can't fathom in our brains. You don't know where it is. It's like you are in the space and you start walking blindly. Now imagine blindfolding yourself, and you're in a place where there's a bit of a valley, and you have to get to the bottom of the valley. You can wander around until you go lower, 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 until you get to the bottom of the valley. And that's exactly what we're going to do. We're going to be somewhere, and then we're going to start taking steps. Now, remember when we looked in my video, if you watch that, just on the simple linear algebra for deep learning, if I want to get to this point, and I see this point as a vector, what I could do is walk that way, but I can move this one here, so that's there. So to get to this point, I might as well walk this way and that way. So that will be so many units of x. I'll walk in the x direction, and so many units in the y direction. If I make that walk, I end up in that same place as if I went straight there. And that's what we're going to do here. We're going to walk in the x direction, which points downwards for us. And then we're going to turn 90 degrees and walk in the y direction along the slope that goes down. And if we do those two things combined, we've gone further down. And the more dimensions it is, you'll just have to do this in more one dimension. But what we do is when I walk along the x-axis, I keep y constant. I don't change on the y-axis. And when I change the y-axis, I stay in one spot on the x-axis. I see those two as constants. And that's exactly what we do when we do derivatives. And we write the partial derivatives like this, and I'm just going to take the derivative with respect to x. I'm going to see y as a constant. I'm not changing on my y-axis, I'm just staying straight on the x-axis. That means all the y's here are actually constants. So if I do this derivative, that x I can do, that's going to be 12x by bringing the 2 forward. Now, that is a constant. There's a 1 there, I bring the 1 forward. 1 times 4 is 4. The x disappears because it becomes a 0, and the y is still there because it is a constant. That whole thing is a constant, and the derivative of a constant is 0. It's gone, because remember there's an x0 here. If I bring the 0 forward, that's nothing. And that is my derivative of z with respect just to x. And if I do the partial derivative of z with respect to y, I see x as a constant. That means here's a y0 here, so that's going to disappear. There's a 1 there, so that's going to become 4x, and that's going to become 6y. And that's going to become 6y. And those are partial derivatives, and all you do with partial derivatives, you keep all the others constant. So if there was also w's and v's and a's and b's and whatever in there, you keep them all constant. You only look at the derivative with respect to this. You keep the other one constant. And eventually, you'll get this multidimensional pointing things, and you combine all of them. You do the one, then the other one. As you walk there and there, you walk along this way, then along that way. And in multidimensional space, if you have basis vectors that are all orthogonal, everything is going to lead you in a different direction. But if you combine all of those things, you're at a lower point. And now we've got a new point on this thing. We can take a new slope, do all the same thing again, and eventually we'll be lower. And so we will go until we get lower and lower and lower if we just repeatedly do this. And that is why we have these things called derivatives. So together with linear algebra, derivatives are very important. Now, if this was all Greek to you, don't worry about it. If you're interested in it, watch my over 100 videos just on multivariable calculus. It's quite interesting, multivariable calculus, but really you don't need that for where we are going. As if you just have some mild, slight concept of what is happening here, that's all that's required. We don't have to take any derivatives when we design. We just have to understand that that is what the algorithm is doing. It is trying to find a path that lowers the slope so that we can get to this bottom point, and that, in any dimensional space, is what we are after, because that is going to be the best values that are learned by the deep learning network to give us the most accurate solutions. In this video, I want to take a closer look at gradient descent. Now, this is a series for healthcare workers, healthcare professionals, those perhaps people, well, everyone, perhaps some people who have an in-depth knowledge of mathematics and computer science, but really want to contribute to this field. So this is not absolutely necessary for you to be able to write the code in the end, but I still feel that it's important, and you can watch that. Now, on the video, which I'll link to up here, the video on just looking at linear regression, to develop that intuition, we really looked at developing this cost function. The cost function, remember, we have this set of feature variables, we're going to multiply them by these parameters, and we're going to we're going to get to a result. That result is going to be different from the target. We subtract those two from each other, we square them, and then somehow we go through all of the samples in our data set, and we can either, one of the best ways is just to average those, and that gives us a cost function, and that cost function will be a function of all of those parameters. And when we just had a single variable, remember, we just had a single feature variable that still gave us two parameters that we had to find that is in two-dimensional space. And if we have many more features, we're going to move into multi-dimensional space. So we have this function in multi-dimensional space. We can draw it in multi-dimensional space. What we want to do, or what we are saying mathematically, is at the bottom of this function, at the minimum, because remember, on the x, if we boil this down to a single variable, which is not realistic, but a single variable, on this axis I'm going to have my values for beta, and on this axis my cost. And I want to minimize, I want to see where the cost is at its absolute minimum. Now, as I said, this is idealized. I'm bringing it down to a function of a single variable. F of x at school, y equals f of x. And here we have x squared minus 3x plus 2, something to that extent. Doesn't matter. We have this cost function, and I want the point where the cost is at its lowest. I mean, for me, that is beautiful that we can break down this problem where we want to create this model that is as accurate as possible. We can break that down into some function that we want the minimum of. So when we have that, there must be a way that we can say, well, initially, we just give a random value. We're saying we are starting right there. Let's start right here with a certain beta value. That certain beta value is going to give me a certain cost. And there's the cost. And I want to now know, well, that is just at random that point was chosen, and that's how it's done in deep learning. I want to get there. How do I get there? Well, I have to use what I have, and I have to update this value. There was in reality, this is the point I am looking for. In reality, I have got to move from this point to that point. How do I do that? And we use this idea of gradient descent. Obviously, the gradient, if I'm standing on top of a hill, there's a gradient down. I'm using gradient descent. I want to go down. I want to descend along some gradient. And a gradient at a specific point on a graph is nothing but a derivative. A derivative. And we've looked at derivatives. I need a derivative. But let me just show you then how this really works, because I can use this derivative to generate a new value for beta, which will be here, which will give me a lower cost, but I've got to get from there to there. And how do I get from there to there? And eventually, in these tiny little steps, how do I get there? Again, as I say, just by looking at this, it's easy to see it's got to be there, but in multidimensional space with lots of beta values, it's impossible to do. How do I physically do that? Because what I will have then is a better beta value, which I will put into my cost function, running again through all of my samples, averaging all my errors, and I'll have a new cost function with this new beta, and that will be slightly better and better and better, and I run through it again and again and again until I eventually approach this point. So what I've done here is I'm just expanding this so that we have this better view. So I start with this random value of beta right there. I have some value of beta which I've plugged into my cost function, and that is going to give me wherever this is, and it doesn't matter which side I start on. It doesn't matter which side I start on. So I start with a given beta value. Now, how do I get from this one to this one, which might be slightly better? The trick is to take this point and to get the derivative of this function. So I'm going to get the derivative of my cost function with respect to this parameter of mine, the first derivative. And remember, the first derivative is nothing other than a slope. So I'm going to get a tangent line which passes and touches that point just there. That's all I'm going to have. And what I'm going to do is I'm going to say I have an old beta. Let me say this beta old, the one that I start with. And I'm going to update it by taking that and subtracting from it some learning rate, which I'm going to just put a Greek symbol for alpha, and we'll see what that is about. A learning rate multiplied by this derivative, dc d beta. And why negative there? What is this? Why this negative? Well, what I'm going to do, I'm going to say beta new, my new one, which I'm going to move towards, is take wherever I start at that value and subtract from that minus the product of these two things. Now, if I'm on this side of the ideal point, my slope will always be negative. Remember, this is a negative slope, and that's a positive slope. Because we go from left to right, so we're going downhill, that's a negative slope, that's a positive slope. So if I have a negative slope, this value here is going to be negative, and a negative times a negative is a positive. So my new one is going to be the old one plus something, this value plus this one, so I'm going to move slightly in this direction. If I was on this side, it would have been a positive, so there will be a negative times a positive, which will be a negative, so my new beta will be the beta minus something, so I'm going to move in this direction towards this point, so it works out beautifully every time, that no matter which side I am, if I do this negative, I'm always going to move in the right direction. This alpha, as I said, is called a learning rate, and that determines, how big these steps are that we take. And usually we have alpha values of, say, 0.01, 0.001, we can even 0.1, there's these orders of magnitude difference between them. Some people, like Andrew Ng, likes 0.3 and 0.03 and he goes up in steps of 0.03 there. It just multiplies by 3 every time and goes up from there. Doesn't matter, it's in this sort of range. And that ensures that this step is not too big. And I'll show you why we don't want this big step. But this is a thing of beauty, because I now have a new beta, which sits right here. I can go up and see what the cost is there. I see the cost is less. And this now becomes my old beta. And at this place, I take the derivative, which I can now plug in there, multiply it by the alpha, subtract that from the old, which is this one now, and get a new one, which is now going to be here. And I'm going to repeat that story every time going through that whole algorithm, and every time I'm going to update my beta by using whatever the slope is, the derivative at that point. At that point. And please remember that this graph is just a graph that comes from the creation of my cost function. Now, just to show you here, the reason why we don't want to take big steps, because you would think, well, then we can very quickly go there. What happens is we overshoot, and we go from this point to that point, and then back to this point, and back to that point, and back to that point, and you keep on overshooting, and you can't do that, because then you're never going to settle on this lowest point. We also don't want this to be too small, otherwise we're going to take so many steps, and we won't move for very long, and that takes computationally, that takes a long time, so it takes a long time for our computer program to get towards that point, and we might never even get there. So that is all very nice, and I hope you really get it. I hope you have an intuitive understanding of what is going on here. It's just this beauty. I mean, if you just think of every step that we've constructed here, it is such a beautiful thing. That we can construct this, and we can go look for that minimum of our cost function, which is really, remember, just an average of all the errors that we make. It is a beautiful system. But please now understand that we use the derivative of every point, which is that slope at that point, to build into this thing. And we keep on updating. We get a new beta by taking the old one where we started, and we subtract from this 0.001, whatever we choose for alpha, times what the slope is. The slope is going to be negative on this side, positive on that side, which means we're always going to we guarantee to walk towards, in the right direction. Now here I'm trying just to do a three-dimensional, very difficult for me to draw. I have not an ounce of artistic ability. Anyway, this is the x-axis, the y-axis, and then the z-axis, and what I'm trying to show here with these dotted lines that I've got this plane, which is parallel here to my x-axis. Because unfortunately, it's not that easy. We don't just have this simple one. Even for a single variable, we can have this shape. For instance, this bowl shaped here in 3 dimensions. So what do we do? Well, now we have a water crisis in Cape Town, so in my office, I only drink from paper cups. Now take a little paper cup like this. I don't want to, because I want another cup of coffee, and I'm trying to spare this. And we use the coffee because we don't want to use water, because we have no water in Cape Town. We have a water crisis. So we have a little bit of water, but we're trying to save. We're all doing our bit. But if I imagine this is my cup, and it won't look like this. Imagine it's round at the bottom. But imagine if I cut through it. Now, this is what I'm doing here. I'm saying there's this three-dimensional object here, and there's this plane cutting through it. And think about that just for a moment. If I have this plane that lies here, obviously on the x-axis, which is here, there's plenty movement on the x-axis, but it cuts that y-axis in one point. I'm keeping y stable. It is not moving at all. And if I were to cut through that, imagine, take a pair of scissors and just cut, try and cut a line through this. There's going to be a very nice little graph there. On that cutting edge, there's going to be a knife. So a knife's edge there. And that is what you do with the partial derivatives, if you looked at the video on partial derivative. So if I take the partial derivative of my cost function here with respect to x, it means I keep y completely separate. And if I keep it constant, and if I take a derivative with respect to that constant, it disappears, it's 0. So it will tell me in what direction I have to come on this axis. And I flip it around, and then I cut through there, keeping the x-axis constant somewhere here, just going through somewhere here, going through a specific spot there. And if I cut through it there again, there'll be another little graph of that line of intersection. And I can check what slope I wanted there. And remember when we talked about vectors, if I wanted to get there, what I could do is first walk in that direction and then walk in that direction. And that's what we're going to do with deep learning. No matter in how many dimensions it is, we keep all the other dimensions constant, and we just look at where we're going to walk in that direction. Then we're going to see what we walk in that direction, and then what direction in multi-dimensional space, multi-million dimensional space. You can all break it down by keeping all the others constant. And think about this analogy of this cup. If I were to cut through it, where that cut line is going to be a nice little graph for me. So no matter how many dimensions I work in, there's always going to be that little bit of a slope. And through this analogy, we can walk in the right direction to eventually get to the bottom where my cost function is going to be at a minimum. I really hope that this helped you. As I said, I'm not aiming this series at someone who's a hardcore mathematician or computer scientist who've studied these things. I want everyone involved. So to help us use deep learning to solve medical problems, healthcare problems, and you don't necessarily have to know this, but I think there's a elegance, there's a beauty in this, and it would be lovely if you did understand it. Leave me some lines in the comment if I can explain it in a different way, because I really want you to grasp these concepts. They are beautifully. Else, I'll speak to you in the next video lecture. In this video, I want to continue our discussion of linear regression to help us cement all the concepts and processes that we're going to need when we look at proper deep neural networks. So I hope you looked at some of the videos just describing the basic linear algebra, the basic video on derivatives, and then the one who looked slightly deeper at gradient descent and have a good understanding of what is going on here. Now remember, these videos, the video series on deep learning is for people interested in healthcare, solving problems with healthcare, so I don't expect of you to have this deep understanding of mathematics or computer science. It is about using it to solve problems, and I want you to be able to use deep neural networks to understand deep learning to solve these problems. So I've got another document here created with R Markdown in R Studio, and it's published on RPubs. Remember that these files are available on RPubs. They're available on GitHub. I'll talk about them on Twitter and on LinkedIn. So follow me on YouTube, subscribe to me at least on YouTube, follow me on Twitter, connect with me on LinkedIn, have a look at these RPubs pages and also GitHub. All the links will be everywhere. I want everyone to have access to this. So let's move down. We're going to use multivariable linear regression. So whereas before all we had was a single feature variable predicting a target variable, we are now going to have 3 feature variables predicting a target variable. And I'm going to import a CSV file that will also be on GitHub in case you want to do that. Now, that was just some random values, so we're going to have very poor prediction of the target value, just 4 columns and just random values, and we can still build a model from that. So I've imported it here in R. Don't worry about it. It's not what this is about. Let's just remind ourselves of where we are. We've now got these three unknowns. I'm going to call them x sub 1, x sub 2, and x sub 3. They're my three feature variables, and there'll be multiple rows of data describing these patients. If they are patients, for instance, we can see their tenure in actual fact, and we have a target variable y. So we need these parameters, beta sub 0, beta sub 1, sub 2, and beta sub 3, so that we can create this. I'm going to take beta sub 0, remember, plus beta sub 1 times x sub 1, beta sub 2, that should say 2, x sub 2, and beta sub 3, x sub 3. And that's going to give me roughly y. Now we say this roughly y because what it actually gives me, remember, is y hat with a little hat on top. And that's going to be different from the actual y. And that's why these squiggly lines means approximately equal to. So that's still going to give me a loss function. You'll see this notation written elsewhere where there's a superscript I, and the superscript I just means every sample. So that first row will be the I1, the second row would be I2, the third row would be I3. It just means the loss function here was going to be this addition of all these things multiplied by each other. So in this first one, it will be beta sub 1 times 20.1, beta sub 2 times 39.3, and beta sub 3 times 1.3. Add to that beta sub 0, and that's going to give me a value y hat for that ith row, that first row, and from that I subtract the actual ground truth value, which in this first instance was going to be 394, and I square that, and that's my loss function. And I can add up and divide by how many there are, so that I eventually get this average over all the lost and call that specifically my cost function. So that'll be a long equation. Remember previously through algebra we just condensed that to a simple one, but it's still going to have beta sub 0, beta sub 1s, beta sub 2, and beta sub 3s in there, and I have to solve for those to give me the lowest possible cost function. Now once again I'm going to cheat a little bit in R, and I'm going to use the LM, linear model function there, and I say y is given by x sub 1 plus x2 plus x3, and the data comes from the data frame. This is how I imported it. I saved it in this computer variable, this object called df. And I can cheat a little bit, and it gives me these values. It says beta sub 0 should be there, 342.7. Beta sub 1 should be there. There's beta sub 2, and there's beta sub 3. And you've seen, see I've written it here. Those are the values that it should take. Note though that if I look at the multiple r squared here, it's only 0.016, very poor model. And as I said, those values were randomly just created, so we expected they'll be poor, so don't worry about that too much. What I want to show you is just this, because that's the idea, the aim of this video lecture. We've got to get used to this little diagram that we've drawn here, because I've taken this multivariable linear regression and I have represented it in this way. If I scroll down, I'm going to decrease the size just a little bit so it all should fit in the same page. There we go. Oh, almost there. Bear with me. Let's go. Let's go. That's better. There we go. Here I have what is called an input layer. X sub 1, X sub 2, and X sub 3. So I'm actually turning this on its side. Whereas if I look at, let's go back up. There's X sub 1, X sub 2, and X sub 3. They lie horizontally for the first patient. There they are. I'm turning that on its side. So X sub 1, that 20.1, and then the 39.3 and the 1.3, they are now this way along. And that's called my input layer. So I can put those three values in there. And you can see they each connected to this layer here. And it's called a hidden layer. A hidden layer of nodes. See the three nodes. And we see I've put a little tooltip there, it's multiply, and there's my beta 1, beta 2, and beta 3. So I'm going, these are called, in deep neural networks, these are called weights. So I'm going to take each input value and multiply it by its weight. Each input value multiplied by its weight, this input value multiplied by its weight, and that gives me the values in this, in the three nodes of the hidden layer. And they each only have a single connection with the input layer. Later on we're going to see it gets much more hectic than this. So I have this beta sub 1, x sub 1, beta sub 2, x sub 2, beta sub 3, x sub 3 in this layer here. And then I add all of these, 3. Remember it was this one plus this one plus this one, and I add beta 0, and that gives me this y hat. And there we have sort of a neural network. We have an input layer, we have a hidden layer here, and we have an output layer. And that is exactly how we construct deep neural networks. We're going to have many more hidden layers, one layer after another. We're going to call each of these a node, but we can also see them as a little neuron, a brain cell that's connected to all sorts of other brain cells. But we're just going to add on adding these layers, and that's a deep neural network. Here we just have this single hidden layer. Now, so much so that if I plug in that first patient did was 20.1, 39.3, 1.3, I multiplied by the weights that we stole from our linear model. It gives me these interim values in my hidden layer. And I've got my bias node there. I add all of these and that one, and I get 241.7, which is my predicted, but the actual one was 394.5. So quite a bit of difference, but I told you through that adjusted R squared, this is going to be a bad model. But anyway, I think this should give you a full, a meaningful, deep understanding of what a network, a neural network is all about. We're going to have this layer of our input values, one for each row in our data. We put them there. We're going to have these hidden layers, and we calculate their values by multiplying the input times this weight. And we'll see later on we can add a bias right here and add a bias even into this. Don't worry about that for now. We have these layers, and then they pass to some output layer. And that output layer can calculate a value for us, or a state even, depending on what our problem is. That is the basic structure of a neural network. And you know now that this was forward propagation. We call this forward propagation to get to this. And now through gradient descent, we're going to go backwards in the opposite direction, doing back propagation, whereby we update these values of our weights. We update them to better values, as you saw in the previous video, and I hope you watched the previous video in this playlist. Whereby we update those, now we have new values for beta sub 0, beta sub 1, 2, and 3. And we can go forward again, get a new value, update that, back and forth, back and forth. Initially, these three values that we have here, when we do proper create a proper deep neural network, we're just going to take stabs in the dark at these. We'll just ask the computer to generate random numbers, so that we start somewhere on our gradient descent graph. We have some point where we can stand, and we start to look at how we can go downhill so our cost function can be as low as possible. And it will run backwards and forwards, forward propagation, back propagation, forward propagation, back propagation, updating those weights every time through this process of gradient descent until we get them as good as possible so that the cost function is at its minimum. The slope is going to get to 0. That's how we know. It's going to approach 0 at least. And that's where we know we've got the best value for these weights. So I really hope this has been a good introduction for you, that you have this a deep understanding of what neural networks are all about. And we used a very simple thing like linear regression to do all of this for us. If you come across this video and it's the first one you find, please go back. I always create my playlist so one follows the other. When you look at our pubs, there'll be a series of these notebooks, these markdown files. So please do them in order so that you know which one follows the next. I'm a surgeon. That means I'm a clinician, but I'm very interested in deep learning, and I want everyone to be interested in it because it is going to be used to solve so many problems, as it already has for us as human beings. Get everyone involved in deep learning. I maintain my argument that it's time for clinicians and those involved in healthcare to learn about deep learning, and we should not just leave it to our colleagues in mathematics and computer science to do this. We should get on board as well. I'll speak to you again. My name is Juan Klopper, and I'm a surgeon really on a mission to introduce healthcare professionals and everyone interested really in solving healthcare problems to the world of deep neural networks. Now, if this is the first video that you see, please go back and start the series from the beginning, else this doesn't really make sense. There's a playlist on YouTube, one video follows the rest. So in case this is the first one that you see, please start at the beginning. It will really mean a lot more to you. Of course, if you've been following along, let's continue our very exciting journey as we move towards Well, this is actually our last step, I would think, before we really get into deep neural networks. Now, up till now, we've really only looked at a target variable that is of a continuous numerical type. So we're just trying to predict a single value. In many cases, though, we want to predict something that is a categorical variable, something such as the patient has a disease, doesn't have a disease. In the financial world, we might say this is a fraudulent transaction or it's not a fraudulent transaction. We might have a CT scan with nodules in the chest, and it might, we might have to classify that CT scan as, or that nodule on the CT scan as malignant or benign. These are categorical outcomes. The examples that I've mentioned have a sample space of only 2, so those are binary or dichotomous problems, but we can really model something with 1,000 elements in the sample space of our target value. Now, this just introduces a slight complexity to the problem, but believe me, it is easily solved and you actually already know how to solve it. So again, this is a document that's available on RPub, so you can download it. I'll put it on GitHub as well, so you can look at these R files. Again, if you just stumble across this, don't worry about the code. As we start developing these, as we move into real proper deep neural networks, you'll pick up how to code in this environment called the R programming language very, very quickly. I use the R programming language specifically because it is so easy to teach, which is what I do face-to-face as well. Statistical learning, machine learning, biostatistics, just using R and RStudio. And although the main language for deep neural networks is Python, once you understand things in R, it's very easy to pick up Python and continue your work there. So no problem at all. Don't worry about the coding though. You will definitely pick it up as we go. So this is the document on RPub. So you can read that. If you don't want to listen to this video and watch this video, you can just read the document. So what we have here at the top, you see a categorical target variable, and we're going to express this as 0, 1, 0, 1, and 2, depending on how many elements there are in the sample space of our target variable. So if we have a binary outcome like yes or no, we're just going to use 0 and 1, and depending how you set up the problem, you can decide which is going to be 0 and which is going to be 1. Now, an easy way to solve this problem is just what we call the sigmoid function that you can see here. There we have it. It says take any input, plug it in there. So if I plug the value -3 in there, it will be 1 over 1 plus e, which is Euler's number, to the power minus -3, and that will give you a value. Let me show you some code of what the sigmoid function actually looks like. There we go. No matter what input we give to the sigmoid function, you see as I hover over here, you see -3.76, -3.6, all the way up. Doesn't matter where I go, look at the values. They are always going to be between 0 and 1. They are constrained between 0 and 1. And following what we are trying to achieve, still trying to get these values for our parameters beta sub 0, beta sub 1, that really hasn't changed. We're still after that. So this little z, we can still see that as a problem that we set up. Here I've got a problem with 4 feature variables, x1 to x4, and I still have my beta 0 plus beta 1, beta 2, beta 3, beta 4, and I can just call that my z and plug that into the z here. So in the end we have equation 3 here, which says sigmoid of z is 1 over 1 plus e to the power negative, that very familiar thing that we've watched in all the videos up till now. That should be very familiar with you, very familiar for you. Now, here's the network that we also saw in a previous video. I have values plugged in here for my feature variables x1, x2, x3, x4. I plug those values in. I multiply them by these parameters, which we call weights, beta 1, beta 2, beta 3, beta 4, so that I get values in my hidden layer here. This is a hidden layer of nodes or neurons, and they are just a multiplication of the weight and my input variable. Say, for instance, the values in row 1 of a spreadsheet. And I add all of that together, and I also add the bias node, and now I get z. And there is z just plugged in there, and I plug it into the sigma function right there, and now it gives me y hat, the predicted value, which, remember, if my output, my target variable only has 0 and 1s in it, 0 and 1, 0, 1, 0, 1, 0, 1 for all the rows, I'm going to get a value here for my predicted, which is going to be constrained between 0 and 1. Sure, it's going to have some decimal values, but it is constrained between 0 and 1 exactly where I want it, because now I have a target variable that is really within range of this 0 and 1 of my ground truth target value. So let's look at an example. I'm going to import this logistic regression CSV spreadsheet file, and here we have it nicely expressed on the screen. We see x sub 1, x sub 2, x sub 3, and x sub 4. Those are my 4 feature variables, and you see the target variables. So for the first patient here, we have 15.5, 110, 2.5, 52.6. You can imagine these are variables for some blood results or, whatever the case might be. And the outcome, the target variable, is a 1. And there's another one, a 1, a 1, a 1. There's 0, 0. And you can go through, click on all of these, run through this whole data set of 150 entries. Now, fortunately for us in R, there is the GLM function, generalized linear models. I can plug in all my values y being predicted by that dot means. It's just a shorthand for x sub 1, x sub 2, x sub 3, and x sub 4. It uses a logistic regression model here with a binary outcome. And if we look down here at the estimate column, we see there are our beta values. There's beta sub 0, negative 13.8, beta sub 1, beta sub 2, beta sub 3, beta sub 4. So if I plug in this first patient's values, 15.5, 110, 2.5, if I plug that in to my function 1 over 1 plus e to the power that, I get a solution of 0.619. Now we can create a simple cutoff. Remember, that's my y hat now, my predicted value for the target variable. Now this patient was a 1.0, and what we can very simply do is say, let's have a cutoff here. Let's go back to the graph. Let's have a cutoff of right there. And we say that everything above, so you see it's 0.5 there on the y-axis. Anything above that 0.5 we'll see as a 1, as it is going to 1 anyway. And so 0.5 and up we'll see as a 1, and less than 0.5 we'll see as a 0. And we can code for that, and we'll do that in when we create the neural networks. So 0.619, that's above 0.05, so the prediction here will be for 1. Lo and behold, that first patient did have a target value of 1, so the error made in this first step when we set up our loss function and our cost function as we did before, so that we can do a back propagation to update these beta values. In this instance, it's going to be spot on. Now, this, as we created it here, is not a neural network. We've just used plain, simple old logistic regression, but as you can see, it is absolutely correct. It predicted a 1, and it really is a 1. So there we have it. I think that was the last piece of the puzzle that we required just before we move on to proper neural networks. Once again, I plead with you to tell people about this video series, about these publications on RPub. I'll put some stuff out on LinkedIn as well, so follow me on Twitter, connect with me on LinkedIn, look at these RPubs. These files are available on GitHub. Subscribe on YouTube if you really are interested in developing your knowledge around deep neural networks so that you can learn to solve problems in your domain. Let everyone know about these videos. Let's start a community where, at least from one point of view, medical professionals get involved, and we don't just leave these problems to computer scientists. We have the domain knowledge, and it is really our duty to get involved with this. Just as an aside, just excuse, of course, all the noise. I've spoken about it before. There's a neuroscience center being built right outside my window here in my office. And it's early in the morning, even before working hours. I come in early, but the noise is already going as they hammer away. Nothing I can do about that. I hope you enjoyed this video, and in the next one, I hope that we get started on proper deep neural networks. So the time has eventually come for us to have a look at a proper neural network. Now, it's going to be a very basic neural network, but we are eventually there. I'm still going to use a document here that I've uploaded to RPubs. I'll leave the link down below. You can also download this RStudio file right from GitHub. Now remember, if this is the first time you come across these videos, please start at the beginning, otherwise things are not going to make much sense. And also remember that I'm really after people who are interested in deep learning, who are not necessarily computer scientists or mathematicians, but really want to get involved with deep learning. In my specific case, really getting healthcare professionals involved in deep learning. We won't go into the code, that will come with time, so let's just get going. I'm going to build on everything that has gone before. And we're really going to construct this network, and it's going to look very familiar if you remember what we discussed when we looked at linear regression and logistic regression. The whole idea behind a deep neural network is just this very loosely based on this idea of a brain cell, a neuron. And we can see one depicted here. We can see that this image comes from Wiki Commons and Wikimedia Commons, and you can just click on the link there and it'll take you to these wonderful images. The whole idea is that there are many connections. So this brain cell with its nucleus here and cell body has all these connections that bring impulses from many other brain cells in, and it gets that impulse goes all the way along and it gets transmitted here along the axon and then to all these connections to other neurons in a network. So many connections to many other connections, and that is what it is all about. Here we go, and I'm just going to make the screen size here a bit smaller so everything can fit on. Let's go, there we go, now everything fits on. Now you'll still see the input layer on this side. You'll still recognize this hidden layer here. You might still notice this node here. But things look a bit different, and the most noticeable difference from what has come before are these many connections. No longer is this one input connected to one other node in a single layer as we did with the logistic regression. Look at this. Number one, there's 3 feature variables here, but there are 4 nodes here. Now that's completely arbitrary. If you design a neural network, you decide how many nodes go here. And that number is something we refer to as a hyperparameter. There are many hyperparameters in the design of a neural network, and if you design that neural network, all those hyperparameter values are up to you. There are 4 nodes here in the hidden layer. In other words, that's a hyperparameter, that's your decision. And different values will work differently under different circumstances. But look at this first one. It receives input from all 3 of the input nodes, not just a single one. And it also gets input from this node up here, which is called a bias node. So I can create a bias value, and that can also be added in to these nodes. Now here we have 3 feature variables. So for the first patient, for instance, or whatever the case might be in the subject, the first row or one of the rows in your data set, the value for the first variable, the variable for the second variable, the value for the third variable. Each of these are going to be multiplied by some weight. And remember, now we're going to move away from calling those beta sub 1, beta sub 2 the parameters. We call them weights now. But each line here represents a value, a weight. So this x sub 1 value is going to be multiplied by this weight and then inputted to that node. This node number 2, this feature variable number 2 is going to be multiplied, that value is going to be multiplied by some weight value, this line here, and as an input, and the same here. And each one of them will be connected to each of these nodes. So if there are 3 on this side, each with 4 connections, that means there already be 12 values here, 12 weights that we need to optimize. Before, when we only had the single beta sub 0 and beta sub 1 for a single variable, that was all that we needed to learn. Just from this tiny little connection, there's already 12 parameters that need to be learned, 12 weight values that we have to optimize for in our loss function and in our cost function. And then we can even add this bias node to all of these values as well. So these multiplications, and they all get added, you can also add this value in there. What you are going to get is a value after all these multiplications and additions, is this value called Z1. And then, not only that, that's not where we stop. We're also going to apply some function to it. In logistic regression, we looked at the logistic sigmoid function, but there are many other functions, and they are called activation functions, and hence this idea of a neuron. You can see now all the dendrites, all the connections coming in, all the connections going out, and there's some decision as to what flows through here. Does an impulse go or does an impulse not go? That's our activation function. Now let's represent things slightly more mathematically. There is a short video just on linear algebra. Remember, I do have a course of almost 100 videos on linear algebra. I link to that as well. But in case you've missed all of that, this might not make much sense to you, watch that single video. It's not that difficult though. If we have a look at it, there is my 3 input values from my 3 feature variables, and I'm going to call this a column vector with 3 rows and a single column, so it's 3 by 1. And I put this little underscore here, this line under, that represents a vector, rank 1 tensor. And the solution I want is this Z1, Z2, Z3, Z4, Z1, Z sub 2, Z sub 3, Z sub 4, depending on where you live. And so my output here is a 4 by 1 column vector. 1, 2, 3, 4 rows times 1 column. My weights is now not just beta sub 0, beta sub 1, and maybe beta sub 2. It's a whole matrix, a rank 2 tensor of values. And if you look at this W sub 1, 1, W sub 1, 2, if we look at node 1, it has 1, 2, 3, 4 values coming out of it. And there we have 1, 2, let's just look at the first row there. 1, 2, 3, 4 values coming out of it. Now, if we do this tensor multiplication, we have a matrix on the side and a vector on the side. So we have to actually transpose it. At the moment, it is 1, 2, 3. It's a 3 by 4. I cannot have an inner product, a dot product of a 3 times 4 matrix with a 3 times 1 vector. I've got to transpose that so that rows become columns and columns become rows. So that changes it from a 3 by 4 to a 4 by 3. Now these inner 2 values are both 3. I can do this inner product, and the result will be these 2 values on the outside, a 4 by 1 matrix, exactly, or column vector at least, exactly what I wanted, 4 by 1, 4 by 1. There we see it. And I can, if I wanted to, even add this bias node, and it'll also have to be, if I add that, it also has to be a 4 by 1 column vector. And if you look at up here, of course, 1, 2, 3, 4, it's got to have these 4 connections. So 4 by 1, and that leaves me with a 4 by 1 column vector. Now I need to apply to each of these values Z1 through Z4. I've got to apply an activation function. Here we call it G. Now there are many. You've seen the logistic sigmoid function. One of the most common activation functions though is the ReLU function, rectified linear unit. You see it's written R and then lowercase e and then uppercase LU. And this is what it looks like. No matter what value I input, if that value is 0 or less, it just outputs a 0. So whatever this value that I calculate here, all these z's that I calculate through this whole equation 5, if that was a -1, the activation function spits out 0. If z2 was -1,000,000, it's never going to be that, but just imagine, it's going to output a 0. So it'll already be 0, 0. If it's more than 0, it just takes on that exact value. This line goes up at 45 degrees. So you can see an input of 0.62 is an output of 0.62. Input of 1.26 is an output of 1.26. This is called a rectified linear unit. And what we do is, each of these values, Z1, Z2, Z3, we pass through this. Very easy, the output then is this. And then right at the end, we'll combine this in some way so that there's an output. And that output can just be as is in a regression problem. It can go through an activation function itself if we have a binary classification, which is all we can do if there's a single node. But you'll see later there can even be more than one node here as an output. And then we'll use a different kind of activation for these last values, something like a softmax function, and we'll get into that a little later. And that's it. there is a single hidden layer neural network. And you can see the differences from this to a logistic regression network that we built before. Many more connections. And now you can see that there's richness built into this, because imagine I had more nodes, more feature variables, more nodes, and then more of these layers. We'll get so many of these parameters, and they all are going to, in the end, remember we're going to get a value here, a y-hat value, which is quite different from, might be quite different from the actual y, the ground truth y, and we're going to see, sum up in some way or average in some way, all these errors. That gives us a big cost function, which is now a function here already. And let's see, just here, there's 12 and 4, there's already 16 connections here. And, there's even more here depending on what happens with deeper layers. You can see how many parameters, unknowns, there are in this massive equation, and we're now really talking about multi-dimensional space, and we have to use backpropagation, gradient descent, and then we'll optimize all of these values, and we'll go through again. Hopefully our cost function will show that the error is now less. We do gradient descent through differentiation, partial differentiation of all of these, how many ever there are, weights there are. We now get better values, and we go forward again and backwards and forwards until our error is as small as possible, and these values all take on an optimum value. As I said, there's really a richness built into this. This algorithm can learn a lot more than a simple logistic regression model. It can really try and mimic at least a simple connection inside of your brain in some way. I look forward to speaking to you again. In this video, I want to introduce you to the R programming language. So eventually we're going to start looking at the language itself. Now there's no ways that in a short video I can really introduce you to the whole of the programming language, but I'm going to show you the essentials, specifically those things targeted towards what we ultimately are aiming for, and that's to write code that will do some deep learning for us. So once again, this document is available on RPubs. I'm going to put it out on GitHub as well. You can download this and install it. A couple of things that we are going to go through. You can see here that there is an interesting history to R, and you can read some of that right there on Wikipedia. You've also got to download and install R. And if we move down here, you'll note that there, and I'll put these links down below, there is a link here to how to download R for your specific programming environment, for your operating system. So that would be for Windows, for Mac OS, and for Linux. You can find all the downloads and install instructions there. It is simply downloading a file and running that file, and it'll install. Now there's a beautiful program called R Studio, and you see the link there. You must also download and install that. That creates an environment, a program in which we're going to write the code, and it's an absolutely phenomenal coding environment. And whether you are new to R or whether you are an expert, it just makes the writing of code such a pleasure. And it allows for the creation of much richer objects than just code. You can write a book, you can write documents, dissertations, you can create websites, you can create applications. There's just no end to its capability. So I really want you to install R Studio as well. It's simply following those two links. As I said, I'll link to that in the description to the video down below, and also where to download all these files. Both viewing them on RPubs, this document, which was created in R Studio, by the way, as all of these documents are, and to the files themselves on GitHub. So without further ado, let's get into a bit of the language, well, at least first the R Studio coding environment, as all the knocking and banging outside my office where the construction of the new neuroscience unit has been done. It really is an earful, so apologies for that. Let's get started. Once you've installed R and then R Studio, you can open R Studio, and this is what it looks like. Now I've installed R version 3.5.1, the newest version as of the time of this recording. You see its code name there is Feather Spray. and installed it for 64-bit Windows system, and here we have it. It should be rather familiar to anyone who's opened a spreadsheet file before, or a file or a word processing file such as Microsoft Word, etc. And we have this menu system up above. There's the normal file, and you can do new file and save as. You can edit a few things that you might not see in usual programs: plots, sessions, build, debug, profile, tools. Tools is quite important because you can go down here to global options and you can set quite a few options. For instance, here in appearance, you have some themes. The default here is Crimson Editor, Dawn, Dracula, Dreamweaver. You can really set your coding environment to look the way that you want, and I've increased the font size here to 16 so it's easier for us to have a look at in this recording. Now there are basically 4 panels. You can only see 3 at the moment, but there are 4, 1, 2, 3 here. The 4th one is as we create a new file. So this panel here is actually the bottom left panel. It has a console, and a console is very simple. You can just type lines of code here, 2 + 2, and I'm going to hit enter, and we see the solution there, 4. And there's a new line indicated there. The 1 here indicates that there's only 1 element in the solution. If there were more, they'd each have an address starting at 1, the first element, the second, the third. That's what that 1 refers to. When it runs over multiple lines, my answer, the first element in a new line, it'll have its number here in square brackets. As simple as that. We also have a terminal here, which is very similar to a terminal that you might find in Mac OS or in Linux. What you might find in Windows as well. In Windows, we call it the command prompt, of course. So that's very similar, and you can interact with your computer if you know how to use that kind of code. Let's go back to the console. On the upper right, there's 3 tabs usually. The environment, and we'll see what happens as we start writing code. The history of code that has gone before, and connections we're not really going to deal with in this video series. On the bottom right, we have the files, which just shows the files in your current structure, and you can also navigate as you would in your normal explorer of your folder structure, your file structure on your computer. Plots, if we've created any plots, very nicely you can export these plots as PNGs, as PDFs. Packages is very important. As you read some of the history of R on Wikipedia, you might notice that there is this base or core R that can do a lot of statistical functions, but there are countless other libraries or packages that you can import that others have written. It's all open source. You can just install them. Click on it and install it, or hit install and then type the name of the package. It'll ask you what the default library is, and that is we are in 3.5. Some packages make use of other packages. Those are called dependencies, so just have that clicked as well. So those are also installed. So click the name of something for instance like Plotly, which is a plotting library. We see it comes up there, and you can simply install it now. It's available. It's extended the functionality of R, and there are so many of these. There's a fantastic help system. You can just type in the name of a function, and we're going to talk about what functions are. For instance, if you want to calculate the average or mean, the keyword function is mean. I can type in a mean, and we can search for that. Let's search, type it in the correct bar, in the correct space, of course, mean, there we go. Let's search for mean, there we go, that looks better. The arithmetic mean, how to use it, tells you what arguments are, and we'll go through, what these things are very shortly. But a fantastic help system. Just type in what you're looking for, and you'll get some help on that. The RStudio website is also a fantastic resource just to look for help. Viewer is something I'll show you if we create documents or dissertations or books or whatever. The viewer can display that for us. So let's just jump into creating a new file, and there we'll simply see this little down arrow there for new. We could also go file, new file, and we see our script, our markdown, and our notebook, our markdown. Shiny is a web applications. You can code in other languages, create text files, presentations, documents, HTML files. So much you can do. Now we're going to create a new script. All the documents that you see on RPub for the series though are created in Markdown, and we'll have a quick look at Markdown as well. But let's just create an R script, and that's going to open up this top left panel here, which was hidden. As you can see, there's the console and terminal now on the left, on the bottom left. So here we just write lines of code. So let's start with something very simple, and that's just a comment. And the comments are preceded by a hashtag, and I'm just going to say this is a comment. And if you want to leave comments for yourself as you write code, just leave comments. Anything in that line after this hashtag is just totally ignored. Now we see a number 1 there, that's our first line of code, and to execute that line of code, as long as I'm anywhere in this line, I can just hit the run, and that will execute that line of code. Now it's totally ignored by R because it is preceded by this hashtag. So I can just hit enter and move down a little bit, create myself some space. So let's leave ourselves a comment that we're going to write some simple arithmetic, if I can spell that, arithmetic in this section. So there we go, simple arithmetic, and let's do the 2 plus 2 again. I like to use spaces, you don't have to use spaces. So I've got 2 plus 2 there, I'm going to click run, and there we have exact same thing down in the console here. We see the 4, and there's only one element there, so we see the 4. So you can try anything else. Let's try some trigonometric function. Let's ask for the sine of pi, the sine function, and we want pi over 2. So that's 90 degrees, pi being 180 degrees, pi radians. And I executed it this time by just holding down the control or command key if you're in a Mac, control for PC and Windows, and hitting the enter key. And instead of being in that line and running, I can do the same thing holding down control or command and enter. And we see the pi of 90 degrees, or the sine of the pi over 2 or 90 degrees is just 1. So there's so many let's do 2 minus 2. I'm holding down control, hitting enter, and I see that is 0. So really try some of these. And in the help section here, if we go there, let's just see what the cosine function would do. And it tells me there, shows me the other trigonometric functions there, and you just do that. Now a function is, after a function you see these parentheses, and then you pass something to the function. And this something that is called an argument. You always pass an argument when you call a function. Calling a function means writing it, and then hitting control enter or return, control enter or command return on a Mac, and then you get this solution. That's when you call a function, but you have to pass, to most functions at least, you pass an argument. And then in the details here it'll tell you, it says there the arguments, you can pass 2 arguments, numeric or complex vectors, and we'll get to what vectors are in a little bit. So there are so many of these inbuilt functions in trigonometric, transcendental, so many built-in functions for arithmetic, and I really want you to play around with those. The next thing I want to just talk to you about is an object. Also we can also refer to this as a computer variable or computer variable name. So I've written something there, 2 plus 2, but I might want to store that value for later use so that I don't have to write that in all the time. Let's create a computer variable, and you can use any word. Try to use words that are descriptive, so when you refer back to this later in your code, that you know what is stored inside of that object. Now an object really is just the space that is created in your computer's memory, in which that object is stored, and that object has a type depending on what kind of data it holds. So let's create this computer variable, and I'm just going to call it something like my text. As I said, there's some restrictions on this, so don't use words that are already built into, don't use sign, for instance, the SIN as a computer variable or object name that already exists, so don't overwrite that, and don't use illegal characters such as spaces. Now there are some conventions that some people stick to. This is camel case. In other words, there are 2 words there, my and text. There's no space between them. The first letter is lowercase, but each subsequent word starts with an uppercase. So that's one way of going about it. Some people use snake case. That will look something like this, where the words are strung together with underscores. Another popular way is just to put dots in between. So my dot text. So let's do that. And now instead of using an equal sign, which you can, but let's just use the convention, which is this symbol. I'm going to hold down Alt on a Windows or PC or Linux, hold down the Alt and hit the minus sign. And you see this less than and minus sign come up. That is equal to an equal sign. Let's put it that. It's an assignment operator. I'm assigning something to this object called my text. And since I've called it my text, let's pass some text. Text is always passed inside of quotation marks. And I'm going to say this is text. I'm going to hold down Control and hit Enter or Command and Return. And I now have my text. Look what happened on the right hand side here. Under the Elements tab, under Values, there is a new variable called my.text and what is held inside of that. So you get this list of all the things that you've created and what the value is that's held inside of this object. And just remember, everything has a type. So the type of the content in this object is a string. A string because it's inside of quotation marks. Let's create another one. I'm going to call this one my answer. So I'm using camel case in this instance, holding down Alt and minus or Option and minus. And I'm going to store in that my answer is the solution to 2 plus 2. Control Enter, Command Return, and we see my answer is now there and it's 4. And later on in my program, I can just use my answer. And as I type it, a tip even comes up and it says, well, MYA, there's something that already exists, so I can just hit Tab and it'll auto-complete for me. If I now hit Control and Enter, Command and Return, we see the solution pop up here in the bottom. The my answer, it holds the value 4 and the 4 is printed there. So that 4 is always stored inside of my answer and I can reuse that all the time. That makes it very, very useful. So let's move on to something called a list. So let's do this. Let's do that. There we go. Let's do lists. And a list is just something that is more than a single element, although in R, even a single value like 4 is actually also a list. And R refers to these as vectors. Everything is stored inside a vector, which is just a list of elements. And a single value, of course, is also a list, a vector. And if it's a list of integers, it's a numerical vector. And if it's a list of text, it's a text vector. And that's just the term that is used. So let's create one. And I'm going to call this one temperature. Temperature, I'm going to hold down Alt and minus, Option and minus to have this assignment operator. And the way that we put lots of elements together is to group them inside of a vector. We separate them by commas, but we use a function called C. I suppose for we're concatenating something, we're putting something together, C. So let's have some temperatures here. Let's have a temperature of 72 and 69 and another 72 and a 70, 70. And there's 4 numbers. Let's make it a more balmy 85. I'm going to hold down Control and Enter or Command and Return. And now we see temperatures saved up there. Now look at it. It says it's a numerical vector and it has 5 elements. So these are the addresses 1. The colon means through, 1 through 5. So there's number 1, there's number 2, there's number 3, there's number 4, there's number 5. So that is a list. I just want to show you another quick way to do this. Let's create another one. I'm going to call this one my list using camel case. And I'm going to assign that a sequence. I can create a sequence of value with a SEQ. And you see SEQ comes up there. There's actually a little tooltip there. And it says if you hit the F1 key, let's do that. The help actually opens up and it gives you the sequence there and how to use the usage, the arguments that can be passed, some more details. So all the help for sequence. Now, the simple way to use sequence is to state a start number. So I'm going to say start at 1. Stop at 10 and go up in steps of 1. Let's execute that and we see what we have here is a my list. It's numbers. There are 10 places and it is the numbers 1 through 10. I started at 1, I ended at 10 and I went up in steps of 1. So to create sequences can be quite helpful. If you want to know how many elements there are in that, just simply use the length function. So I'm going to say what is the length of my list? And very quickly it's going to tell me it has 10 elements in there. It just counts how many there are. So that's quite useful. The next thing I want to talk to you about is just some for loops. Let's do that. Let's do for loops. Now that is how you iterate through something. I'm going to iterate through a piece of code over and over again, but I'm going to control how this iteration works. So let's create a variable. I'm going to call it my numbers. Computer variable and object, assignment operator. I'm going to use a sequence, and the sequence starts at 1, ends at 10, and let's go up in steps of 1. Let's do that. So I have my numbers now, very similar of course to the my list that we just created above, but I'm going to do that. Let's create something that holds a 0, and I'm going to call that sum.total. And in sum.total, I'm going to store the value 0. Hold down Control, hit Enter, or Command and return on a Mac. And now we have this sum total. Now I'm going to create this for loop, and the keyword is for, and I type in for, and then I'm going to put in parentheses what I want to happen. I'm going to use a placeholder. You can use any placeholder. Many people use I. Let's use I now. So for I in my dot numbers. And you see the little tooltip coming up. I'm just going to hit tab for auto completion. So what does this say? It's actually, it's actually very close to just normal English. It's saying for I in my numbers. And you can see my numbers is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can well imagine for I in my numbers means, well, first take the 1, then the next one which is a 2, then the next one which is a 3. Just go through each of the elements that are held in the numerical vector called my numbers. We're just going to iterate through that. And then after that, what I want to happen during each of these loops must go inside of curly braces. So I put my curly braces there, and whatever has to happen happens inside of these curly braces. Now it's useful just to hit enter or return here, and you see there's this automatic spacing that happens that last, when I was between those two braces, the last one went to the bottom, and there's this bit of padding there. It just looks nice on the screen, and that's something that RStudio is doing for you right here. So what do we want to do? Well, what we want to do is take sum total. So I'm going to take sum total. Remember at the moment that is 0. And now I'm going to use the equal sign. And it's going to look weird the first time that you see this. I'm going to say sum.total, again, plus I. Now that doesn't look like very good mathematical algebra there. And certainly most computer languages don't work like algebra. What it does when it sees an equal sign or an assignment operator, and as I say, normally we use this assignment operator, but inside of these loops we'll use equal. It says whatever's on the right hand side, execute that first and then place it inside of what is on the left. So what is in sum total at the moment? At the moment, sum total is an object and it holds a value 0. And I is at the moment is the first element in my numbers, which is 1. So it's 0 plus 1, and that is 1. And this 1 now gets passed to sum total, and it gets that piece of memory, that memory in your computer gets overwritten where it had the 0 in it before. Now it holds the value 1. So it's going to go through the second time. Now remember, I moves to the next element, which is 2. Sum total still has the value 1 in it. I is now 2. 1 plus 2 is 3. 3 is now passed to sum total, which now holds the value 3. And we go through each of these. So let's run that. And let's call sum total. Sum.total. And see if I take the numbers 1 through 10 and I add all of them together, what am I going to get? Well, I get 55. We can see the 55 here at the bottom. And we can see sum total has been updated here on the top to 55. So that is very convenient just to run through some code, just doing something over and over again, and then extracting some useful information from that. Let's move on to functions. And we're going to use what we've just done now inside of functions. Now we've seen a little bit of functions before. We've seen what the sine function looks like, and we know that it's built into R, and we have parentheses around that when we pass an argument to that. Say for instance I just want to calculate the average of the values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a built-in function called mean, and I'm just going to pass my dot numbers as an argument to the mean function, and we see at the bottom it's 5.5. So the mean of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is 5.5. Now this one's going to be a bit difficult. I want you just to concentrate now, and I want to show you something very beautiful actually, in that we can create our very own functions. So I'm going to call my function my.mean, just to be different from the inbuilt mean function. So I'm going to give it my.mean. It's an object, I give it a name. But I want to tell R that this is not a normal object, that this is actually a function. So I'm going to use my assignment operator, and I'm going to use the function keyword just to tell R that my mean is not a normal object, it's actually a function. And remember, a function has arguments passed to it. Doesn't always have to be. There are some functions that don't have arguments. You still use the parentheses though. But I'm going to put just a placeholder in there, and I'm going to call it vals, so I can refer to vals, some value that I'm going to pass to my function. So the argument has the placeholder name vals. So in mean we passed, remember, sum total as an argument. The same here with vals, but it's just a placeholder. So I've got this function, and again what happens to it must go inside of curly braces. So in between my two curly braces, the second one was automatically put there when I opened the first one. I hit return or enter so that it makes a new line, and it all looks very nice and neat. So what I want to do inside of this, I want to recreate the mean function. Remember, the mean adds all the values and divides by how many there are. So I'm going to create a computer variable called number.of.elements. It's a descriptive one. I understand what it means. So I'm going to assign to that, I'm going to assign the length of whatever the argument was that is passed. Remember, length just tells me how many elements there are in what I pass. So that's one. I want to create another one called cumulative.total, and I'm going to initialize it with the value 0. The next thing I want my function to do is go through a for loop. So I'm going to say for I in vals, and that's exactly what we did up before. So it's just going to iterate through everything that I pass to this. Again, what happens goes inside of my curly braces. What I wanted to do is to say cumulative.total equals cumulative.total plus I. So exactly the same as we did with the for loop before. So whatever I pass to my function, my mean, it's just going to iterate through all of them, and it's going to sum all of them up. The first one plus the second one plus the third one, exactly as before. So now I want to go outside of my set of curly braces for my for loop, because that's all I want my for loop to do. Now I'm back in the curly braces of my function. And what I wanted to do is to return something. So return is a keyword, and whatever is inside of these parentheses, it returns. And what I want to return to it is the sum total divided by how many there are. So it's cumulative.total divided by number of elements. Number of elements. That's what I wanted to return. And I'm going to just go outside of that curly braces, hit enter, control and enter, command and return, and I now have a new function, and we see it appear there, my.mean, and that is a function. Let's test it out. So I'm going to say my.mean, I'm going to call that, and I'm going to pass that my numbers to it. The my.numbers that we created, the 1 through 10, remember, I'm going to pass that, and I see my solution again is 5.5, just as the inbuilt mean function was. So pause a bit, look through this function again. It really is plain English. It tells you what it's trying to achieve, and it's very expressive. Now these things that I create inside of the function, they are these local variables, and something that I create outside of a function, those are global variables. I'm not going to go into that, but you can read up. That exists for many computer languages. But it should be quite simple to figure out what is happening here. I've created a function called my.mean. It takes an argument which I can pass to it, and in this instance I pass my numbers to it. What I want to do is to have two things: sum up all those values that is passed as this argument. I want to know how many there are so that I can return this total divided by how many there are, which is the equation for arithmetic mean. And to do that, I went through this. Well, there is an inbuilt function, of course, in R that can do this for you, but I used this for loop inside just to go through each of these and just add them. So you can create your very own functions. The next thing I want to show you is just how to load a data set. Now, how to do that, I'm going to actually open the source document that I created for our pubs, and that is on GitHub. So this looks very different. This, you see it's a tab there. This is the script file we've created, and we can save that. On this side, we have an R markdown file. So when I said file new, this was not a script, but a markdown file. And a markdown file is like HTML that you would know in a website. So you still see the lines of code here on the left-hand side. It starts off with something. Now this will be created automatically. This is YAML, Y-A-M-L, just another markup language. A markup language is just well, in some sense you can see it as a subset of the full set of HTML code which is used in websites, the language for websites. So it sets out a title and an author, and then output. I want this to be outputted as an HTML document, a table of content to be set to true, and that's where you see that table of content on my rpubs files, and I don't want the sections numbered. And now what happens is you can write normal paragraphs and create all sorts of nice things, but the R code itself has to go inside of these 3 ticks. So that's on the top left of my keyboard next to the 1 key. There's 1, 2, 3 of them, which indicates we're starting the R code, and 1, 2, 3 ticks, we've ended it. Now this is some automatic setup for this page, don't worry about that. I've also included some style, a cascading style sheet here. Don't worry about any of that. I'm just saying colorize my large headings with this color, my second largest headings with this color, my third largest headings with that color. Just creates a bit of color in my documents. You see the orangey gold and the blue that I always use. This is my PNG file, which is the logo, and this is how I get that to be expressed. 2 hashtags here, those not comments, this is outside of the code. That just says heading number 2, so that gives me a fairly large heading, and that heading is introduction, and then I start writing normal paragraphs, normal English paragraphs. I write all of that. And if I want something to look like code, but it's not really code, I put that inside of these single little tick marks. Write more normal code, and here 2 hashtags, that is markup language, and it says do heading number 2 again, so that's larger, normal text, heading, normal text, heading, etc, etc. I want these to appear as code. They're not executed, just as code, so they go inside of those single ones. You see these 2 dollar signs here. Whatever I put inside of these 2 dollar signs is called LaTeX. And LaTeX is a way to write mathematical expressions. And you see there the Euler's number e to the power 1. You see how that is created. Single little underscores before and after word changes that word into italics. So that will be printed in italics. If I put 2 of those, that will change to bold. So I open and close a word or a sentence or some piece of part of a sentence in these, and that becomes italic. And you can see it goes on. And here I want to execute some text. So those goes inside of 3 of these little ticks. And it actually has something here on the right hand side. I can actually run that content. It's called a chunk. This piece of code is called a chunk. So that will be the code that you write as we wrote here in the script file. That is something that we write here. And it's called a chunk. And I do that with just telling it that we are writing in R, because you can specify other things inside of these set of curly braces. It says R code is about to follow, and we close that R code. And that's how we go about it. So I just want to go down to the section I want to get to. There was the section on the for loops, and you see the code written there. I can execute that code by just hitting that run, that current chunk. And we see the functions bit coming up there. And there we are with loading the data. Now, when I create a file, I can save the file somewhere on my hard drive. Now, this document's already saved. You see the little save icon there is blanked out. It's saved at the moment. If I change anything, that'll light up again so I can save the changes. So I like to save these on my hard drive somewhere. And if I want to import a spreadsheet file that contains some data, if I want to work on some saved data inside of a spreadsheet file, I want to import that file. What I usually do is I save both this file and that spreadsheet file containing the data inside of the same folder on my computer's hard drive or solid state drive, so that they're both in the same. And I can use this get working directory function. If I write that line of code, it'll tell me the address on my hard drive or my solid state drive where this file is saved, but I can also set a working directory. So I'm saying set working directory to the get working directory. So it's going to go out and see where is this current file saved, and then pass that to set working directory, so that this document says when I look for files, I'm going to look inside of this directory or folder where this R document is saved anyway. So that if I want to refer to a file, I can just simply refer to that file. Here we have logisticregression.csv, a comma separated value spreadsheet file. And I don't have to type the whole address to it. So on Windows that would be C:\/ blah blah blah, and of course on Mac that will be different. But I don't have to refer to that because I've set the working directory to the current working directory where this file is saved, and I know I've saved logistic regression in the same folder or directory that this markdown file is saved in. So I don't have to refer to that long address. And to import a spreadsheet file, I use the read.csv. This is a CSV file. So I'm going to call the function read.csv, pass this as an argument inside of quotation marks, and I'm going to pass that to this object that I'm conveniently calling data. So let's set this working directory first by running that line of code. And you saw the little green there as that got executed. And now we're going to import that line of code and run that line of code. So data is now imported. And if I look up here, I see there's new data. So that was values. We had functions before, but now on the top here we have data. And if I click on this little square on this side, it's actually going to open something on a tab here. It's very small to see, but there you can actually see the spreadsheet file. Beautiful. And that's why I say this is such a lovely coding environment, and then I can actually play around with this, filter some of the data. Beautiful environment here. But let's get back to my file. So that's imported in data now. I can also call the view function with an uppercase V that will do exactly the same as clicking on that little square at the top there. Let's just close down this bottom left. And that is how you import data, and that data is now ready to be used, and we're certainly going to use data in this way when we do create our deep learning or our deep neural networks. Now we're going to use TensorFlow in this course. TensorFlow, of course, is Google's open source framework for tensor calculations. Those are the calculations and the framework we need to create and run our deep neural networks. And we're also going to install Keras. Now Keras just sits on top of TensorFlow. It can also sit on top of other frameworks, but we're going to use Google's TensorFlow. And it just makes writing code a lot easier. It's much simpler code. It looks like R. It's very easy to do. So you don't have to do the laborious coding that is sometimes involved with TensorFlow. There are new versions of TensorFlow coming out, which is going to make the writing of code slightly easier. But Keras has become so popular that it's even built into versions 1.9 and up of TensorFlow. So you write a simple line of code, it recreates that in more complex TensorFlow code behind the scenes so that you don't have to write that complex code. But it's the same thing. It's still going to be TensorFlow code. So to install TensorFlow, I want you to install two packages first. One is called Reticulate. So you can come here to Packages, hit Install, type Reticulate and install it. And the second one is called DevTools, DVTOLS. And you're going to do that in exactly the same way. Now, if you're on a Windows machine, you also have to install RTools, as you can see there, RTools. And click on that link, which is in the document. I'll link to it as well. So on Windows, you have to install that RTools for DevTools to work. So install DevTools and Reticulate. On Windows, also install this RTools. The RTools you have to do from the website. With DevTools and Reticulate, you can do that right here. And then we're going to install TensorFlow and Keras. Now to install these, simply follow this link. Once again, in the description below, it is very simple to install then TensorFlow and Keras using DevTools. The description cannot be easier on these websites. Just go to tensorflow.rstudio.com/Keras. It'll show you how to import TensorFlow and Keras. Now for TensorFlow, there are two versions. There's of course the normal CPU version that will run on your computer, no problem. But if you have an NVIDIA graphics processing unit, a gaming card, you can use the GPU version. That is much faster than a CPU. It allows for parallel execution. TensorFlow can use those GPU cores, CUDA cores, so it's got to be an NVIDIA GPU, and it'll run a lot faster. Now if you're in a normal laptop, even if it does have an NVIDIA graphics card, and I'm recording on just such a laptop and it has quite a high-end graphics card in it, it's still not enough. When you get to very large data sets, specifically if you look at images as your data set to do some deep neural networks to learn from images, you are very quickly going to run out of the capacity, and specifically the memory capacity of that GPU, and that's just going to be very frustrating. So for the kind of things we're going to do in this course, and if you're starting off with deep learning, just install the normal CPU version. It's going to run slower, but it's still going to get the job done. If you're adventurous or you have got a monster desktop with two Titan X NVIDIA graphics GPUs in them, go ahead, install the GPU version, no problem. So that was a very short introduction to R. I think that's the basics that you require. It is a lot in one video to get used to. So perhaps pause, go through it again. These files are available, play with them. There is just one way to go about this though. Sit down and start playing. It is fun. It is a lot of fun, and there's a great sense of accomplishment when you get something done. So really, I just want you to do it. We're also going to write lines of code when we create our TensorFlow deep learning models. So you will have to write some lines of code, and as you write those lines of code in the future videos that I will make, you just pick it up along the way. So it really is fantastic and an easy and nice way to do it. This RStudio environment is fantastic. I'm going to stick with R for this introductory series on deep learning because it is such a nice environment. As you can see for yourself now, picking up the language is very easy. And then to write the same models in Python, once you can do it here in R, it's just a breeze. I mean, it is the smallest, tiniest little learning curve. So if you want to move over to Python, which is the natural language for TensorFlow, it's a no-brainer. It's very easy to do. And perhaps I'll make some videos just to show you how this works in Python as well. Stick to R for now. I mean, R is fantastic for normal data analysis, normal statistics. I use the term normal, but just for that workhorse and creating beautiful graphics, graphs, plots that you can put inside of your dissertations, inside of your publications. It's just a phenomenal environment, as is Python. I mean, Python, R, there's this debate, which one should you do? Do both. That's just the solution to the problem. Just learn how to do both. They are very similar. There's some quirks, specifically on the R side, that you've got to get used to. The Python side is actually much, much, much easier. So once again, if you start with R, this makes Python a breeze. And but learn how to use both. That would always be my suggestion. It really is not a stretch. This is not difficult. Really not difficult to learn a computer programming language. So I hope I've got you excited. I hope you feel comfortable that you can start playing in R now. Go and enjoy yourself. So the time has come for us to look at designing a proper deep neural network. We're going to have these two hidden layers and an output layer. And I'm going to show you how to design it and how to write the code. And I'm also going to move away from showing you the actual RPubs document. We are here in RStudio and we're going to look at the actual code. Now it's already all written, as you can see here. And what I did to create it was just to say it's a new, so on that little triangle there, R Markdown. This is a Markdown file. Now a Markdown file is different from a script file. You see script there, in that we have this rich environment. Most importantly, up here, very small, you can see this little tab that says knit. And if I click on that downward facing little arrow there, we see I can knit this file to an HTML. That is what we do to create a file or an HTML file to upload to our pubs or upload to the web. And I'll put the link in the description below of this exact document. You can also knit to a PDF and you can knit to Word. So it is a lovely environment from which you can create all sorts of documents. Now I want to show you the code, the RStudio coding environment itself, and then the deep learning. So there's a lot to this video lecture. So it always starts off with these three little minus symbols and closed by those. Inside of these is a type of language, I suppose you can call it that, called YAML, Y-A-M-L, just another markup language. Now the web is built on HTML, hypertext markup language. That shows a web page how to display things together with cascading style sheets. And markup language is, you could see that as a simplified form of HTML. And what we have here is a few things that are pretty standard. There's title, author, and then output. And you see the title, that will be the title that's displayed on the top bar of the website. It'll have the author listed. And then output, I'm specifying here that it must be HTML. So I am going to knit it to HTML, but I'm specifying, overriding that by saying this must be an HTML file. There must be a table of contents, and then the number sections is false. So it's not going to have number 1, number 2, number 3 to the different headings that I do have. All the code that you write go inside of these three little tick marks. On my keyboard, it's top left next to the number 1 key on the top row. And you have to have 3 of them, and you close with 3 of them. And you can see that RStudio colors this in a different color. Mine is light gray, as we can see here. And the first line stipulates inside of these set of curly braces a few things. The first thing is states the language in which this piece of code called a chunk is written. And I'm specifying that it's written in R. You can give this chunk, this piece of code inside of these little tick marks, a name. You needn't do that. This is done automatically. So this chunk was called setup. And if we look right down here, there's a little tiny little piece of text there. If you click on it, you can see all your code chunks, and you can see there chunk 1 setup because it was named, but I didn't name all the other code chunks. But if you do name them, it's easy to navigate to those code chunks there. Include equals false. This means this is not going to be shown in the final HTML or PDF or Word document. This is also set up automatically. You don't have to worry about it. There's some options here. The echo is set to true, which means that in all the other ones to follow, unless you say include as false, the code is actually going to show up. And I've introduced this set working directory to get working directory. So it's going to get the working directory where this actual RStudio file is saved, RMD file is saved, and it's going to take that address on my solid state drive of my computer, and it's going to set that to the working directory. Now here's another code chunk. Well, before we get to that, you have different ways to run this code chunk. When you're inside of it, you can click the run button up there, or you can click this little run button right here, and you'll see there's a brief little green stripe there, and it will go from top to bottom as it executes the lines of code, and it is now executed. Another way to execute that is to have your cursor somewhere inside blinking there, and to hold down Shift, Control and Enter. That's PC and Linux I should say, or Shift, Command and Return on a Mac. That'll also, if you have that key combination, it'll also execute. So here's my second code chunk, and again those 3 little tick marks, you can type them in. And I'll show you a keyboard shortcut for that a bit later. And again, open and closing curly braces, and I only have R in there just to show that this is R code. I haven't given it a name or specified anything else. And I'm going to import 3 libraries, Reader, Keras, and DT. But see that it's also enclosed in a separate function called suppress messages. If you import these libraries, it's going to give you a bit of information. Some of them contain functions that overwrite the base and core functions in R, and you'll get those little messages, but I don't want to see them on the screen, so I just say suppress messages, and then library, Reader, Keras, and DT. Reader is a package that helps to import files such as spreadsheet files in a better way than the base, or an extended way than the base or core R can do. Keras, of course, is our deep learning neural network package, which is going to provide us with function and code to be able to design and run deep neural networks. It sits on top of TensorFlow in my case. And then the DT stands for data table. It is just a package that allows for you to create very beautiful dynamic and interactive tables on a web page. Because I'm going to export this as RPubs, I use DT just to do that for me. Now this piece of code here was also something that I introduced as a bit of cascading style sheet, and it just says that my heading 1, heading 2 and heading 3 should have different colors. It's that royal blue and then the orangey gold that I always use. This is also a line of text that I introduced. If you do this in this way, so we see the exclamation mark, the open and close square brackets, and then inside of parentheses, this is the name of the file that lives in the same folder directory as this file, which is a PNG file, and that is the image, the logo that you see on the RPubs documents. So if you wanted to put your own logos in there or any other kind of image file, this is the way you go about it. Next up we have two hashtags, pound signs. Hashtags, I think, is what most people would know them as. So we have the two hashtags. That's markdown language, and that indicates that whatever is to follow must be in heading 2 size. So that gives you a nice heading to the paragraph that is to follow, and it's the introduction. And on the RPubs file, or when you download this specific file from GitHub, you can read all about this, what is coming in this lecture. So let's start with the data. We're going to import a file. It's a CSV file, comma separated file, so it was opened up and created in Microsoft Excel and just saved as a CSV file. It contains 50,000 observations, so 50,000 rows with 10 feature columns, so 10 feature variables, and then a target variable that is binary. So it only has 0 and 1s in the sample space of that target variable. Remember, the sample space are all the different elements from which the values that actually go into the target values. The data point values are chosen from a set, and in this case it is nominal categorical, and there's only a 0 and a 1. So I'm going to use this read_CSV function that's different from the read.csv. That's the built-in core R function. Read_CSV comes from the reader package, and it creates what is called a tibble, which is different from a data frame, and the data frame comes from the read.csv, and there's slight differences between the two, most notably in the way that the data sheet is displayed, especially if you use an R script file. It just displays it differently on the screen here in RStudio, making it more manageable, and there's subtle other differences which we needn't be concerned about now. You can read about some of them there. So here's our code again, tick marks, curly braces with the R, and I'm going to create an object, a computer variable called data.set. That's my choice. That's what I use when I import files. You can use your own name. Just bear in mind that there shouldn't be illegal characters like spaces and leading numbers, etc. And again, my assignment operator there. Now the assignment operator is easy to do. It is just Alt or Option and the minus key shortcut. So read_CSV, and now the name of the file, which will be available on GitHub, simulated binary classification dataset.csv inside of quotation marks, and I'm setting the col names argument to true because the data file does have its first row in the spreadsheet file is the column names. And then I'm using data table. Now data table is a function from the DT package, and I'm going to pass to it what I want to be printed out. That is data.set. So data.set, I want that expressed as an HTML table on a website eventually. And I'm using, remember what these square brackets are, they are addressing for row. So there's the row, comma, there's the comma actually, comma, column. Now you see the column is empty, and if you leave it empty like that, it means all of the columns. So which rows do I want? There are 50,000 rows. I don't want all of them. So I'm just going to take a 1% sample, random sample of all the rows to put in my HTML table here. So I'm going to specify the first argument in the sample function. Remember, this is all part of which rows to select, comma, which columns to select. So I'm going to use the sample. The first argument is the total number of rows to select from, and I'm using the number of rows in row function and passing the data set object to that. Replaces false, so when a row is selected at random, it's not put back into the bowl to be reselected. So I'm saying that as false, and the size, the number of rows or samples that I want, is 0.01 times the number of rows of the data set. So that's 1% of the data set. So that's a random selection, a random sample of all the rows, showing all the columns. And when we run this bit of code here, we execute that. First we have to import it. So that happens quite often when you do this. So we've got to go all the way back up, and we didn't execute these lines of code. So let's set the password. Let's import all of those libraries. Let's go down, let's go down, let's go down. You see the little red there? It tried to execute and gives you an error. It says cannot find read_CSV because we did not import the reader package yet. So now we do that. You see the green line. That's all done. And you can see a representation of what it is going to look like on the eventual HTML file. Very nice, because you can select these variables and you can order them in descending or ascending order. You can search for specific values. Say for instance, some of these were names, nominal categorical variables. You can search for them, and you can go previous and next and look at all these pages. Very nice way. Now I'm going to use the summary function and pass the data set to that. Let's just do that, and that's going to summarize all of the columns for us. And we see that the column names were var1, var2, var3, var4, 5, 6, 7, 8, 9, 10, and the last column, column 11, was named target. That's in this actual spreadsheet file. And we can see the descriptive statistics: min, first quartile, median, mean, third quartile, max. And you can see all these values have a mean of around 0, so they like from a standard normal distribution. This was a specially created data set, which makes the training of the neural network that we're going to create very easy. So it was designed specifically for this, with this lecture in mind. Now, we've imported this data, but it does not exist in a format that we can pass it into the neural network once we design the neural network. So we've got to prepare the data, and that's called pre-processing. And we've got to go through a few steps. The first step is to take this tibble, this data frame or this list, whatever you want to call it, and transform it into a mathematical matrix. Now remember, that's a type of tensor, and if you were to bring in images, so eventually we are going to bring in images as data, that has to be transformed, and we're transforming this into a tensor, and in this instance a matrix, because we're going to have rows and columns so that's going to be a rank 2 tensor. And so we change that into a rank 2 tensor or matrix using this as matrix function. So I'm going to recast the data set as a matrix data set. So now it's not a tibble or data frame or list anymore, it's now a matrix. And then I'm going to discard all the column names so that I only have the numerical values. And for that I say dim names of the data set, set that to null. So all I have is this rows and matrix of numbers. Now, if we had categorical names in there, like benign, malignant, whatever, we would have to change that into numbers as well. But in this instance, in this simple first example, we have none of those worries. They're all numbers to start off with. You could see that they were all numerical, and all we're going to do is just change it into a matrix and remove the variable names, the column header. Now, the next very important concept to understand is the splitting of your data. Now, you've got to split your data into two parts, a training set and a test set. Very important. You want to take some of the data out of the data set and keep it separate and call it a test set. Now the test set must not be seen by the matrix. It must contain some of the samples, some of the rows that will never be seen during the training phase. So we've got this test set, the training set, which makes up the majority, and we'll speak about how to split it and what size is used for the split in a moment. We are going to split it so that the training set is what we actually pass to the neural network, and from that it's going to train and optimize its parameters by minimizing a cost function and this continuous process of forward and back propagation and the back propagation through gradient descent. We've talked about all these things, but then once it's all done, we want to pass new data to it that it's never seen before, data to which we know the answer, so it comes from this original data set in which the target is known. This is supervised machine learning, remember, and then it can test the accuracy for us. So we've got to do this splitting of the data. By the way, we see the three little tick marks, so we're coming up to a next bit of code. I just wanted to tell you how to do this in a shortcut way. So instead of typing this, all you have to do is hold down Control, Alt, and I, the I key. That's PC and Linux, and on Mac that will be Command Option I. So if I just do that, you see all of that was created in an instant, and it's ready for me to write some code. So that keyboard shortcut is very useful. It's highlighted and deleted. So what do we have here in this? I'm going to use the set.seed function, and that means every time this piece of code runs, it's going to generate the same random values for me in the same order, because I'm going to generate some random values here, but setting the seed, and you can use any numerical value here. I've just used 1, 2, 3. You can just use 1 or 1, 2, 3, 4 or 10 or 15. It doesn't matter. But it just means that every time this code is run, it'll follow a little recipe during the pseudo random number generation, and every time we run this code, we'll get exactly the same values out. So I'm going to create an object called index, short for index, and I'm going to use the sample function that we've seen before. The first argument is 2. Now what happens here, it creates a little list. It starts at 1, and it counts up in whole numbers, so in integer values, to wherever you want it to stop. So in this instance, I'm going to have a sample space of just 2 values, 1 and 2. And the next argument stipulates how many of these I want, and I want that to be equal to the number of rows in my data set. Replacement is true, so at random it's going to pick a 1, but now there's only 2 left in the bowl, the number 2 left in the bowl. So next time I can only pick 2, so I can only have 2 random values. But what it does is imagine there's a little card in a bowl, and both of them, one's got a 1, one's got a 2 written on it. They fold it, you put your hand in, eyes closed, wriggle them around, take out 1 at random. You see what it is, jot it down, and you put it back in the bowl. That's what the replacement is. So that means I can do this thousands of times over, and I'll get 1, 1, 2, 2, 1, 2, 1, 2, whatever. So replace is true. And I'm also setting a probability in the same order in which these two numbers came. Because we used shorthand, we just wrote the 1 number, but remember there's a 1 and a 2. I'm going to set the 1 to be chosen with a probability of 90% and 10% for choosing the second one, which is a 2. So very imbalanced here, 90%, 10% at random. So there's going to be many more 1s than there are 2s. Remember, this has got a sum to 1. So we're going to run that 50,000 times. Let's run that 50,000 times. So I've got this long list now of 1s and 2s, of which there are many more 1s, and they are equal to exactly the number of rows in my data set. So that's great, because now we can actually use this to split our data. Now there's many ways in R to split the data, so this is just one way. It's a little bit laborious, but let's have a look at it. I'm going to create two objects now, one's called xtrain and xtest. Now it's customary in machine learning to use x for your matrix of features. So that does not now contain the target, the column vector of the target variable. If you draw out only the features, we usually call that x, and I want two. I want a training set and a test set. And what I want to do is to assign to that the original data set, and then I'm going to use square brackets. That means I'm going to do row, comma, column indexing, addressing. So the rows I want where index equals 1. So this is very compact code. So it's got this index 1, 1, 2, 1, 1, 1, 1, 1, 2, 1, 1, 1, 1, 2, 1, 2, 1. Go through all of those, all 50,000, and wherever it's 1, it is going to use that for the row. So it's going to select all the 90% of the original rows. It's going to draw them out, and the columns I want is only columns 1 through 10. Those are the 10 feature variables. So remember, there were 11 columns, so 11 is the target one. I don't want that. And the test set is then where the index is 2, which only comprises 10% of the data, and also just those. So I'm creating these two I am creating these two matrices, a train one and a test one. I should call them two tensors. So that takes care of splitting the data as far as the features are concerned. We need to do exactly the same thing for the target, and we better have them stay exactly the same. So the same ones stay with the train and the same ones stay with the test. Otherwise we may mix them up. This makes no sense whatsoever. There's one little side track I have to go down, because later on I want, when we do the testing, I want a separate object, and I'm going to call mine yTestActual. And I just want to save that separately, because remember, that is what we're going to test against. That is our ground truth. So I'm going to take data.set where the index is 2, so that means it's going to be equal to this x test, and column 11. So I'm just going to store that separately. I always do that right in the beginning, just to keep them separately. Okay, we're almost there. We still need a bit of pre-processing. The last bit we're going to do is something called one-hot encoding. Now, one-hot encoding is something that we use quite often, and it changes a single data point value into a lot of dummy variables. So remember my target variable consisted only of 0, 1, 0, 1, 0, 1, 0, 1. But I want to create, because there are only 2 to choose from, my sample space is 2, I'm going to create 2 dummy variables. And they're always called 1 and 2. If they're 3, they'll be called 0, 1 and 2. If they're 4, they'll be 0, 1, 2, 3. Doesn't matter. So one of these, the 0, would represent one of the elements in my sample space, and the other one would represent the second. So imagine I didn't have 0 and 1s, but I had benign and malignant. There are 2 in my sample space, so imagine my target just said benign, malignant, benign, malignant. One-hot encoding means I'm going to form 2 dummy variables called 0 and 1, and the 0 will be benign and the 1 will be malignant. So now I have 2 columns in my target variable, a 0 and a 1. And if that specific one says benign, I'm going to mark a 1 in the 0 column and a 0 in the 1 column. Makes sense? One-hot encoding, so only one of those possible ones will have a 1 under it. And if the 1 is under benign, which was 0, that means that was benign. And if the 1 is under malignant, and all the others, the 0 in this instance, have a 0 under it, it means that was malignant. So let's do that. And there's a Keras function called toCategorical that will do that for me automatically. So pay attention. I'm going to create 2 objects called yTrain and yTest. y_train, y_test, and I'm going to use the toCategorical function. I'm going to pass my data set and again use addressing, so index is 1 and index is 2 and only column 11. Let's run that and let me show you what it looks like. The noise outside is obviously tremendous. Again, apologies for that. I mentioned in the other videos it's the Neuroscience Center built right outside my office window here. Unfortunately, nothing I can do about it. I'm going to open the environment tab up above, which was not open initially. And all the objects, computer variables that we've created are listed here. So we've just created yTrain and yTest. Let's have a look at them. I'm going to show you yTest. Let's open it up by hitting that little button. We see this opens up here. Now look at it. Instead of there being a single 0 and 1, 0 and 1, we have these 2 variables. And the first one was a 0 and the second one was a 1. It's the one that has the 1 under it. So this means this first one was a 1. You can see the second one was a 1. Third one was a 1. Fourth one was a 1. Fifth one was a 1. Sixth one was a 1. And that's the one-hot encoding. So if you had more, because your sample space was bigger, only one of them would have a 1 under it. One-hot encoding. Right, let's carry on. Let me do this bit of code. I'm going to use the cbind function that's going to combine whatever I give these are vectors, those are R vectors, and I separate them by a comma, so it's just going to combine all of these as columns. Let me show you. So there we have, the first one is called yTestActual 1 to 10, so these were the actual values. Remember I saved that separately, so my test set, the actual target were 1, 1, 1, 1, 1, 0, 0, 1, 0, 0 for the first 10. And now I'm passing white test, which was one hot encoded, as the next two columns. So you see column 2 and column 3. So because this was a 1, the one hot encoding gives me 0, 1. And when it's a 0, the one hot encoding gives me 1, 0. It's the 1 under the 0 column, and therefore the actual one was a 0. So I think you get what one hot encoding is all about. So we are doing that in this instance. Now, strictly speaking, you can have a sigmoid function, an activation function. I'm going off on a tangent here, but bear with me. You can put in a sigmoid function in your output node, but we're going to do something different here, and I do that on purpose because in many instances our sample space is going to be more than just 2. That would be quite common. And it's good to get used to this one hot encoding and having a different activation function for our last couple of nodes, and not only to have a single node. It's a sidetrack. You'll better appreciate it as this course continues. Now, very, very exciting. Let's create our first model using Keras and TensorFlow. Going to skip all of those, that written word, and here we are in this chunk of code. We're going to create a model. First of all, we're going to give it a name. So our object's called model, just model. And I'm going to say that this is a special kind of object. Remember when we created functions, we started off by saying object and then assign to that a function, and then in parentheses what the arguments are, and then inside of curly braces what the function actually does. Similar sort of thing here. I'm going to specify that this object is a Keras underscore model underscore sequential. A sequential model using Keras. Inbuilt function in Keras. There are two ways that you can create deep neural networks in Keras. One is the sequential model, which we use quite often, and the other one is a functional API, which allows for very intricate modern type of neural networks to be designed, and we'll get to that in a future lecture. So I'm just instantiating this object, and I call it model, and it is a sequential Keras model. Now you're going to see something new. This is a pipe symbol. So it's a percentage greater than percentage, and all it does is shorthand. It takes a function, so the function is actually called layer underscore dense, which is part of Keras, and it takes whatever's on the left-hand side of this pipe symbol, which is model, and it passes it as a first argument. So right there with a comma. So it's actually layer dense, comma, name, etc. But what the pipe does is it allows for you to embed things. So you'll see another pipe there and another pipe. So this model goes as first argument there. This whole thing from there to there goes as first argument right in there. And then all of this goes as first argument in there. So it's this layer upon layer upon layer. It's a very nice part of R. It's actually part of what is called the tidyverse, and we might have time to discuss that later. But it's a very nice design so that you can still set out things like this, but just like telescope it, but pull it out so one thing fits inside of the other thing. Don't worry too much about that. So we're going to say model and pass that to the first layer. The layer underscore dense. It's a function in Keras, and it says that this first layer is a dense layer, a densely connected layer. I'm just going to move down. Oh, we'll have to look at that separately. We're going to just do the dense layer. The first argument is a very optional argument. I'm giving it a name, deep layer 1. See, there are no spaces there. That would be illegal. So I'm just going to give it a name. You do not have to give it a name. This is just for completeness sake. I'm stating that the first hidden layer must have 10 nodes. Remember, I had 10 feature variables, so I'm going to use 10 nodes. That's up to you. That's what is called a hyperparameter. A hyperparameter is something that you decide on during the design of your network. I have just decided that my first hidden layer must have 10 nodes. Up to you. The activation function, you've seen this one before. I want that to be a rectified linear unit. And for your first dense layer, you have to stipulate the input shape, because it doesn't know what data you are going to pass to it after the design phase. And you need to stipulate the dimensions of this incoming vector, which remember is each row vector, the samples, one row after the other that you're going to pass into this network. And because there were 10 variables, I'm passing the number 10 to it. This refers to the number of variables, feature variables, in my data. And it is because we're going to do behind the scenes. Remember, forward propagation is the inner product between two tensors, and those dimensions have to be correct, otherwise that inner product, that tensor multiplication, cannot happen. It's a type of mathematics, remember, linear algebra, and it cannot happen if the dimensions are not proper. So I've got to stipulate that. Now all of that gets passed into a next layer, another densely connected layer, hence I use the layer.dense. Name, I'm going to call it deep layer 2, needn't do that. Again 10 units, again the rectified linear unit activation function. This time though, the size of the dimensions of what gets passed need not be stipulated. It would be inferred from what is coming in. So from that 10 and this 10, it can infer what the dimension should be. You needn't do that. You needn't worry about that for subsequent layers. Then another dense layer, and this is going to be my output layer. It's going to have 2 nodes, and the activation function is not sigmoid, it is softmax. Now in the future we are going to discuss these, including softmax. Softmax is a very special kind of activation function. What it does, it takes the number of units that you have, the number of nodes in the layer, and it will, after activation, provide a probability for the value in the first node and the value in the second node, such that the probabilities add up to 1. And you can see where this is going. Because we must predict either a 1 or 2. It is going to have a probability for the number 1 node and a probability for the number 2 node. And similar to what we did with the one-hot encoding, what it's then going to do is going to take which node, the 0 or the 1, had the highest probability, and that will become the predicted output. Lastly, I'm going to call summary of the model. Let's do that, run that, and it will give me a little summary of the model. Now, how does this work? It gives the layer and its type, and because I called it deep layer 1 and deep layer 2 and output layer, we're actually going to see those names there. If you didn't put the name, there'll be something generic there. It says the type. Both of these are densely connected layers, so all the nodes are connected to each other. The output shape is going to be these column vectors of size 10, 10, and 2. And we specified that with a number of nodes. And the number of parameters that it has to learn through continuous backpropagation, forward propagation, backpropagation, forward propagation, backpropagation, like backpropagation using gradient descent to minimize the cost function until we have optimum values. It says how many parameters there are in each layer. Now, how did it get to 110? That's very easy. Remember, I had 10 in my input, so there were 10 nodes in my input, and the first one had 10 in it. The first hidden layer had 10 units in it. So if each one is connected to each one, that's 10 times 10, that's 100. And remember, each of the 10 in the first hidden must also get input from its own biased value. And that biased value must also have a size of 10. There must also be 10 of them. So 100 plus 10 is 110. Same for that 110. And the last one, remember, there are 10 nodes connected to 2. So each of the 10 has 2 connections to it. So 10 times 2 is 20. But that 2 also has input from a bias node. So that's 2 extra, giving you 22. That means I have a cost function that is a multivariable function with 242 unknowns. Now remember from school, y equals x squared. The x, that's a single unknown. I now have an equation with 242 unknowns which I have to optimize through partial differential equations, just through taking partial derivatives, I should say. So that is beautiful. You can see it coming together. It is so nice. Now I've got a little image there. That's what I wanted to show you, but I've forgot that you don't actually see it here before we knit it. So I'll show you what that looks like. Now that my network is created, I have to compile it. Now I'm going to introduce a few new things here which we're not going to cover, so just have a look at them and we'll discuss them later. So the compiling of the model says, again with a pipe, use the compile function. So the first argument is going to be model, but I don't do that, we use this pipe. And then I've got to specify a loss function, an optimizer, and a metric. Now the loss function, instead of mean squared error, we're going to use categorical cross entropy. We're going to discuss what that is and how that differs from mean square in the future. Just take my word for it, this is a better loss function. The gradient descent is going to be done in a specific way which is different from the very generic ways that I showed you before, and it's going to use an ADAM, what is called ADAM, an ADAM optimizer for this gradient descent. Stochastic gradient descent is another famous one, and the metric we want to use is accuracy. So our measure of how well the model is training is going to be accuracy. So we've created our model and we've compiled our model. Let's fit the data to it. And to fit the data, there's going to be a few other things in here which we'll discuss later. And anyway, I'm going to call this fitting, I'm going to give that a name object, create an object called history. And it's going to take the model and pass it as first argument to the fit function. The fit also part of keras. In the fit function then, the model is passed as first argument through this pipe symbol. I'm going to pass x train and y train to it. So x train is my matrix of feature variables and y train is my matrix of target values, which is one hot encoded now, remember. Epochs. We've discussed epochs before. That is how many times we're going to have a step of full forward propagation and back propagation. So going through all the data once forward with all the tensor multiplications and additions of the bias values, and then activation functions creating the value and then creating a loss. So the prediction and then a loss. So all that and then back propagating through gradient descent, through the derivatives, and updating all of our weights, our parameters, so that full one's going through the network once and coming back through back propagation. That's one epoch. And I want 10 epochs. I want it to run back and forth 10 times because I know every time I should have better parameters. The batch size is something new. What the batch size is don't run through all the 45,000 samples in one go. Do it in small little pieces and then update in small little pieces and update in small little pieces. And I'm going to set it to 256. By the way, if you're using a GPU for your training, which we're not going to use here on this machine, although I do have a GPU, I've only installed the CPU version of TensorFlow in Keras. Make it a power of 2. So 2 to the power 4, 2 to the power 5, 2 to the power 6, 2 to the power 7. So I have 256 here. It's just a good way for memory to work in these size batches if you use powers of 2. That's also, all of these are hyperparameters. So my 10 epoch size of 10, my batch size of 10, 256, my mini batch size, for which the argument is only batch size, not mini batch size, but this is actually referred to as a mini batch. These are hyperparameters that I set. Now here's another thing that's new, a validation split. As we split the data into a training and test set initially, I'm also splitting the training set within the learning process. That allows for this network to have this special little set held separately, so 10% of the training set, and test itself all the time so that we can view it and see that it's actually doing well. It's obviously going to do well on the training set because it knows what the answers are and it's doing that forward propagation, back propagation. But now I'm giving it data that it hasn't seen inside of this training phase, which is called the validation split, just to test itself. And you want that to also come down. If that doesn't come down, it means something, again, something that we're going to discuss in future, that it is not generalizing well. It is learning the data too well, and it's memorizing your data. And if it memorizes the actual data, the training data, it would not generalize to unseen data that well. Points that we'll really discuss in depth in future videos. And then there's this verbose argument. It just tells what to show on screen as this runs. So let's do our first training. Whoop, there we go. And we see a few things happen on screen. So even though there's 45,000 rows of data to go through in batches of 256 forward and backwards, we see even on a CPU, now this is a Core i7 CPU on this laptop, rather high end, so it's not too shabby and it's running quite fast. You'll see a little bit of nonsense up here saying that the TensorFlow binary was not compiled using some of the features in this specific Core i7. You're always going to see that. You can just ignore that. But it does stipulate that we're using the CPU here. And they ran through the first epoch, the second epoch, up to the 10 epoch. It'll tell you how long it took. The first run took a second, and then it was a fraction of a second to run through the other epochs. If I run this through a GPU, it'll be much, much faster. It said it ran through 40,000. Remember, there was a validation set of 4,512 samples kept out. Now let's see what happened during the first epoch. It had a loss of 0.7 and an accuracy of only 59%. And of the validation set, it had a loss of 0.47, but quite a good accuracy. Now remember, the accuracy is the correct predictions. It's the correct predictions divided by the total number of 83%. And now it went back through back propagation. It had better values to start off with for these weights. Now something we didn't discuss, the first time it runs through, there are random values. All those parameters, 242, were given random values to run through the first time. Somewhere on that multidimensional curve, we start off at some point. It was just totally random. But now, through gradient descent, it got to better values. So the second epoch was run. The loss fell dramatically for the training set. The accuracy went up to almost 91%. The validation went, the error dramatically decreased as well, and the accuracy went up. And you can see as we go along, it gets better. You might have also noticed this beautiful graph that RStudio provides for us, and this is really great. And one of the reasons why I love RStudio as opposed to just running this in a Jupyter notebook and using Python, is that this was a dynamic thing that happened, and you can see the validation is in green and the training set is in blue, and you can see as the epochs were running, the error got lower and lower and lower, and the accuracy got higher and higher and higher. And what you see, something that we'll get into, is these two are very close to each other. So it is generalizing quite well. The training is not only specific to the training set, which will always get better here at the bottom. The loss will always go down, the accuracy will always go up. But in tandem with that, the validation set, which it just uses to measure all the time, also gets better. That means it is generalizing well to data it has not seen before. So that is a very good marker. Now, this is a toy data set, simulated data that I designed specifically for it to do this. This is not what you're going to see in the real world. And we'll certainly do some more real world examples in the future, and you'll see these two being quite far apart, and that's bad. And you'll see what we call it, what the problem is, and what to do with it, how to change the design of your deep neural network to combat those problems. I'm just going to use the plot function, and it's going to create a nice little plot here. It's a GG plot type of plot that we can see of the loss and the accuracy, in case you wanted to save that and use that in a publication. So let's evaluate our model. Now I'm going to use the evaluate function, and now data that it hasn't seen at all. It's not the special validation set that it kept out during the training phase. It's the actual data that it has never ever seen, X test and Y test. I'm going to pass that to the model, and this is where the tire hits the tar, whatever that saying is. So it says of the data that it's never seen before, the loss was 0.158 and the accuracy was almost 96%. Not too bad. We can improve it though. There would be ways to get to change the design to get even better, but that's not too bad for data that it's never seen. It was 96% accurate. Now you're not going to get to 100%. When I designed these 50,000 rows, it was designed so that there's a bit of overlap, and that is what happens in the real world. You're going to have variables, and for similar variables, you're going to get a different target value, or the other way around, and that's real life. And it's because the variables that we gather are not always representative of what the real causes are. The target is not caused by the variables that you have in there, and that's a fundamental problem, which is very difficult, specifically in healthcare, in that the variables, the data point values for variables that we do collect is not necessarily the ones that determine the outcome, the target. Or they might be surrogates of a deeper lying physiological process that we don't understand yet, and we can't collect data on that. And that's the true determinant of the outcome, the target value. And that is a real world problem. That's a problem that we deal with in normal statistics and here in machine learning. Are the variables the actual ones that cause the actual outcome? That's a deep deep debate that we can have there. But let's carry on here. I'm going to do something else called create a object called predict, and now we're going to do the predict classes function, and we pass x to it. So it's only going to give us the prediction of the test. Is it predicting a 1 or 0, 1 or 0, and I'm going to pass that to a table, and my table is going to have 2 rows and 2 columns, and I'm going to call the top part predict and the bottom actual. Let me run that and show you what it does. It's called a confusion matrix. So the actual goes on the top, that's the second one, and predicted goes on the left hand side here. So it says if the actual value was 0, remember that comes from this y actual, it was predicted as a 0 in 2,424 cases, and if the actual was a 1, it was predicted as a 1, and that's what this predict classes is going to give me, just this long list of 0, 1, 0, 1, 0, 1. If it was actually a 1, it was right in 2,250, but if the actual was 0, in 34 cases it was predicted as a 1, and in 173 cases where it was actually a 1, the prediction came out to be a 0. This is called a confusion matrix, and it also helps us to determine, it's a visual way of seeing how good this test data was managed by this network that was trained. Another function that you could use is the predict probber, and I'm going to save that in a computer variable called prob, because what I want to show you is what happens. The predict probber is going to give me the prediction of, in this instance, only because we have a 0 and a 1, remember through the one hot encoding, it's only going to give me the probability of this first one, the 0. But because we've set it up, we're actually interested in the 1s, so I'm just going to subtract them from 1. So the prediction of the first one, the 0, is going to be subtracted from 1. That gives me the probability of the second one, the 1. So if I run that and I do the first 5, you can actually see what the probabilities was in my one hot encoding, my second node in the output, the 1 in actual fact. So it was 99%, 99.99%, 56%. That was a close call. So it just shows me this first 5, what the actual value was in node number 2. And that's what the softmax function did. It gave a probability for the second node and the first node, and I'm only looking at the probability that was outputted from the second node through the softmax function. And what actually happens for us to get either 0 or 1, there'll be this cutoff of 0.5. If it's 0.5 or higher, the final the final prediction would be a 1. If it's less than 0.5, the final prediction would be a 0. Now, let's do that through cbind, so you can actually see what happens. So I'm passing 1 minus prob, so that was the probability in the second node, and then I'm passing the predicted value based on that for rows 1 to 10, and then the actual one which I saved right in the beginning. So we see that the second node was the highest at 99%, therefore the prediction was 1, and that was quite correct because the actual value was 1. So you can see how this all comes together. And that's it for this very long lecture. I hope it was as exciting for you as it is for me. Deep neural networks and the design of it using Keras on top of TensorFlow here in R is just such a wonderful, exciting thing to do. It really is just such a pleasure, and I really hope that you are as excited as I am. So download this file from GitHub. Look at it on RPubs, and in RPubs you're actually going to see what it looks like. Let me do that for you. So let's save everything we've gone through, and now I'm going to knit. So I'm going to knit to HTML. Let's go. I'm going to warn you, if you use the GPU version of TensorFlow and Keras, you're going to run into problems at times when you do this knitting. It might not work properly for you. If you use the CPU version, it does. And here on the right hand side we see the viewer. This is what we now can publish to our pubs. And I've already published it, so it's going to say republish. But this is what the document looks like. All the web elements done very nicely. We see what we typed. There's this very nice column thing. We can look at page number 2, page number 3, page number 4. Very nice widget there. We see the summary there. We see the colors of the different headings that I did in the cascading style sheet initially. And I just wanted to scroll down actually and just show you give you a visual indication of that network. This is the network that we created in visual form. So I have my 10 input nodes, and they densely connected. So they connected, each one is connected to each of the other ones. And that's why you get the 100 weights here. But there's a bias node as well. So after this tensor multiplication, we're going to add this column vector of bias node values. So there's another 10 giving me 110 weights there. 110 parameters, of which 100 are weights and 10 are biases. And another 110 here, and then the 22 there, giving me the final output of these two corresponding to the one hot encoding. So whichever one through the softmax gets the highest probability, that's going to be the final predicted value. I'll speak to you in the next video lecture. Now let's continue our look into deep neural networks. Now I want to pause a bit and discuss poor performance of a deep learning model. So if you come across this video and it's the first one you see, please go back to the beginning. That really is my suggestion. Watch the whole series. One lecture just builds on the other. Now in the preceding lecture, we looked at building our very first neural network. We had these two hidden layers. We wrote the code inside of RStudio using Keras with the TensorFlow backend, and that to me is very exciting. In the real world though, no one ever writes a single neural network and just runs the data through it and everything works perfectly. It's beautiful. There are usually problems with the results. The code works well, the neural network performs well, but the choice of the hyperparameters and how the network is constructed must be changed based on the results that you get. There must always be this attempt at improving the model. So in real life, there's data pre-processing, usually with the help of a domain expert. Now that doesn't always happen, but having a domain expert present when the data pre-processing is happening really makes a big difference. A network is designed. Later on we'll also see that you can just import some already existing networks. We run the model, put the data inside of the model, we get results. We have to look at those results. Somehow we have to interpret what they mean and how good, especially how good they are, so that we can subtly change things to that model, change the hyperparameters, change the architecture of the network, do something else to improve the results. Now for that to happen, we must have some way of understanding what went wrong. And I don't mean what went wrong in the execution or writing of the code. Why is the results not as good as we think they would be? Or better still, how can we think about improving them? So first of all, let's just go back to the training and the test sets. And there's something specific about these that we might have mentioned before, but we should just spend a little bit more time, because it is this pre-processing of the data that is really important before you start assessing how well your model did. Now, I want to remind you that you have a data set and you then split it so that you have a training set, that is the data that's going to be passed to the model, and it learns from that, a big black box that learns from the data. And then you must pass a set of data to it that it has never seen before. So the model never learned from these new cases, and that's the test set that we keep totally separately. Now, you don't always need to split that from an existing data set. It might well be that you have a data set and you use that data set, and while the network is being developed and while all of that takes place, the data collection continues, and it's this new data that is going to be the test set. So it needn't just be a splitting of the original. So that can also happen. One thing though is to consider just the size of the data set. We mentioned before that if the data set is very small, the norm used to be this, we can see it there, the 70-30% split. Because we needed enough data in this test set to make it worthwhile to make the testing accurate. But in modern days where we have perhaps millions of samples, we can really have this 5% or 1% split in making that test set. That will still contain enough samples to be representative of the whole data set in itself. Now, a few problems might arise here. It might very well be that the test set and the training set are not the same, especially when they are collected, that data is collected at different times. Think, for instance, of cases where images form the data that we want to train on, and that the training set might be very nicely selected, high-resolution images, so that we have this fantastic results when we do the training. But then when we pass real-world images, they might be blurry, the lower resolution, we get very poor performance. So there's this difference between the training set somehow and the test set, and those differences must be minimized. In the end, we want a model that will work well on real-world data. That brings us to this point of a class imbalance, one of the types of distribution, where we think about distribution in our data. Think, for instance, of a situation where one of the elements in the target variable occur very infrequently, that 95% of the target variable is just one class, one of the elements, and less than 5% is the other. That just means if that really exists, I might as well just guess the majority class every time. I'm going to be right in 95% of the cases. Why do I need a deep neural network? So if that is the truth in real life, then yeah, perhaps you don't need a neural network. But if it's because there's something wrong with the data collection that there's this class imbalance, then you have to do something about that. And one way to go about it, of course, is just better data collection. But if that is not possible, to look at something like data augmentation, which we'll discuss, we'll discuss later. Another point to belabor is that a training set is not absolutely required. And some data scientists will take the whole data set initially and just do the validation split inside of the model. And some even refer to that validation set as the test set. Another name for it also is also a holdout set. But that holdout set, validation set, that is, or development set it's also called, that can be done inside of the model, and we saw that in the preceding lecture, that validation set can just be extracted when the model is training, and we can just see that as our test set. So when you see that occur, don't worry too much about it. Just to be formal here, we're going to talk about a training set from which we split a small little validation set during the training, and we have the separate test set. Just make sure when you see that that you're not confused about it. So really put these thoughts into before designing, just think about the data for a minute. Think about the things that can go wrong with the data, and specifically the splitting of this data. The next important thing to talk about is just the idea of a ground truth. Have you ever just thought about it? Somehow, someone, or by some means, every sample in the data set had their target variable denoted in a spreadsheet, in a database, doesn't matter how. But someone or something decided that that is the actual value that has to go in there. That if this is a CT scan and that is a benign nodule or malignant nodule, someone marked that as benign or malignant. And that there might be an error there. That might have been wrong. And what we refer to as the ground truth, the labels that exist in the data set that we have, might not be absolutely correct. So we're training on something that has an inherent mistake in it. Now there is this idea of an optimal error. That's the maximum theoretically the smallest possible error that exists in the target data set. It's also called Bayes error. And that is what we are trying to work towards. We want our models really to achieve, or get close to this Bayes error or optimal error. And at times this can be different from the human error rate. So imagine we have a bunch of CT scans and it was a radiologist who just sat, or a couple of radiologists, and they just marked this one is benign, that one's malignant. There's going to be some human error in that. So at the very least, we really want our models to exceed the capabilities of our human. So the human error must be exceeded, and we want to really approach this theoretical optimal or Bayes error. One way to think about the ground truth, though, is when you sit down and you look at the data set and you want to try and think about it and evaluate it yourself, think about how was that target variable, how was it decided? So examples of human errors coming very close to the optimal error is if we have a group of experts looking at every sample. So you can't get much better than a group of experts, say a whole group of radiologists who then sit together and label every CT scan. That's as good as it gets. When it is a piece of apparatus that just makes a measurement, you want the best possible piece of equipment there, the best apparatus to record that target value. So think about when you see it makes a difference what the error rate is in your actual data set and what this theoretical optimal error is. It makes a difference. So how do we evaluate the result? Data is pre-processed, we've fed the data, we test it now against the validation or the test set. How do we know how good or bad it is? And there are two things we have to discuss here, and that is bias and variance. And these are, they're easy to understand, but there's some subtlety to bias and variance. Let's just quickly start with bias that we can see here. That's also called underfitting. And that is where the model does not separate two classes very well. So I want to just draw your attention to these little samples. They come from the scikit-learn website, and there's some Python code. You can just write it in Python and it'll produce these images, and I got them from writing that code from their website. Now I just want you to suspend there's a bit of a difference here between this and what happens in machine learning. So all this is these data points, and they fit this orange line, and that's the actual function. And because this apparatus that measured these data points is perhaps not that absolutely accurate, there's a bit of noise in that. But what we want to do now is just to align a model to this data. And if we have a degree 1 polynomial, that means a straight line that goes through this. So given any x input, what does it predict the y output going to be? There's going to be a lot of mistakes made here. So the straight line is a very poor fit. It underfits this data. Now, if we just move this slightly, just use your imagination, change this to a machine learning scenario. What this line will be what we call a decision boundary. And if we have lots of data points, the one side of this boundary will be predicted to be of the one class. So let's just imagine a binary target variable. And anything on the other side of this line will be predicted to be something else. And then you might have ones going on the wrong side of this line as far as the prediction is concerned. So that would be that model or boundary line would be a poor model neural network. But in this instance, where we're just fitting a line to data, it's also poor because it makes big errors. If I give an input value here, down here, there, the actual value is up there. There's a big difference between those two. It's a poor fit. Now we can make our machine learning model more complex, so we move away from a straight line decision boundary to something that's more curved. And in the instance that we've drawn here, there's a much better fit to the actual real world behind the scenes line, this orange one that was the true line. And this model, it's a very close fit. That was somehow the optimum. Now remember, that's what we're trying to achieve with machine learning. We never know what this orange line really is. But again, if this is a decision boundary, it's going to be, it curls around some of the data. So imagine again, suspend or use some imagination. So we see this graph in a different way, that there'll be points on either side of the line. And again, on one side and on the other side, they will be predicted as different classes. And if it sort of squirms around these data points on either side, that's a better decision boundary. But look at the right-hand side now. We've upped the degree of the polynomial so much that this equation, this blue line, which is an actual equation, actually goes through each and every, or almost each and every one of these points. And that is complete overfitting. So complete overfitting means that if you then see this blue line as a decision boundary, it's going to curl around the training set data points so well that it completely separates the two classes. But if you give it new data, that's way too convoluted. That overfits the training data, but it's going to be very poor when it comes to real-world data. We call that overfitting, or this model will have what we call a high variance. I actually started off by wanting to discuss bias, so let's get back to that. This is a bias problem that we have here, that there's a total underfitting. It really does not separate the classes very well. If this was the decision boundary, there isn't a good separation of the two. So you're going to make a lot of error there. So see bias on the one side, underfitting, and variance overfitting on the other side. This is also called memorization. So if you pass data to a model and it does very well in the training data, it might very well be just that it's just memorized. It's called as memorize the data, and it will perform very poorly on actual data. Now, how are we going to know when we deal with bias, underfitting, or high variance overfitting? Well, we're going to look at two things: the training set error and the validation set error. Now, if you think back to the preceding video, we had those two come out, the error, the two sets that went into the model, the whole set, but then the validation set that was split from that. So let's look at overfitting with a very low training set error. So that really indicates then there's a large difference between the error rates of the training and the validation set. So when you look at those lines that formed when we ran the model in RStudio, that the training set, that error just drops and drops and drops, and it becomes very small. But unlike the example, the contrived example that we had with the 50,000 data point samples, we might find that the error on the validation set, the green line, was much higher, much different. So imagine the error rate of the former being about 1% and the error rate in the latter being about 10%. That's high variance. So it's trained, it's overfitted, it's trained to the training set too well, and it doesn't work well on unseen data, the validation set. Now imagine there is poor error between both of these. So they both have in the order, the training set and the validation set are both here in the order of about 15 to 16%. Under the assumption that the error in the target variable was very low. So it was very accurate data that was fed to it. So just bear in mind that little assumption, because that's going to make a difference in a short while. So the difference between the two, the validation set and the training set, the error is very close to each other, and they are much higher than you would expect the error inside of the target variable itself. So this model is said to have high bias. So it's not even doing well on the training data that it's being given. And then we might get a scenario where both the variance and the bias is high, that is still assuming this very low human error or optimal error inside of the target variable, and then say a 15% error on the training set and a 30% error on the validation set. And that's going to give us both high variance and bias. So let's just think about this influence of the optimal error though. So if we moved, when we had 15 and 16% up here, we had both, the training and validation set errors being very high, but that was under the, and that gives us bias, that was under the assumption that there was no error in the target. You bring up the error in the target, say to 14%, that we know that there might be a misclassification in the data that we bring in, and we still sit with an error of 14 to 15%. That's actually a fantastic model with low bias and low variance, same error rate. So you've got to see this in context of what you think, as a domain expert, the error rate is in the target variable itself. In short though, this is what we're after. Look at, when you run the model, what the training set error is, and what the validation set error is, and what the difference between them are, keeping in mind what the baseline error, the ground truth error, might be. Just to mention, in older reports, older research documents, you might see this trade-off between bias and variance. You change your model, and if you change it, you go more in the one direction, and change it going to the other direction. But really, in a modern world where we have big data sets and where we have very sophisticated deep neural networks, that trade-off thing no longer is really the norm. You can get very low bias and very low variance in the same go. So if you get these errors, which you should understand, you can read this material again until really it becomes part of you, so that when you run these models, you know exactly what's happening. Just a few pointers as to what to do if you see high bias. So this model really underfits the training data. And ways that you can go about solving this problem is just the following. Write this down somewhere, and this will become part of you as you do more and more, create more and more networks. If you have this high bias, just create a bigger network. That means put in more layers, put in more nodes in every layer. That's just one way to go. If that doesn't work, just train for more epochs. It just might be that you haven't gone to the bottom of your gradient yet. So just train through more epochs. And then lastly, you can try a whole different architecture. So when the input was, for instance, images, don't do a normal deep neural network, try a convolutional neural network, for instance. And we'll get to designing and writing code for convolutional neural networks in the future. When you have high variance, large difference between the error rate of the training and validation sets, you can try the following possible solutions. Number one, capture more data. That is king. You can augment the data if you can't get your hands on more and there is this class imbalance. You can really think about augmenting your data for both those problems. And then the interesting stuff, because this we can manipulate in code, and that is implementing within the design of your neural network, implementing regularizations, dropouts, batch normalizations, and other techniques. And in the very next video, we're going to look at this very exciting concept of understanding regularization. So that was a bit quick. As I said, it's easy concepts to understand, but there's a lot of subtlety to it. Don't let these confuse you. I'm trying to depict two things here. One is just this fitting of this actual data, but I want you to use your imagination to also see these blue lines as a decision boundary, where it's going to predict a class on one or either side. Now remember, in higher dimensional space, it's not just going to be a line, but some hyperplane. But you can imagine it going from just a straight thing to something that is convoluted and curled all around. That's what we call the decision boundary. And that decision boundary can just become too complex, and you have this high variance on the side. It can also be totally not complex enough, and you have this high bias on this side. So you've got to sort of aim for this middle ground here. Read this document again. So there was no coding in this. So read this document. It is going to be available on our pubs, the actual file on GitHub. I'll put the links down below, and I'll speak to you in the next lecture. In this video, I want to talk to you about regularization. Now, we looked at this issue of high variance, where the model that we build is just way too specific to the training set, and it doesn't generalize well. And regularization is one of those ways in which we can tackle this problem. Now, when you start writing the code, it's just simple little additions that you make. It's a few characters that you type when you create this. So strictly speaking, this video is not necessary. You don't have to watch this, especially if you're not interested in the mathematics behind what is going on. I would advise, though, that you just listen to it with one ear, or at least just read the RPubs document or download it from GitHub and just read through it. As with the previous one, really to have the document in front of you and go through it a couple of times is perhaps better than listening to this video. So if you're interested in the mathematics, or at least some of the philosophy and lightly touching on the mathematics, watch this video. So the problem here is that we have high variance, that the model is just fitting our training data just too well. It's memorized that data, and we need to do something about it. The first concept I really want to talk to you about is the hypothesis space. And a way to look at the hypothesis space, one way to look at it, is just to look at all the possible solutions that our cost function can take by doing this gradient descent and getting these optimum values for the weights and biases, the parameters. And that all of those values together make up the hypothesis space. And one way to do it is just to try and constrain this hypothesis space so that not all the possible values are available to the model during this gradient descent process, this back forward and back propagation process. If we can limit that hypothesis space, then perhaps we can get to some values. They might not be the best, but they might, for the training data at least, but they might generalize better to the training set or real world data. And one way that we can go about this is to just consider this concept called complexity. So the hypothesis space is large. I mean, the more variables we have and the bigger our network is, just the more and more parameters we're going to have, and so many possible values to those. And if somewhere, if we can create a measure of complexity, if we have such a measure, then perhaps we can start cutting down on that complexity. And the way that it is done is just to take this hypothesis space and make a sequence out of it. And we're just using this double script notation here of the H, just denoting that that is a set, and the H1 hypothesis subspace 1 is contained within 2 is contained within this total 1 at the end here. So we just create the sequence so everyone is totally within the next one. So this is the big one, and then if you just take some of it and some of it and some of it, getting smaller and smaller and smaller, if we can create this, we can start thinking of putting a number or some value or something to this hypothesis space and deciding where we want to make the cutoff, so that anything beyond that is now not available as a solution, because that is perhaps where these solutions lie that are just too good for the training set and not so good for the rest. So let's look at ways that we can denote complexity. Can we wrap our head about one way of classifying complexity? Well, there's 4 for you here. And I'm just considering simple linear regression. We started this series off with that, but it really just expands naturally as I write here 2 parameters in neural networks. So one way to look at it is just to look at the dimensionality of the input space. How many feature variables you have. If you have fewer feature variables, you cut down on complexity. That is a measure of complexity. Now, that's not something that we can use here, and that's nothing to do with regularization. I just wanted to introduce this concept of complexity because I can now constrain this measure by only taking 4 of my possible 34 variables, feature variables, or I can take any number, but you can see that I have this sequence of complexity if this is my measure of complexity. 2 feature variables will be less complex than having 5, which is less complex than having 10, which is less complex than having 20. Another way is just to look at the number of my non-zero coefficients. So remember in linear regression we had, and then even in the feed forward, the forward propagation section, we take a weight times x sub 1 plus a weight times x sub 2. So all these weights, these parameters, they are coefficients. And if I take all the ones that are non-zero, I can count them up, and that can be a measure of complexity, and I can cut down by just throwing away some of these. And this measure of complexity, that's known as this script L sub 0, that's L sub 0 complexity. Another way to do it is just to take all these weights, my parameters, and just take all the absolute values, so make them all positive, and just add all of them, and if there's millions of them, just add millions, and that is called L1 complexity or lasso complexity. And then if I square each of them and then add all of them, that's called L2 complexity or ridge complexity. And that's the one that we're going to concentrate on here when we talk about regularization, because you get L1 and L2 regularization. But if you think about it, these measures of complexity, say we take number 4, that allows me to symbolize it. Let's call our symbol for the complexity based on this little equation as omega, and then therefore we can choose some element of omega, let's call it R, such that we can constrain the hypothesis space. So we're only going to look at stuff that is within this level of complexity, and it doesn't carry on here to the right hand side. And so now let's get to regularization, because we can set this R. Now it's not a value that we're going to set, it's just think of it as a concept. Somehow we're going to build a constraint into the system. Now there are 2 ways to go about it when we look at the cost function. Here's in 3, I'm just showing you the cost function again. This curly C is a function of all the weights and the biases. And remember, this cost function is just a function of all the predicted values and the actual values. So if it was linear regression, it's the difference between those squared, etc. But it is going to be some measure of error between what the predicted value was and what the actual value was, and we sum over all of those, and then we divide by how many there are. So that would be one. This idealized form, a generalized form, I should say, of the cost function. And the whole idea here is that we want to if we do this forward and back propagation all the time, we're going to get these idealized values of all the weights and biases, the parameters, but we want to constrain that somehow. And we can build something into this function that will constrain it. That's called an Ivanov type of constraint. But another way to go about it is called the Tikhonov regularization. And what we do there is we're going to add a term, as we can see here in function in equation 4. We're going to add this term. It looks horrendous, but we'll break it down. It's actually very, very simple. You know, when you see stuff like this, you think, wow, but it really is this very fancy writing for something that's very simple. We're going to have this lambda value. Now, lambda is a hyperparameter. That is something that you will have to actually decide on when you design your network. Divided by 2m. And what we just do is we take the square of something to do with the weights. You can see something to do with the weights. Now look at this, what's happening though, we are adding something to the cost function. So we're making the cost, remember, as a value in the end. We're just trying to make it more. We're increasing the cost. And when the backpropagation tries to, through gradient descent, tries to minimize this cost function, it actually has something added now to deal with. And one way that it's going to minimize this cost function is by making each of the weights, because you can well imagine that this is some matrix of all the weights, it's going to make the weights tend towards 0. If they tend towards 0, that makes the model simpler, less complex. If some of the values of W get closer and closer to 0, you can well imagine that, I mean, it's easy to imagine that we have a simpler, we knock out some of these weights, that it just becomes a simpler model. And if it's a simpler model, we have actually constrained the possible values that it could take. And the way that we did that was this Tikhonov regularization. We add a term to it. If we add a term plus, there's an addition here of a positive value, we're going to therefore force this gradient descent to select out smaller and smaller and smaller versions of all the parameters. Another thing that it actually does, if you think of the tan H function, when we do the activation, if we make it smaller, the weights closer to 0, we're going to be in this linear part of the tan H function. And if we do that, we almost have a linear model. And remember, a linear model gives us a much straighter decision boundary. And the decision boundaries that we discussed in the previous video gives us closer to that kind of model. And the end effect of these things, these thoughts, are that we are constraining the hypothesis space. Not all values are possible anymore, and that's where this R as an element of omega idea comes in, because I can set this lambda value up here when I write the code, and that is somehow going to, the larger I make it, obviously the bigger value I add to my cost function, thereby driving the value of W even less and less and less until they come closer to 0. And that is the thought behind this. So there is this Ivanov regularization where I actually build something into this function. Adding something is sort of a different idea, but they all sort of boils down to a similar thing. It's called, you can see down here, the Lagrangian duality theory. We're not going to discuss that, but it all boils down to the same thing. And specifically then, if we think about the ultimate goal here, and the ultimate goal is just to generalize the model, and whether you build something in there or whether you add another term, you're going to end up with the same thing. So this is done all the time in machine learning. This is called L2 regularization, because we use this form here. And if you look at it, just taking this part down here, let's break it up, it looks something like this. And you think, well, that looks even worse, doesn't it? But let me just show you what it's all about. Remember, in the forward propagation, we take the weight and we multiply it by the vector, the weight matrix times the vector of, this is the vector here of the column of the previous layer, and this x here, the L, refers to the current layer, L minus 1 is the previous layer. So to get the values inside of that layer, the previous layer, you take the weights of that layer and you multiply it by the previous layer's column vector. Watch those videos again. And to do that, just look at the weights or the dimensions at least. So after transposing, the weight matrix should actually be L times L minus 1. So that's the number of nodes in the current layer times the number of nodes in the previous layer. And remember, this is the previous layer has dimensions. It's a column vector of L minus 1 times 1. And if you multiply those out, you are going to get L times 1. So let's just look at W, and let's make W something that's 3 by 2. And there we have it, 3 rows, 2 columns. And what all of this does at the top of there is very simple. It just runs through each of the rows. So this column and this column through each of the rows. So it says 3 squared plus 4 squared, and then 2 squared plus 1 squared, and then 1 squared plus 1 squared, and you just add all of those and you get 32. It's as simple as that. This whole thing just means just square all the values. And that's ridge or L2 regularization. And that's all we're going to do. We just add this term which just squares all the values in the weight matrix and just adds all of the values. That's as simple as that. And if we think about taking the derivative now of this, if this function psi here is what we would have had without the regularization term, the derivative of this extra term is just this, very simple, and that's why we put the half in there. It's just a scaling factor, because if we bring the 2 forward during the derivation, it cancels out with the half that's there, so we're just left with lambda over m times actually the weights there. So if just bringing that forward, remember these are just additions, and if you think back at derivatives, if you just have a bunch of terms that are just added, you can just take the derivatives of each of those separately, and that's all that happens. So this term is actually very easy, and when we update the weights, it's just subtract from that the learning rate times this very simple derivative. So it doesn't add much to the computation, and in the end you're actually just going to write a line of code just to add the regularization to it. But I think now you would have a deeper understanding of what this regularization is. You can of course do L1 regularization, where you just add the absolute values there. We looked at it at the top here. There we would just add the absolute values of all of those. That would be L1 regularization. Here we have L2 regularization. You can see what it really is, very simple. And that's it. We're adding to the the cost function, thereby driving some of the weights to 0, making for a less complex system, and that really constrains this to only certain values of the weights, the parameters that we are trying to learn, only certain number of them being available. We're constraining the hypothesis space. So we're going to get worse performance on the training set, but that might generalize, and that's what we're after, generalizing better to the test set or real world data. So in short, that is regularization. The document will be available. Read through it. It'll make sense when you read through it a couple of times. It's actually very easy to understand. The calculations are very easy. And just eventually when we do write the line of the code in using TensorFlow or Keras, then with the TensorFlow backend in R, it is simple. So as long as you have some understanding of what is really happening behind the scenes, we're just trying to constrain the hypothesis space. I'll speak to you again. In this video, I want to continue our talk on what to do if we have this problem of overfitting, high variance. So that our model fits the training data very well, but when we look at the validation or test set or some real world data, we notice that that fit is very poor. And the method that we're going to talk about in this video is called dropout regularization. In short, I'm just going to refer to it as dropout, just so that we differentiate it from the term regularization, by which we usually mean L2 regularization, which we looked at in the preceding video and chapter. So what dropout does is just removes some of the nodes. Now it doesn't remove them, they're still there, but it creates a 0. So the value of that node becomes 0. And you can well imagine that if we have a couple of nodes in a layer become 0, that is very much the same thing that we achieve with L2 regularization, whereby we drive the value of those parameters to 0, giving us, during the multiplication stage, giving us values close to 0 for those nodes. So how it actually works is, well, there are different ways, but the normal is just to use what is called inverted dropout. So what inverted dropout does is it looks at a layer, and a layer contains a number of nodes. We can see there a layer of nodes, and some of them are just going to be chosen to be 0. And how does that work? Well, we create a vector of the similar number of elements. Here we have 1, 2, 3, 4, 5. So we would create a vector of 5 elements. And each of them will receive a random value in this domain from 0 to 1 inclusive. And we set this value, say 0.2. And if that random value is less than 0.2, we turn that value in the vector into a 0. And if it's 0.2 or more, it'll become a 1. So we'll have this vector of 0s and 1s with that just be random. And then we have element-wise multiplication. Therefore, some of the values that remain in that layer after activation, remember this happens after activation, that is going to be either the actual value or a 0. The actual value or a 0. So we have these zeros in there. Now we actually, when this all happens during randomizing those values, we actually subtract that value that we decide on the 0.2 as our cutoff. We subtract that from 1, and that gives us an 0.8. And that is what we refer to as our keep probability value. You see the keep probability. And in essence, then you can think that is what happens. We're going to keep 80% of these at random, and 20% are going to drop out. So our keep probability rate, if we set 0.2, would be 0.8. If it was 0.3, it'll be 0.7. And I'm just going to refer to that as a kappa value. Our keep probability value is 0.8. Now with the inverted dropout, there's actually one more step. Now remember, when we do this feed forward, when we do the forward propagation, we're going to multiply our matrix of coefficient of parameters with this column vector x of the previous layer, and we add all of those once the multiplication takes place to give us this value. But some of them during this addition is now going to be 0, and imagine we use a rectified linear unit activation for this node. It is now going to be smaller than it would have been before, because during all of those additions from each of these inputs, some of them are now going to be 0. And we have to compensate for that somehow. And the way that we compensate for that, it's each of these values that come in, or each of these values that we now have after this multiplication gets divided by the kappa value. That's very important. We divide all of them by the kappa value, so that when we do add, before we do our rectified linear unit activation, for instance, that we are on a similar scale that we would have been should we not have had 0. It is a very important step, and if we write the code, that's actually going to happen automatically. But I think it's important just to realize that we have a scaling problem whereby the node is going to be different, the value is going to be different for the activation. So we divide these values by kappa. And the effect of all of this is that we might have some of these nodes starting to overwhelm the system. They become more important. And they become more important during the training phase, and then that fits the training data very well. But it's a falsehood, and we want to try and prevent that. So there's this random chance of removing some of these. And as you can imagine, then once again we constrain the hypothesis space, and thereby we create this model, a simpler model, which might then fit our test or validation or real-world data a lot better. So in very short, that is dropout. Those are just the key thoughts on dropout. So just understand what is happening. We are just going to create some of these values to be 0. The technicalities of that you needn't be too concerned about. Simple addition to our code. And very excitingly, in the next video, I'm going to show you how to implement L2 regularization as well as dropout, and we're going to see how that affects the data and how that's going to try and fix the problem of overfitting that exists in the data set that we are going to use. Now, we've looked in the two preceding videos, we looked at regularization and dropout regularization as methods to tackle this problem of overfitting. So, whereas those two videos really were not absolutely necessary to watch, you could just read the documents that are on RPubs or download them from GitHub and get a sense of what we're trying to achieve here. This is the important video. We're actually going to write the code and we're going to implement L2 regularization and also dropout. So I'm not going to do this in the RPubs document during this recording. We're going to use RStudio here just so that I can also use the opportunity to show you one or two things in RStudio. So here we go. This is the document. You can download it from GitHub or just view it on RPubs as I mentioned. So our YAML up there just to show that this is going to be an HTML document, that we don't want numbered sections and that we want a table of contents. You can always just copy those. My first cell here, which won't be included in the document, so we have this include equals false statement here, and I also have a name. Now this is automatic, remember you can always put names, and what we're going to do is just put a bunch of names to each of the code chunks, and if you go to the bottom here you can actually see all the names there, which allows you to quickly find where you want to go in the document. That is very helpful. So let's run this first just to set things up. And these are the libraries we're going to use. Keras, obviously, we're going to use Reader, Tidier, Tibble, and Plotly. Let's run those. And we've got some cascading style sheets as well. Now, one thing I wanted you just to notice here, just a quick sidetrack, we get these warning messages. One way to get rid of them is if we are in a code chunk like this, go to this little gear icon there and show warnings and show messages. You can click those so they're off. See, the green disappeared, and then this code appears here. Message equals false, warning equals false. So you can either type that in, or you can just do it from this little gear icon, hit apply, and then when you run it, those messages won't appear. We've got the cascading style sheets there, so that's a bit of a side issue. Let's get to actually implementing regularization and dropout. So we're going to do some sentiment analysis. That's very exciting. That's a kind of data that we haven't looked at before. So in Keras we can import this data set. It contains 50,000 pieces of text. So someone wrote a piece of text and it was about just reviewing a movie database. Or movies at least. So you write a piece of text. So the only input is this text, and some wrote long paragraphs, some only wrote sentences. So how do you convert that into something that's computable? So as I mentioned, there's these 50,000 examples. They are labeled, and they are labeled as either positive or negative towards that movie. So we have the sentiment, positive and negative, and they were encoded as integers 0 and 1. So the way to do that is by looking at each of the specific words. And I'm going to get into that by showing you in the code what it means. It's called multi-hot encoding. So we've looked at one hot encoding. We're now going to take the feature variables and multi-hot encode them. Very exciting stuff. And I'm not going to say too much about it now. I'm going to show you what it looks like, and then it'll make much more sense. Now, the data set that we are going to import from Keras is not a normal spreadsheet. It actually imports quite a few things, and one of the things that it imports is, behind the scenes, is just this enormous list of words. And it's a list of words that occur very commonly, and up to a list of words that don't occur so commonly. So we can set how many of those words, and there are quite a few of them. We're going to set a limit of 5,000. So we're also just going to import this list of 5,000 words, and what's going to happen is we're going to create 5,000 variables. So in our feature set is going to contain 5,000 variables where each of the variables is just one word. And you can almost guess at what the multi-hot encoding is going to be about. So let's import this with the number words argument set to 5000. And we're going to save that as IMDb. It's going to take just a little bit of time to download. There we go. And now we're going to use this $train and $test that's part of this IMDb that was imported. And we're going to create this training data and training labels and test data and test labels, these 4 objects. And they're each going to contain, at least the train and the test set, they're going to contain 25,000 subjects each. And that is wrong. I mean, we never in real life, please don't split things 50-50. We've discussed this in large data sets like this. We might have only used 10% as our test set, but this is built into this data set. So we're going to go with the flow and we're going to create these 4 computer variables. Train data and train labels, and test data and test set. Now we're going to use multi-hot encoding. Now, as before, remember we did that for the target variable. That's not what we're doing here. We're doing the one-hot encoding. We're doing multi-hot encoding on the training and the test set, the feature variables. Now, with the one-hot encoding, there was this 2-categorical function inside of Keras, but there isn't a similar one. So we have to write one. I'm not going to go into this. This is a bit of scary R code here. You can copy and paste this and always use this. Perhaps later when we talk about R again, we might go through what these 4 loops are doing and what the addressing is doing, etc. It's not very difficult when you read this. It's almost like reading English. You'll figure out what it does. And what we're going to do is we're going to take the training data and the test data. Remember, those are just sentences, paragraphs, and we're going to turn them into multi-hot encoding across 5,000 variables. So we're going to, in the end, have this spreadsheet that contains 5,000 columns. So let's run that. And that is both for the training data and the test data. So we pass that to this multi-hot sequence. And we saw when we created this function, we had 2 arguments. The second argument was the number of dimensions, which are 5,000. Now what I'm going to do is just to show you the first one and only the first 10. So I'm using addressing here for test data. So we're going to take this data, which has 5,000 columns and 25,000 rows. I'm only going to show you row number 1 and columns 1 to 10, just to show you what the multi-hot encoding does. So there we go, only the first 10 of the 5,000. And we see here that word number 1 did occur in that first subject's review. So that text that that first subject wrote, it's going to look for, in that text, 5,000 words. And if that word occurs in that text, it gets a 1. So word number 1, we don't know what these words are, and it doesn't matter. Word number 1, word number 2 was there. Word number 3 did not occur in this person's review. And word number 4, 5, 10, they all occurred, and then we'll have 0 and 1s up till 5,000 of them. And if you think about that, that is a very clever way of converting something that is just text of different lengths and different whatever, paragraphs, etc. Turn that into data that is computable. That's a very clever way of going about it. Now let's create a baseline model. It's going to be a densely connected model. Let's have a look at it. Once again, I'm using a name here, baseline model here. And as I said, when you go down here, you can actually find there's baseline model. Because it was 2 hashtags, it's actually a level 2 heading there, and I can find baseline model chunk there, and it'll actually jump to this. Now again, that's a bit of RStudio information there for you. Let's create this. I'm going to call it baseline underscore model. It's going to be a Keras sequential model, and we use the pipe symbol again. Remember to pass this Keras sequential model as first argument, which is supposed to go right there. And we can to layer these one inside of the other. So the first one anyway is a dense layer. It has 16 nodes. We're going to use the ReLU activation function, rectified linear unit activation function. And for the first layer, remember we have to tell it what shape, what the input shape is, and that's a 5,000 element vector. And remember, I'm just using numwords here because I saved numwords up in the code as a value, as an object with a value of 5,000. So you've got to put the input shape there. Then a second densely connected layer also with 16 nodes, ReLU, and then we're going to have another dense layer with only a single unit, and its activation is going to be the logistic sigmoid function, so just sigmoid. And that, remember, the sigmoid function, that gives us a value between 0 and 1, and it'll automatically have this split at 0.5, so a value of less than 0.5 will be coded as an output, a y hat output as 0, and 0.5 up till 1 will be a 1. And that's different from the one-hot encoding we showed before. So this is a different way of going about it. If you only have a binary output 0 and 1, 0 and 1, 0 and 1, if that's your target, you needn't do the one-hot encoding as we did before. I showed you that because that's very common to use, because in many instances we're not only going to have two values, we're going to have a target sample space which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 10 of them, 20 of them, 1,000 of them. And then that makes one-hot encoding very useful. So in most circumstances, use one-hot encoding. This is a very special case where we only have a binary output and we're going to have a sigmoid output. We're going to compile our model then. I'm going to use the Adam optimizer, and my loss function is going to be binary cross entropy. We're going to cover this in future lessons. So Adam and binary cross entropy, my metric again is going to be accuracy. And then I'm using a pipe here to just load baseline model as the first argument in the summary function. So I could also just have written, remember, summary and then baseline function, just to show you a different way of doing it. There we go. And there we go. We see we have 80,305 parameters that have to be learned. So now let's go through and fit the data that we have. So we have baseline model there, we fit to that the train data and the train labels. We're going to run through 20 epochs. Batch size, we're going to cover that in future, 512. And as my validation data, I'm passing a list, which is the test data and the test labels. We've spoken about this before, if you watch the previous lectures, that you can use your test data as validation. And verbosity we're going to set as 2, so that we get both our training and test data. The training and test data, we're going to get the loss and accuracy for both. And that's why the verbosity, the verbose, is set as 2. Once again, you can see message equals false and warning equals false. If I type that in, but I could also go in the little gear and you can see that they are not selected. So this is going to take a bit of time. Let's run it. And there we go. It starts as the noise outside with the neuroscience center being built just gets to a crescendo. It really is maddening to be in this office, and I spend as little time here as possible because of all that noise. We see that there is a problem here. We can see in blue the loss of the training data coming down, down, down. But look at the loss of our test data, our validation set going up, up, up. There's this huge difference between the two. And if we look at the accuracy, whereas the accuracy of the training data keeps going up, we see that the validation or test set, that accuracy is really performing poorly. So there's this huge discrepancy between the training and the validation set there. In other words, we have high variance. We have overfitting. It's overfitting here because it is really, the accuracy is really good, going towards 99%, 98% there in the end, with a very small loss of 0.0583. So that's very close to what we would think of this baseline ground truth. So that's overfitting here with a very high variance. And if we look at that, we see I'm not running this on a GPU. This is a Core i7 Intel CPU, and it takes about 2 seconds here for each of the epochs to run. So it takes quite a bit of time. Now let's simplify this model, because that's one way to go about it. Let's simplify this model. So instead of 16 nodes in each, we're just going to keep everything the same, but we're going to only have 4 nodes. So there's not a lot of capacity here to learn from the data. Let's see what that does. Going to create that model, and then let's fit the data exactly the same as we did before. And as the model runs, we can see we have a similar problem in that we still have this issue of high variance with the overfitting of our training data. Now let's just make things a lot worse, and I'm going to create an enormous, well, let's say relatively enormous model here, and I'm going to have 512 512 nodes. Now remember, my input space was a vector of 5,000, so 512 perhaps not that big, but let's put 512 nodes in each of our layers and let's see what happens. So let's create that model and let's run it. And there we go. We can see there's an even bigger problem here. Because this network had a large capacity to learn, it really learned the training data very well, but performed very, very poorly on our validation set. Let's scroll down. And what I'm going to do here is just use Plotly, and here in figure 1, I'm just going to plot the comparison of what we've done before. We've had our baseline, our small and our bigger model. Let's have a look at this. I'm just going to create a data frame in the code up here. We might have a look at this in future lectures if we just look at R a bit closer, if we have time for that. So there we go. I'm just creating a bit of a data frame, and then I'm using Plotly. I do have a few separate lectures on YouTube on using Plotly and R, and let's just run this code because that's what is more important. We saw all of this happening in our studio on the right hand side here, but let's have a look here at figure 1. I like Plotly because it's interactive. I can zoom, I can save this as a PNG file separately right from here, etc. And as I hover over it, we can see what is happening. So look at our bigger train here at the bottom, doing very well. We see on the y-axis we have the epochs, on the x-axis we have the loss as I specified here in the code. And there's our bigger train, and let's look at our bigger, where is our bigger loss, bigger validation. There we go. So bigger train and bigger validation. Look at that large or very high variance that we have there. If we look here at baseline train and baseline, there we go, baseline validation. So that's this green and the orange one up there, still a big difference. And we look at the smaller one, it didn't perform as well, obviously, on the training set, but we constrained the hypothesis, so it's doing better on the real world or test data than the other two. You see the smaller difference there. So a very nice graphical representation of this idea of a very high variance, overfitting, and then how we constrain the hypothesis space, which is actually getting better with a baseline and getting even better with a smaller model. Let's now move over to L2 regularization. And straight off the bat, let me show you what's going on here. We're going to put 16 units in each of our two hidden layers, so that's staying the same in our output, just being 1 and the activation being the logistic sigmoid function. And what we're doing here is we are adding kernel regularizer as a keyword argument here, and we're doing regularizer L2. So L2 regularization, and we're passing a value of lambda of here of 0.01. So we use it as an argument inside of that layer, as simple as that. Everything else is staying exactly the same. There we go. And let's run this model and let's see what happens. Okay, so we can see that we still have some overfitting going on here, but certainly is not as bad as we've seen before. And in the end, we'll do another Plotly graph and we'll see the difference. Now that is implementing regularization. Oh, yeah, we've got it. Let's do the baseline, which is compare the baseline and regularization in a plot here. Let's have a look at that. And if we look at that, there was our baseline training, and up here was our baseline validation. And we can see the regularization training and the testing much closer to each other than the baseline. So we made some improvement. Let's do some dropout. Now in the code here, whereas we use dropout or regularization at least as an argument, the dropout here, we're actually going to use a dropout layer. So we're going to, there are different ways of doing this in Keras and in TensorFlow, but here we're just going to add them as a separate layer. I want to show you different ways of doing it. So layer dense, it's going to have 16 activation value. Our input shape is still going to be that vector of 5,000 elements. Then a dropout layer set at 0.6, another 16 unit, another dropout of 0.6, sigmoid, everything else stays exactly the same. So note that we use the pipe and we feed that to the next layer, and it's a layer, we had layer dense and then layer dropout, layer dense and layer dropout. So that is how we introduce this idea of dropout to the model. Let's run this model and see what it does. Okay, so there we go. We see another improvement as we look on the right-hand side here. Let's go down and just compare that to the baseline with our Plotly code here. And there we go. Look at this difference. So here we have the baseline again, and then here we have the dropout training and the dropout validation. So let's just compare the whole lot to each other. Let's just have a look at this. Just plotting the regularization versus dropout in this instance. And there we go. We see the L2 train and L2 validation at the top, and in the middle here we see the dropout train and the dropout validation. So in this instance, dropout helped us quite a bit. It was quite a bit better than regularization. Now that's by no means the norm. These are hyperparameters, both in the design. I mean, we had 2 layers, we had different number of nodes. We could have had 3 layers, 4 layers, etc. Different parameters we could have chosen for our dropout, different for our regularization. These hyperparameters, what we used here and the improvement that we saw here, that was specific to this data. If you use other data, it's not going to look the same. The dropout is not going to necessarily be better than the regularization. These hyperparameters you have to sit with, you have to play with over and over and over again. That is unfortunately the way deep neural networks work. You have to work at it. It's time consuming. If your models are large and they run over many hours, you really have to look at multi-GPU systems just to maintain your sanity, because you want it to run as quickly as possible. So that in short was how to implement regularization and dropout. It's very easy to do, and use your data sets. Try and implement these to download this code and do exactly this, but try to use your own code as well. Perhaps in the future I'll just show you how to create a bit of your own code and how to introduce your own code. And that's it for regularization and dropout. In this video, I really want to discuss very briefly some improvement techniques in the training phase of neural networks, as you set it up just to improve training. We have this problem that when you do training, that it is a very empirical process. We're not talking about inferential statistics where we have well-defined equations and tests. It is also iterative. You have to run a model, see what happens, and look at the results, and then change things. And you have to repeat this over and over again. And for very good training, you also need very big data sets. So all of this really, it takes a toll on your computer resources and your time. And we have to look at things that we can do just to improve this learning process. So in this video, I'm going to mention a few things. I would rather you read the document that's available on our pubs that we are looking at now, or download the RMD file from GitHub and have a look at it yourself. There is some mathematics in it. I've kept it very, very easy, and I'd rather just mention a few concepts so that when we do get to the code, you understand it, at least have some intuitive feel for what is happening and why we are using it. So one of the first things that we want to do when we bring the data in is to what is called normalize the input features. We can also call it standardize. There's different forms of scaling of the input. But imagine you have a number of feature variables and they're all at very different scales. Some might be just fractions. Some might have data point values that are in the thousands. Those are very different scales. And that is going to perhaps lead to a multi-dimensional gradient that we're looking at, a cost function, that is in some way very elongated in some directions as opposed to others. And what you want to do is just bunch those all up so that they're all within sort of the same scale. So one way to do would just be to normalize it. This actually standardization, standardize it. So you calculate the mean and the standard deviation for each of your feature variables. And then you go feature variable for feature variable, data point value for data point value, that's what the x sub I is, subtract from that the mean for that variable and divide it by the standard deviation of that variable. So that's a very common thing to do when we start looking at images, for instance, and if the image is made up of pixels and the pixel is just some brightness value from 0 to 255. We can just divide every value by 255. That's the maximum. So that would be another way of scaling. But this is one of the common ways of scaling, just standardized. So you can imagine if you do that, you're going to end up with that variable having a mean of 0 and a standard deviation of 1. That's why we call it a standardization. There's an important thing that you have to note, though, is when you split up your training and your test sets, you calculate the standard deviation and the mean for the training set. That's what you do. And then you use that very same mean and standard deviation on the test set. So don't do the mean and standard deviation on the whole data set, and don't take the test set and do its mean and standard deviation for its normalization. You use the parameters from the training set, and you also apply those same parameters to the test set. That's a very important point, and sometimes that gets missed. Another thing I just want to mention is just vanishing and exploding gradients. So just imagine, you can all think about fractions. If I take a half and I multiply it by 2/3, these are commutative. It's multiplication with real values. I can switch those two around, but in any way, I'm going to get a third. Or a quarter times 9/10 is 9/40. And if you think about it, if I have these AB times A over B times C over D, I'm going to get AC over BD. And if I put some constraints on this, so that A is always smaller than B, so that's always going to be some fraction less than 1. C and D is also going to be some fraction. And I make AB, C, and D, they're all positive integers. So those are my constraints. If I do this multiplication, what we're always going to find is that A over B is going to be less than or greater than AC over BD, and CD is also going to be bigger. So what I'm just trying to say is this value here is always going to get smaller and smaller and smaller. And if you think about what we do with the weights, just forget the biases at the moment. We start with this weight matrix times the input vector. That gives us something, and it goes through an activation function, addition, all of that. And then I take the weight 2 and I multiply it by these two, and so on and so on and so on. And what you can see with these weights, if they're all very tiny between 0 and 1, what is going to happen, it is going to get smaller and smaller and smaller, and that is what we call the vanishing gradient problem. So these weights, they are just going to get smaller and smaller, and the derivative smaller and smaller, and you get that it vanishes. What you could also get for the same argument as we used before here, if these are all more than 1, this is just going to get bigger and bigger and bigger if both of these values are more than 1, and then you get the exploding gradient problem. So for the same argument, you're going to get that, and then the similar arguments hold for the backpropagation step, of course, with updates. The whole system just means that you get this either vanishing gradient problem or the exploding gradient problem. And one way that we can mitigate that is this: when we set up our problem, we can initialize our weight values. Remember, if we start a neural network, those initial weights for that first multiplication, those are just random values. We can normalize that, and what we do is we set the variance of the weight matrix to the reciprocal of the number of input nodes, which is to be multiplied by that matrix. You can read that sentence. It's not that difficult. And just a little caveat is that if we use the ReLU, we divide by, or we use 2 over n instead of n. So what we do is we take that n is the number of nodes, and that we are going to be multiplied with in that layer, and we just multiply each value in the matrix by this. For ReLU it's 2 over n, for the others it's just 1 over n. And for tanh functions, that used to be called Xavier initialization. So that just means what you do is you just calculate the variance of the matrix, or set the variance of the matrix. And you do that just by multiplying each of the elements. If it's ReLU, you multiply by 2 over n, where n is the number of nodes in that layer that you're going to work with. And for the others, it's just 1 over n. And that is just something we can set in code. The next thing I just want to mention is mini-batch gradient descent. So if you think about an epoch, before you take any step in any of the directions in your cost function to go down the gradient, you are going to have to work through all of the values. And if we have very big data sets of millions of samples, Now that's going to take a lot of computation before you can take one tiny little step. So there was this invention of what is called a mini batch gradient descent, where you break up your data set, all the rows, into little sections called mini batches. And instead of using the whole data set when you do your forward propagation and back propagation step to update your weights and your biases, you don't do that on the whole data set, you just do that on a small batch. And then the next batch and the next batch and the next batch. And in each of those, of course, you take a little step. So running through one epoch, which means going through the whole data set, you've already taken many steps before you get to the end of that data set. And we call this mini batch gradient descent because you create these little mini batches. But when we write code, usually it's just referred to as batch size. But in reality, if you do batch gradient descent, it refers to using the whole data set. And when you use sections of it, it's called mini batch. But in code, we set the batch size, which refers to the mini batch. The extreme of this is a mini batch of 1. So every example, you're going to get a y predicted. You do your cost function, and you update through every sample. That's called stochastic gradient descent. And you can well imagine that's, if you have 1 million rows of data, that's going to take 1 million little steps through one epoch. And it's just going to wander around almost aimlessly. It's not aimless, but it's going to wander around quite a bit. And there's ways that we can mitigate that. So the usual thing is to go somewhere in between. And we set these mini batch sizes to be powers of 2. It's usually here in the range of 128, 256, 512. And that works very well with the memory architecture of many systems. What you need to do, though, is, depending on the type of data that you have, is that these batches fit within the memory capacity of your CPU or GPU. If that is so, if you can set these batch sizes so that it just maximizes that potential of the memory of your CPU or GPU, it has to fit in there, otherwise you can't run it. So that's the idea behind mini batch gradient descent. Then there's gradient descent with momentum. Somehow what we're trying to do is we just want to speed up the gradient descent in the eventual direction which it needs to go. And this is quite technical. The idea behind this, and if we scroll down, we're going to get to root mean square RMS prop, is that we use something called the exponentially weighted moving average. This is something I just want to stop at and just try and explain very quickly. Imagine you have a set of data points. It's very easy to calculate the mean. But you can also have a moving mean, a moving average. In other words, you start at the first value, imagine it's 10, and its average is just 10. You go on to the second one, and the second one might be 20, so now the average between those is 15. The next one might be 17, and the average between 17 and the previous 15 is 16. So you can have this moving average as you go through the values. So that's one way. What you could also do is to weight some of the previous ones so they don't all count equally towards what the current mean is as you run through all the numbers. You can weight them. And a very good way is to exponentially weight them so that the ones that are just prior to the one that you're calculating at the moment, where you are at the moment, counts more than ones further down the line, further back in time. And that's called exponentially weighted moving average. And that's the idea that we do here with momentum. So we're somehow going to keep track of the weights, and we're going to average over the last couple of weights, but the further back in your gradient descent the weight values go, the less they contribute to the current average. So we can use averages for the mean, for the weights, and not the actual weight that you're doing during that gradient descent step. You actually do an average over the last couple, and somehow you retain some of them so that you move forward quicker. And that's called momentum. So yeah, I just have some data point values. You can see that, you can look at the code there. It's very easy to set up some code X and Y, and we're just going to add some random noise to this, and it's in the form of a sine function with some random noise, and you can actually see the actual sine function value there. It's plus added to 1. Every value is plus 1, so it starts at 1, not at 0 as the normal sine function. But you see this, and if we add a moving average, exponentially weighted moving average, and you can look at the code to do that, you actually see this green line, which takes these data points from left to right as it goes, and it calculates a moving average, but it does the exponentially weighted moving average. So of course it's going to start at 0 because at that first step you have no average, because at the first step that you take there's nothing that came before, so you start at 0. So it takes some time, but you see that it always lags behind the true value, which in this instance is just the sine function. It's always going to lag a little bit behind, and that's what you want. And that's the equation there for it. So that the moving average is you take some beta value, some fraction, and you multiply it by the previous moving average that you had, plus 1 minus beta times the current value that you are at. And by setting beta, these updates can be much more ragged up and down, as it pays much more attention just to the previous ones, and the decay is a very quick decay back. And you can play with this value. Usually we set it at about 0.9. And you can play with this code as well. Just put in different values here for beta, and you'll see this green line differ quite dramatically. And when you expand this and we just approximate a little bit, what we can see here is that the number of previous data points over which the average is computed is approximately given by 1 over 1 minus beta I, and that I is whatever step you are at, how many you've included up until that point. So what we do with a momentum is we take these updates in the weight, so that's the gradient according to that specific weight, the partial derivative for that specific weight. And we keep tabs of it as we run through all the gradient descents. And the same thing, we're going to get this beta value between 0 and 1. And so we look at what the previous average was, and we add that to 1 minus the current partial derivative, and that gives us a new value. And that's what we're going to plug in when we do the update of the weights. Another way to go about it is RMS prop, and what we do is almost exactly the same, other than the fact that we just square this partial derivative in the end. And when we do the update is we take the partial derivative and we divide it by the square root of this value that we calculated up here. So a very simple actual concept. What is very powerful is to combine this idea of momentum and RMS prop. And when we combine them, it is called ADAM, and we've used ADAM before. That stands for Adaptive Moment Estimation. Adaptive, ADA, moment M, and then there's no E for the estimation, but it's ADAM. And we just combine these two. One thing I just want to show you is there's a way to get rid of this initial having to catch up, and that is no matter what you use, if you use this equation, the V equation here, or the S equation here for the different two, no matter which one you use, I've just used the row here to indicate it's either one of those. You take it and you correct it by dividing by 1 minus beta to the power t. And t is whatever step you are at now, so wherever you are, we used I before, but whatever step you are from left to right. If you plug it in there, as t gets larger, this is a fraction, this disappears, it approaches 0, so you're just dividing by 1. So the further along you go, it will have negligible effect and will end up with a green line, but initially it will move this one way up and it'll start at a much more appropriate spot. So we do correct this. And then what we do is we just combine this. So the update is going to be the V corrected from the momentum and the S corrected from the RMS prop. And we divide those two, and that becomes what we multiply the learning rate by. So we've got two hyperparameters that we can set. There are defaults, of course. And the defaults is, or what most people would use, is 0.9 and 0.999. You have to look at the current documentation to see what the defaults are, but you can set them when you use ADAM. The next concept is just learning rate decay. And we always set alpha just to be 0.001 or 0.003. But what you want to do is initially you can have a large learning rate, but as you move along, you make it smaller and smaller so that when you get to the theoretical minimum, that you don't overshoot. That means in the end, you're going to take smaller steps as you approach this minimum, but at least you don't overshoot. And that initially at least speeds up the learning, but then doesn't overshoot. It doesn't keep these big steps that you take And there's various ways to go about it. You can see one equation there, but there are many types. There's exponential decay, there's staircase decay, there's all sorts of decay. And the best way that we're going to look at it is just to use it as we do the code with all of these. We can start using them, but at least you've heard of them before and you have some idea of what is happening. That's all I'm trying to do. The last way to try and improve your learning is just called batch normalization. Just as we normalized or standardized our input values, our input variables, we can also normalize the weights that we are going to use at each deep or hidden layer. And what we do is we just normalize the values in the nodes, and those are the values before the activation function kicks in. So you're going to do all your multiplications, your weight matrix times your vector of the input values, and then you're going to normalize them and then apply the activation function to each of those values for each of the nodes. And you can see what happens there. There's also a way to write this value, this updated value before the activation takes place. Just to mention, you can also do it after activation. There's some papers on that as well. You can do that as well. But is to take this and to add parameters to it so that you get this z that I've written here with a tilde, and have these two parameters which are learnable parameters. And we'll see how to set that in the future video as we make use of batch normalization. So these are not hyperparameters, but they're learnable parameters. And we can use those very effectively just to try and set these values before the activation kicks in, and optimize those values. And that really helps gradient descent as well. So we're really trying just to improve on the computer resource consumption and our time consumption by implementing these. And as I've mentioned before now, we are going to start using them in the very next video. I'm going to show you some of these. And as you start using them, just refer back to this very simplified version of it. Of course, you can read the original papers about all of these if you're interested in the mathematics, but as long as you have some understanding of what we're trying to achieve here, that is fine. As you start using the code and you see the effect that these things have, that's the important part. So in the next video, we're going to start looking at implementing some of these. So in the previous video, we looked at a few ways just to improve training, a few concepts. You can still read the RPOPs documents, download the RMD file from GitHub, have a look at those. What I want to do in this video is just to show you how we can implement at least a few of those improvements that we saw in that video. I'm also going to introduce you to a package called tfruns. Let's just move down here. And we can see the tfruns. Install it via your package manager, and it is going to help us to look at the effect of changes that we make to our model. Now this demonstration, I'm going to use just a normal R script. So that would be file, new, and then we see R script here. Just an R script. And there are two files here. You see the file that I'm working in, but there's a second file that just contains the model. It should be familiar to you. There's our Keras model sequential. We compile our model and then we fit the model. So that's all that is in the second file, just the actual model. Look, we're not even importing Keras here or TensorFlow or anything. This is just the model in the second file. So let's go back to the first file and let's get things started. First line of code, I'm just going to set my working directory, and I'm just going to hold down Control and hit Enter, or Command and hit Enter on a Mac, and that just executes that line of code, and we can see at the bottom here in the console that line of code has been executed. So my files, both of them, live inside of this folder or this directory, and now it's easy just to reference the files that are in there. I'm going to import Keras and import the reader packages. Reader, remember just to read a CSV file. Keras, because we need to do some machine learning. Now the training and the test sets for this example exist in two separate spreadsheet files, comma separated value files. So they've already been split, and I'm using the computer variables train.import and test.import to hold those two CSV objects. Read _CSV, not .csv, because this comes from the reader package. So let's do that. Control Enter, and the second one, Control Enter, and we'll see we have two imports here: test import, train import. That's what I called them, and you can click on those two buttons and you can see. We notice that there are 27,020 observations over 13 variables in the training set, and then in the test set there's 2,943 observations across the same 13 variables. As per usual, I want to change these into matrices. So I'm going to say train.import, and that's going to be as matrix, the train import. Let's do that. And then I remove the names. They were column headers, and I'm going to remove them, and I'm doing the same for test import, and I remove the column headers. So I'm left with these two matrices. What I want to do now is to create my train and test data, and for columns 1 to 12, that was the feature variable, and the target variable is in column 13. Remember, it's row comma columns, square brackets indicating that I'm using indexing. So I'm creating two train and two test sets here, that two of each, a train data and a train labels, I should say, and a test data and a test labels, just to hold the features and then the target variables separately. So I'm going to execute all four of those. Now remember, in the previous video we spoke about now just normalizing those, and the way that we're going to normalize in this video is take the mean and standard deviation of each of the feature variables, so each of those 12 columns. And what we're going to do, that's for the training set, remember, we're going to, for each value, subtract its mean and divide by its standard deviation for that variable. So I'm going to create this empty variable, this empty vector. I'm going to call it feature.means. It's a vector, and it has a length of the number of columns in my training data, which was 12. So it's this empty vector of 12 spaces. Control Command Enter, and we can see it here, feature measure. It's just 1 to 12, and it's all false, false, false. It's just this empty vector of 12 values. Now what I want to do is I'm going to iterate through each of the columns. So for a for loop, I in 1 to the length of the feature means, remember there are 12 of them, so I'm going to iterate from 1 to 12. And I'm going to start populating feature means. Remember there are 12 empty spaces, so during the first loop, that will be spot number 1, will be the mean of my training data's all the rows in column 1. So I'm looking down column 1, I'm calculating the mean, and I'm putting that in position 1 in my features mean. Then it'll be 2, so it'll look at column 2 in train data, get its mean, and place it in position number 2. And so until we get to 12, and then we see here, we have feature means up here. It's 12 numbers 1 to 12 in the indexing, and it's the mean of each of the columns. And I'm going to do exactly the same for the standard deviation. So standard deviation, and run my for loop as well. So I've got 12 means and 12 standard deviations. Because what I want to do now is to create this normalized feature set. So first of all, I'm going to create an empty matrix that's going to be the same number of rows and columns. Remember, it was quite a lot when we first imported it. It was 27,020, so rows over 12 columns. I'm creating this empty matrix to hold that. And then I'm going to do two for loops, a nested for loop. So on the outside for loops, I'm going to go through all the columns. And in the inside for loop, I'm going to go through all the rows. So what I'm doing with this, I'm going to populate all of these empty values in this matrix. And I'm going to start with row 1, column 1, and that is going to be that position, train data. Subtract from that the feature mean divided by the feature standard deviation. So the n refers to those columns. So I'm going to go down each and every step, each and every row in the first column, each one of those sample data point values, and I subtract from that the mean for that column or variable, divided by the standard deviation for that column or variable. And once I'm done through all of the first columns, all of its rows, I come outside back to the first for loop, and we go to column number 2, and we repeat it for all the rows in column 2, etc., etc., etc. So we just run through all of those very quick. Now we're going to do the same for the test data. So I'm going to create this empty matrix of the same number of rows and columns as my test set, my feature test set. And then I'm going to loop through all of those, this nested loop, same story, but I'm using the feature means and the feature standard deviation. That's from the training set's mean and the training set's standard deviation. So I'm subtracting the test data. So from each individual sample value, data point value in the test data, I subtract the mean and the appropriate mean and standard deviation, but from the training set. Now let's import TF runs. And you see we're using the training underscore run function from training runs. I don't have to put this training runs in 2 colons, TF runs in 2 colon symbols, but just to show you that's where this function comes from. And now I'm going to reference the model that I actually have. So let's run through the model. Our model is I'm going to call it baseline model. It's a Keras sequential model. It has a dense layer, another dense layer, so 2 hidden layers, and then an output layer. The output layer is a single node because this is a binary classification. So I'm using the sigmoid activation function there very nicely to go from 0 to 1. Let's have a look. I've got 48 units and 48 units, so quite a bit more nodes there than the 12 nodes of my input vector. I'm using rectified linear unit as my activation function in both. And remember, in the first one, I have to input the shape, which is equal to the number of features, 12. But I've got this new thing here called kernel initializer. And remember, the first time that we get the first multiplication during forward propagation, it's just going to initialize random values for the weights the first time we go. But we can also set those. We can have a specific one. And this time I'm going to specify kernel initializer, and I'm going to set it to init underscore w, which I created up here. So instead of typing this here, I could have just put in all of this right here. But I've just done it separately to show you that's possible. So I have this initializer, and this is a Keras function, initializer random normal. So it's going to use a random normal distribution for all the weights in that very first tensor that is going to be multiplied by my input vector. And I'm saying that the values for that tensor must have a mean of 0 and a standard deviation of 0.05. And I'm setting a seed value here, 1, 2, 3. That means every time I run it and you run it, you're going to get exactly the same weight values. By default, the bias nodes, they are set to 0. All the biased values are 0 initially, and you see here, I'm not even referencing it here, but you could put it in here as well and just initialize zeros. That is for the bias nodes, but it's 0, doesn't matter. So what I want to do is just bring up a page for you here. Let's bring up this page. So this is keras.rstudio.com, and I've moved all the way along, and I've clicked on the reference tab at the top. And you can see the contents here of this whole long page, but you can just go to the right hand side and you see there initializers, you see regularizers there, you see losses there, optimizers. Let's have a look. So here's one of the initializers. We used initializer random normal. You can see how it works. There's a mean, a standard deviation, and a seed. And you can set those any way you want. And you can also see all the other initializers. So you can try any of these. And if you click on them, here we have a LeCun normalizer from Jan LeCun from a publication. And you can see, you can read more about those, read this efficiency backprop by Jan LeCun, I think. Yeah, that was. And we can try that normalizer. It just has a seed, so there's no other argument to set there. If we look at some of the optimizers, this is the RMS prop optimizer. You can see we've discussed some of these arguments in the previous video. You can read up more about them. Let's get back to our model. So we're going to get to the compile step, and I'm going to use the optimizer RMS prop, and I'm only setting two things: the learning rate. I'm setting the learning rate, and I'm setting row value here. So 0.01 and 0.9, those would be the defaults. My loss is going to be binary cross entropy. I'm dealing with two categorical variables. That's a good loss function. And then we're going to fit, and we pass the training data normalized and the training labels to the fit, and our validation set is going to be test data normalized and test labels. Now this is a data set that contains a lot of noise, very difficult to learn from this data set. So let's go back here, and all we're going to say is training run, and the file equals the name of this file because it lives in the same directory or folder. And up here we set the working directory. I don't have to refer to its full address. I can use it as such. Now it's going to open that file, and it's going to run that file. And then something else is going to happen. Let's have a look. We see that the model starts running, and we can see there's a big gap. There's a lot of variance here, a bit of overfitting, I would say. And we can see the model run over the 40 epochs that we have set. There we go, and then this page opens up. Very nice. We can see some information here on the right hand side. We can see an accuracy of the training set of 75, so we can certainly let this run a lot longer. And then 70% for the validation accuracy, so quite low there. So a few things that we have to do. We see the model here at the bottom, the model with the layers created. And if I go to output there, we can see what the model was, and the code will give me the code of my model and the code of the file from which it was called as well. So very good. Let's close that. Now we can go back to improvements, and we can say, let's make some changes to this. I want to make some changes. So let's change let's make this a smaller network. We're going to put 12 in each of these. Let's put only 12 nodes in each of these. And let's make our learning rate slightly smaller, 0.5. Let's set the row to 0.5. Just changes you can make. Look at those pages on the RStudio Keras website. Think about some of the concepts that we've discussed before. I'm just going to illustrate some for you here. So let's just save this, go back to our original, and let's run this again just to show you. If you do latest run, let's just run that. It'll just give you some information down here in the console as to what had just happened, but we saw that in the overview that came up. So let's train this again, same file, but the changes have now been made. Let's run that. And there you go, it's run, and we can see what has happened as we did before. What I do want to show you though is just, instead of latest run, let's use compare runs. And if we do that, very nicely, we're going to see both of the two previous ones come up, and we can see the changes that were made. So where the units were 48 before, they are now 12. When the second hidden layer had 48 units and now has 12. The learning rate, you see the change, and the change in the row there for the RMS prop. So you can see the changes that were made, and you can do a side-by-side comparison to see if you've improved things. So we can see we can do quite a few more epochs because this was still going down. So I'll certainly do that. We see that we've certainly improved our variance here, our high variance, in that these are closer. Pay attention to the scale though, because that might trip you up. that the scale might make this look a lot better than what it really is, the improvements really are. So have a look at these. But that's a beautiful way to go about it. Just to do these, make changes and compare the runs. Make changes and compare the runs. Let's try something else. Let's go back, and for the weight initializer, we're going to use this Lacun. Let's bring that back up again. Lacun, and you see what happens here. It is going to be a normal distribution, but it is going to vary according to the number of input units, and we spoke about that in the previous video. So it's going to do this according to the input units the input units for this weight tensor. So let's just have a look at that. All we have to do is say initializer Lacun normal. Let's do that. So let's save this. We go back and we're going to run our model again. And there we go. We can see what I would perhaps do here is introduce some dropout or regularization, and I would certainly let this model run for quite a bit longer. But let's have a look. Compare runs now. And now we can see from the previous one the changes that we have made. We had the normal, a random normal initializer before. Now we have the Lacun normal, and we just see the change that we made there, and we can see the difference that it had caused. So it is a beautiful way to play around with your model and see the changes that are made. So in this video, I want us to explore the sequential model a little bit more. Just delve slightly deeper level. It's all about becoming familiar with what is possible. Now, if this is the first video that you see in this playlist, I would really urge you to go back to the start, watch this playlist from the start. I'm a surgeon. I'm involved in research as far as deep neural networks are concerned, and this series really is about deep neural networks for domain experts. So you're not necessarily a computer scientist or statistician. You are an expert in a field outside of that, but you want to get involved with deep learning. This is a course, a series, a playlist on YouTube to get you to become comfortable and familiar with deep neural networks, and we're using TensorFlow as our backend, Keras on top of that, and we're using the R programming language for statistics, a beautiful environment, an easy environment to start learning about deep neural networks. So we're at a stage where we've played before, we've used TF runs as far as it really is this tensor board, playing with that. Let's delve a little bit deeper, and I've got, we can see up here, it's very small, but you'll see the tabs, Model 1, Model 2, and Model 3 already created. But let's first get to grips with what's going on. I'm going to set, as always, my working directory. I'm going to hold down Control and hit Enter, Command and Enter. So we're going to accept that. I'm going to import Keras, and I'm also going to import Plotly, but I'm just suppressing the messages so that I don't get all those yellow messages at the bottom here. So we're going to have Keras and Plotly here. Now let's import a data set. I'm going to use one of the inbuilt data sets inside of Keras, and it's the MNIST data set. Now I just want to move here. I'm going to go onto my other monitor. Let's bring this up. There's the MNIST. In case you haven't heard about it, it really is famous. It's the easiest data set. By that I don't mean easy for a computer to learn, but to explain things. So there are many of these handwritten digits. They're tiny little files. It's 28 by 28 pixels. It's monochrome, so every pixel in this 28 by 28, I mean, remember how big the photos are that your phone can take, so these are really tiny. 28 by 28, and every pixel of that 28 is just one after the other, 28 in one column after the other, and then next row, next row, next row. It's just between 0 and 255, 255 being a bright white pixel, 0 being a pitch black pixel, and there's this gray, all the grays in between. So it just gives a value at each of these 28 times 28 pixels, and each of these are looked at by a human being, and a human being has marked all of these, that's a 6, that's a 6, that's a 6, and then you want the computer to learn what, if I give it one of these, what it is. So that's what we're after. Now, the best way to do images is not through a normal multi-layer perceptron, a densely connected neural network. A better way to go about it is a convolutional neural network, and we are very close to start looking at convolutional neural networks. We are not there yet, so I'm going to do something with this data set that will still allow us just to use our normal densely connected neural network, our multi-layer perceptron. So let's have a look at this, and I'm going to use my normal function that we have, or the symbol that we have here, this percent with a backward arrow percent, and it's the data set underscore mness. That's our function, and we're going to import that, and it's very nicely written in Keras that I can immediately split it up, done all for me. So I'm using C to have these this list of lists, and inside of that I have X train and Y train. That's my X train would just be my training set and my training labels, my test set and my test labels, and that's what I've called them. My objects I've called X underscore train, Y underscore train. So it's going to take a second or two, but let's import that. There we go. Now let's have a look at the dimensions. I'm just calling dim on X train, and right here at the bottom we see there are 60,000 and then 28 and 28. So this is a tensor. It's not just or I should say rank 2 tensor. It's not just a rank 1 tensor, or a rank 2 tensor I should say, where it's just a matrix of rows and columns. We've added another dimension to make this a rank 2 tensor. So it's 60,000 images of 28 times 28. Now what I want to do, now think of that 28, it's one after the others in the first row, so that we have 28 pixels in the first row. We jump to the second one, 28. But what we could do is just make them all into one long vector. So 28 times 28 is 784. So I'm changing this into something that has 60,000 rows and 784 columns, and that's 784 columns. So each sample in that one long row is just all the 28 times 28 pixel values in one long row, and that's what we're doing with array underscore reshape. It's a function, and it's going to take X train and it's going to reshape it into this row and column. So the columns are easy. It's 28 times 28, that's 784, but the rows are a bit different. You have to call the number of rows of X train and put that inside of our C function there. And we're going to do exactly the same with X test. So that now, if we look at the dimensions, we see 60,000 rows for X train across 784 columns. As simple as that. Now we need to normalize. Remember, we need to bring them all down. And the way that we're going to normalize this is not by doing standardizing it, by subtracting the mean and dividing by the standard deviation. It's because we have this very gradual, very linear from 0 to 255. All we're going to do is we're going to use broadcasting by dividing every value by the maximum, which is 255. So every pixel value is now just going to be some fraction between 0 and 1 of what it was, because we're just dividing each of them by 255. So that's one way of normalizing our feature set, our feature variables, which we haven't seen before. So let's just look at what train number 1 was, our training label in our training data set, what the first label was as far as the target's concerned. Yeah, it was a 5. So now we're just going to do one hot encoding. Remember, that's the 2 categorical function inside of Keras, and because it's from 0 to 9, the handwritten digits, there are 10 of them, so I'm using 10 as an argument, and we're going to do both of those. So let's look at what 5 was. So I'm going to call Y train 1, the row 1, comma, space there to show me all the columns, and look at this, 0, 0, 0, 0, 0, 1. So if I count from 0, 0, 1, 2, 3, 4, 5, the 5 is one hot encoded. So indeed that 5 is now represented by this 10 element vector, of which the 5th one here with a starting from 0 is one hot encoded. Excellent. Now let's import TF runs so that we can actually have our tensor board to look at these. And I'm going to call mnest underscore model underscore 1.r. Let's open it up and let's see what this one was all about, because I promised you we're going to delve slightly deeper into the sequential model. What can we add? And the first thing that's going to pop out here is this callbacks. We haven't seen callbacks before, and I want to introduce you to callbacks here. So my model is just going to be a Keras underscore model underscore sequential. We've seen this before. I'm going to use my pipe symbol here. So I'm going to pipe model as the first argument to layer dense. So I'm going to have 1, 2 dense layers here and then a third dense layer. My first dense layer, 256 units. That's fairly conservative, remembering that I have 784 columns. So I'm going down from, remember, right at the beginning, we drew all these circles with all the lines in between them. I'm going from an input vector of size 784 to down to 256. My first hidden layer has only got 256 nodes, whereas my input had 784. So that's dropping down quite a bit. My activation function would be a rectified linear unit. And remember, for that first layer, you've got to tell TensorFlow or Keras in this instance then what the input shape is, and that's 784. It's got to accept that. From there, it'll infer how big the weight matrix is, the weight tensor that it has to multiply. So my second one drops down even further to 128. Rectified linear unit is my activation. My last one is 10 units, and I'm going to use softmax. I've got to use softmax because I want a probability for 0, 1, 2, 3, 4, 5, 6, and 8, 9. And the one that has the maximum probability, that's going to be the predicted value for that handwritten digit. Then I'm going to compile the model. My loss is going to be a categorical cross entropy, as we should do in this type of problem. My optimizer is going to be RMS prop. We've seen that video, what RMS prop is all about. My metric is going to be accuracy. And then I'm finally going to fit my model with X train and Y train. I'm going to run my mini batches, 256 rows over 50 epochs. Now let's get to callbacks. You pass a list of all the callbacks that you want, and I'm only going to do one callback here, and the callback is early stopping. Early stopping means it's going to run. You know that we're going to see this graph on the right-hand side, but when it sees that something is happening, it's going to terminate the learning process. And the arguments that we're going to use there is what to monitor and for how long. So monitor, in this instance, I'm going to monitor the loss. Because I pass validation data to this, I could have just loss, or I could have val underscore loss, or I could also monitor the accuracy or the validation accuracy. I've chosen loss as my simple example here. And my second argument here is patience. So every time a loss comes up, it's going to look at 2 beyond that, because I've set it to 2. And if my loss doesn't decrease, then for 2 mini batches in a row, it is going to say, halt, stop the bus, we're not learning anything more, exit from this, I'm stopping. And that is what this callback is all about. I'm still going to set my verbosity to 2, and my validation data, I'm going to use my test data as my validation data. So that's model number 1, and I just have to write it out like this. I don't have to import Keras. It's all going to come from here and from the TF runs. So let's run this training run for that model, and because we've set the working directory and these models all live in the same directory, I can just use the name.r. I don't have to type in the full address. So let's run that. And we can see in this instance, so I can do the recording and post this to rpubs. I'm not using my GPU, I'm running this off of the CPU, so it's a bit slow, but we can certainly see things starting to happen there. You can see the little zigzag pattern there in my validation data set. It probably means that, remember that my mini batch size is too small, and that we get this noise inside of it going up and down, depending on the specific data inside of that mini batch. We can smooth this out by making the mini batch size, the batch size as it's called, as an argument, slightly bigger. Now let's just, while this runs, just talk for a moment about the base truth that we have here. This was done by a human being. We're going to accept that the base accuracy here, the human level accuracy, was very close to 100%. So if we think about our variance and our bias, and we look at this, certainly we're getting very close to 100% in our training set, so that's going very well. But there's between that and what we expect the ground truth to be, the real truth, is very small. And so we're probably dealing with a bit of variance here, a bit of overfitting, and we have to do something about that. But we've called TF runs, and we've got called train data, so we get this beautiful tensor board illustration. But look what's happened. We see this early termination here because of our callback. So it's recognized that for 2 steps in a row there was no increase in the accuracy, or was it loss? Now I can't remember what I called. Let's have a quick look. we used loss. So it didn't see that the loss got less for 2 after 1 was called, so it terminated early. No problem whatsoever. And that's very good. It's very good to set that so that you don't sit with bigger models. I mean, all of these are toy models that we've dealt with. You don't want to sit for days and have something run and nothing really is happening. Your model's not making any improvement. So to put these callbacks in, very, very good thing to do. So let's just go to our second model. Let's see what we did there. So what we've done, it's a bit more restrictive, 128. So that space, that hypothesis space, I'm shrinking it down, and I'm also doing a bit of dropout, 0.2 there. So I'm adding these 2 dropout layers there. I'm using RMS prop still. I'm still using my callback, so nothing's changed. So there wasn't, I don't know if one can really call this that there was high variance, but between what we assumed to be this baseline of 100% accuracy as the labels were done, the training data got very close to that, but then there was this gap, slightly to the test data, the validation set. So let's try and improve that by constricting our hypothesis space a little bit, just for fun. Basically, as a reminder, I haven't introduced anything new, but let's run this model, and we can see training is going on. We can see quite slow. Remember, I'm running this off of a Core i7 Intel processor, so it's not running off of my GPU. So it's going slowly, but we're certainly getting there. And we can see our model there went right to the end. So the callback did not terminate. It didn't have to, didn't find this reason with the patients being set to 2 to terminate early. So we see this whole run taking place over all 50 epochs. So let's compare these 2 runs. We've seen that before. And now we can see the 2 runs. So let's look at this accuracy. Really, for the training set, went up to 99, 98 for validation. And here it was on this side. Let's have a look. Yes, on this side it was 99, 98. So certainly you must always have a look at the scale. It's deceptive, this y-axis, very bad. And so just look at that. So as I say, we haven't really improved this, and whether we should call this high variances, that's also debatable. But it's about the principle, you get it. And then we can see the changes we made. We went from 256 to 128. All the greens are the new ones. We introduced a dropout layer there, and etc., etc. Let's look at model number 3. Something new I want to show you here as well. So we've got our constricted model still. We've got the dropouts, etc. And now when we get to compiling in the optimizer, before we would have just put Adam inside of quotation marks. What you do there is you just accept all the default values. And in the next video, if I have time, I might show you an easy way after creating your model how to get to what all the defaults were. It's very easy to do. But here we instead of just using all the defaults by putting Adam inside of quotation marks, I can actually use the proper function. It's called optimizer underscore Adam, which allows me to add some of these default values or change them even. So if I just hover there, it's tiny. You're probably not going to see this on your YouTube video, but it says there learning rate 0.001. So I've changed that to learning rate being 0.003. There's beta underscore 1, beta underscore 2. We've spoken about that before. We have an epsilon there, a decay rate, a AMS grad, clip norm, clip values, etc. So I've changed 3 of the arguments there. And that is how we drill down deeper into the sequential model, where we start manipulating things to our heart's content. And it is so easy to do. So there we go, a lovely example of drilling a bit deeper. So instead of using the default values by just using the name, and this for Adam, it would just be Adam in inverted commas, I'm actually using the function optimize underscore Adam so that I can manipulate the arguments that go with that. So that's beautiful. That is something new. So let's just run this model 3. Now while that runs to the end, I'm going to stop the video here. We can just compare them. It's going to show us the comparison. You've seen that before. But now you've seen drilling down a bit deeper, getting a bit more finesse, taking more control over your sequential models. So before we move on to Looking at regression problems, I want to just stop and give you a little bit of an insight as to how we calculate a loss function in a classification problem. Now, of course, with numbers, it's very easy to state what the difference is between numbers. I mean, there's a variety of ways that we can do this: mean squared error, etc., absolute mean square error, absolute mean error, I should say. But what do we do if something is either a nodule or not a nodule, a cancerous growth or not a cancerous growth? Or when it comes to imaging, when is it a bus, a stop sign, another car? How do you calculate that difference? If the target value, the actual value, was a bus, and our model predicted that it was a stop sign, how do we calculate that loss? And of course, we do it through cross entropy, and we have the binary and the categorical cross entropy loss functions that you've seen before. So let's just peek a little bit behind. I just want to give you some intuition about this. So imagine I have these 12 elements. We're going to start off with this concept of entropy, really. Entropy just borrowed from physics, where it just means order or chaos. As a system is just left to itself, to its own devices. There's no external energy input. We're going to increase the entropy, so the chaos is going to increase. And I use here, if I have a house, if I start with a heap of bricks and bags of cement just lying there, it's not going to build a house by itself. You have to put some energy into that system. But if you start with a house and you just leave it, it's slowly going to decay until you have this rubble, and you're going to see the bricks and the cement dust just lie as the house decays. So the entropy increases. And we use that same concept here. We just borrow that concept about if we have information about something, how can we quantify that? So I imagine I have these 12 elements. I've just grouped them all together, but they needn't be in this specific order. So I have car, 6 of them, bus, 4 of them, human, and a stop sign. So you can well imagine this is some classification problem, and it is for self-driving cars. So it's these 12 elements in an image, or different images. And I task you to come up with a series of questions such that when I draw one of these at random, now you can see there are 6 out of the 12 are cars, so there's a high probability of being a car. 4 out of 12 of being a bus. 1 out of 12 me selecting the human at random, and the stop sign at random, also only 1. So there's a different probability of me drawing one of these at random. But if I did, you had to ask me questions. How can you structure those questions to get to what I do at random? So this is one way to go about it, a clever way. You can ask, is it a car? Now these are binary questions. Is it a car? And if it's yes, if the answer is yes, well, then it was a car. If it's no, of course, it can be any one of the other 3. It'll be better to ask the second question, is it a bus? Because if it's yes, then it is a bus. If it's no, I only need one more question. You can ask either human being or stop sign. If you ask human and it's yes, it is a human, and no, it's a stop sign. So on average, you had to ask one question for this group that had the highest probability. You'd had to ask 2 questions to find out if it was a bus, and you would have to ask 3 questions before you found out whether it was a human or a stop sign. So we can sort of put those 2 together. We can say, well, I had to ask one question for something that had a probability of 0.5. So I can say 1 times 0.5 plus. I had to ask 2 questions for that thing that had a probability of 1/3. I had to ask 3 questions times the probability of 1/12, and another 3 times probability of 1/12, and that gives me this entropy value. And it comes from information theory. So it says that on average, if I did this many times over with that probability, you would have had to ask about 1 2/3 questions to find out what I drew at random. That is the information locked away in the set. Now we can look at it from a theoretical point of view, where we can calculate the theoretical minimum number of questions. So if everything here, as far as the probabilities were concerned, were a power of 2, then you're going to see that these 2 values for entropy and the theoretical entropy is going to work out exactly the same. But if not everything is a power of 2, as far as the probabilities are concerned, you're going to get this theoretical minimum at the bottom Here we can see 1.62, which is slightly less than the 1.66. And here's the equation for entropy. It says take the negative of the sum of all these products. And what you do is the probability of the first one, that was a half, times the log base 2 of that probability. So I would do half, log base 2, half, and then a third times log base 2 of a third, and then a 12th times log base 2 of a 12th, and then another, add to that another 12 times 1 over 12 times the log base of 1 over 12. So just plug in those 4 probabilities there, multiply them, those two, the product of that, add all of those and put a negative sign out the front, because we're going to end up here with a fraction and we want a positive value, so we're going to put the negative out there. So this vector D, that just refers to the fact that it's just a vector formed by these probabilities, half, a third, a 12th, and a 12th. So let's build a little function here inside of R. I'm going to call my function entropy. I'm going to use this assignment operator, and then I'm going to say I'm specifying a function. It's going to take a single argument D, and what I want to do is I'm going to just create this internal variable called x, started at 0, and then for I in D, so in each of my elements in D that I pass to my function, I'm going to say take x, whatever it was now, we start with 0, and I add to that, it's 0 at the moment, I, so that's the first, that's 1 over 2 times log of 1 over 2 base 2. Now, if I run through it again, x now has a new value, and I add the second element, the third element, the fourth element to that, and I want to return negative x. It's minus the sum of all of these. So if I run entropy and I put my vector in there, it's going to come out to 1.652815. That's the entropy. So that's the theoretical minimum number of questions or bits required to answer this question. So from there we go to this idea of cross entropy. Cross because we are not comparing a single distribution of probabilities here, but 2 distributions. We're going to compare 2 of them. And remember multi-hot encoding, one-hot encoding. So remember, also let's suggest that one of my target values, the actual value, is 0, 1, 0. So it had 3 elements in it. The target, the number of classes, or the sample space of my target variable had 3 elements. And in this case, it was the second one. So maybe that was car, bus, and stop sign, and this one was bus, because the second one was 1. So I'm taking an object, a categorical variable, and I'm changing it into a vector. And my predicted values might be something like this, 0.1, 0.1, 0.8, 0.1. So we've got to see this as a distribution, and this is a distribution. And we're just going to compare the difference between those 2 distributions. And the way that we do that is a very similar thing. So we're going to take each of the elements in my vector of the actual values times the natural log of the corresponding value in my predicted vector. Why natural log and not log base 2? Well, we're not asking binary questions here. And remember that if I ask for the log, say that A was 2, log base 2 of something, that will just be log B divided by log A. And if A was 2, I'm just dividing by a constant. So it's kind of useless just to do what you are doing by asking for log base 2 is you're really just dividing by this constant. So usually we just stick with the natural log, and that's why I put L in there just to indicate natural log. So remember, this is my target and this is my probability. Now it's very rare that one of these would be 0, because you can't take the natural log of 0. And they'll just be code inside of TensorFlow or whatever framework you're using, just to have a little escape should one of those be 0, to still give you a return on that. So just to create that little cross entropy function, you're going to take 2 vectors, p and p hat. I've just named them p and phat. And there is exactly the equation that we have up there. And we're just going to return negative the sum of all of those, and we do the sum by iterating over all of these. So that's one way to do it. There are many other ways to do it. So if I pass my 2 vectors here, 0, 1, 0, and 0.1, 0.8, 0.1, we see a categorical cross entropy value of 0.22. And hence, we can do gradient descent. We can do back propagation to do gradient descent to improve this this error, this loss. And that loss is categorical cross entropy. And remember, with the categorical cross entropy, to get the derivative of the log function, the derivative of the log of a value is 1 over that value. So the back propagation is definitely not that difficult. So that's it. I just wanted to give you some intuition, some idea behind what do we do, where do we get this difference between two categorical data point values. And the easiest is to do it in this format of categorical cross entropy. So welcome back to the series, just for domain experts trying to learn something about deep neural networks. So up until now, we've just looked at classification problems, and we've also just stuck to our multi-layered perceptron, that is just this densely connected neural network. And I want to draw it to a close by just moving away from these classification problems where our target variable is actually categorical in nature to a target variable that is numerical in nature. So we're trying to predict a continuous numerical data point value. And that is called regression problems. So I'm going to show you just how to construct a regression problem, how to construct that deep neural network to handle this regression problem. So one or two little changes we have to make from the classification problem that we looked at before. And I just want to show you one more piece of insight into how these layers are constructed, and just something to show you that you can explore on your own, something else you can change about your models. This is going to be the end of the section on the densely connected neural networks, and we're going to move on to the, I think, much more exciting world of convolutional neural networks very soon. So let's have a look. We're going to use the reader library, Keras, of course, and Plotly. Let's have a look. So I'm just going to import some data, and I'm going to use the read_CSV from my reader library. And I'm going to import this file. Of course, this is on RPubs, this document that we're looking at, and the file, this actual RMD file, and this data file will be available on GitHub. You can just look at the links in the description below this video. So regression data.csv, column names is false, so it's just rows and columns of numerical values. The first row does not contain column headers, there's no variable names. And if I look at the dimensions of that, I see I have 4,898 samples over 11 columns, and those 11 columns will be my 11 variables. That's 10 feature variable, and the last one, just to tell you, is the target variable, which is numerical in nature. As per usual, this is my way of working. I want to change it into a matrix, and I'm also going to remove the dimension names, because even if I change it into a matrix, and if I look at a view that's with a capital V in RStudio at this, I'm still going to have the x1, x2, x3 at the top, so I remove all of that. This is a pure matrix of numbers. That's the way I like to use it. Just to look at the summary of column number 11, which is my target variable, we see that it's numerical variables with a minimum of 2.5 and a maximum of 9.3. We see medium of 5.9, and we see the first and third quartiles there. If I use Plotly, remember Plotly, open and close brackets, that's just going to give me this empty canvas. And I use my pipe operator there, so I'm going to add a histogram. On the x-axis is going to be the data set, all the rows, column 11. I'm going to give it a name. The layout will have a title. We see the beautiful title here at the top, and the x-axis as a list will have a title, and the 0 line being false. I don't like these big black lines across my plots and graphs here. You can do what pleases you. And look at this wonderful, we see these peaks that it forms my numerical target variable ranging from the 2.5 to the 9.3 at the end. So we see this beautiful histogram. Lovely. Now the train test, we're going to do that split. I'm going to do it in the usual way. I'll set the random seed, so when you run this code you get exactly the same split. Remember, I'm going to just create this index of values 1 and 2, and that's what the 2 is for. We'll automatically start at 1, and I do that over and over again until the number of rows of the data set, that's the 4,900 odd, and we're going to get here, I want an 80-20 split. so that 80% of the data is going to make it into the training set and 20% into the test split. We've looked at this many times before. I'll just move over it quickly, and I'm going to create my xtrain, xtest, ytrain, ytest variables, and doing that by using this index that I created up here. Very easy to do. I've also got to normalize my data, and remember, I'm going to calculate the mean and standard deviation of my training data set, and I'm going to scale my test data set according to the mean and standard deviation of the training set, not the test set's mean and standard deviation. And then, of course, I've got to just scale xtrain as well, and the scale will do that for me. It'll bring all 10 of the feature variables, it will bring them into a mean of 0 and a standard deviation of 1. Great stuff. Let's build our model, because that's where we're going to see the first little difference. Still a sequential model. I'm going to have 1 dense layer, 2 dense layers, 3 dense layers. It's just for demonstration's sake here, nothing special. I have 25 hidden units in each. I have the rectified linear unit as my activation function in each, and my input shape for my first hidden layer is just the number of feature variables, which is 10. I've got 20% dropout in each of these, and then here's the special one. The last layer, because this is a regression problem, I'm just going to have a dense layer with 1 unit. No activation function, nothing else, just 1 unit. That's it. Let's look at the summary of that model, which then gives me 1,601 learnable parameters. And we can see the last layer there, just a single node, no activation function, nothing. I want that pure value that comes out of there. And this is the bit of deeper insight I wanted to share with you this time around as we end off the section on multi-layer perceptrons or densely connected neural networks, is this getConfig function. So I'm using pipe just to pass model as the first argument here to getConfig. And look at this. Let's start with our first layer. It has a class name. This is behind the scenes because we just did this. There's lots of other arguments that I can pass to layer dense, and here they are. So the class name was dense. The config was name dense1. I didn't give it a name. Remember, we could give it a name, so just the default. Trainable. That is something we're going to look at in the future, especially when we get to convolutional neural networks. It says that all these weights and biases, I want them to be trainable. With backpropagation, I want them to be updated. Now, what we're going to do with convolutional neural networks, you can actually download pre-trained neural networks that'll have these values already in them, and they can form the first part of your neural network. And those weights are cast in stone. Someone else created them, used huge numbers of data, and has already trained those weight and biases values. And we're going to use them, so we can actually set that our weights for that layer is non-trainable, especially if we bring that layer in from a pre-trained model. We see D type there is float 32, and that's the default for TensorFlow. It takes 32-bit floating point values. The units 25 hidden units. The activation, we actually said, ReLU, use biases that by default is set as true. You can also set that as false, so there's no biases, a bias vector in your deep neural network, or tensor I should say. And the kernel initializer, remember the first time this runs, it just initializes random weights, random weight values. And there's different ways you can go about these. And the way that is default is by variance scaling. And the config is a scale or standard deviation of 1. And the mode is this fan_average. And the distribution is uniform. And there's no random seed. So look into all of these. These are actually quite fascinating. And there are a lot of these distributions you can use to set your weights initially. The bias initializer is going to be set to zeros. The kernel regularizer is set to none. The bias regularizer is set to none as well. The activity regular... I'm not going to say that word today. This is impossible for me. None. Kernel constraints and bias constraints, also called clipping, those are set to none. Also something you can look at. Then we get to the dropout layer. The dropout is also trainable. Set to true, this trainable. The rate is 0.2, which we set. We set no noise shape, and we didn't seed it, so that the same values are used every time. And then we get to dense layer number 2. So there's lots of these arguments which we never ever used when we constructed this. Look into those. They are quite amazing. So we've got to compile now, and that's our different
The second difference, other than the dense layer with a single node, no activation functions, our loss is just going to be, we'll choose mean squared error here. And our optimizer is going to be RMS propagation, the RMS prop there. And we see there the RMS prop empty parentheses there because we're just accepting all the defaults, and the defaults are a learning rate of 0.001, a row of 0.9, epsilon null decay rate of 0 for our learning rate, and a clip norm and a clip value of 0 and 0. Now the metric we're going to set to mean absolute error. Now the metric, remember, that's like a type of loss function, but it does not form part of the actual gradient descent and the back propagation. That just gives us our view of the error as this runs. The loss function that we're actually going to use is not mean absolute error, but mean squared error. Let's fit that data. We ran it through 50 epochs here, batch size of 32, validation split of 0.2, and I put in a callback, and my callback was early stopping, and I was monitoring the mean absolute error, and if 5 values did not do any better, it would terminate those epochs. Verbosity at 2. I ran my model, do that, and then let's just print this out. So something new. If I use this backwards pipe, so look at this, it's less than and a minus sign. So this evaluate function is going to give me two values. It's going to return 2 values, and I'm placing them inside of this list, loss and mean absolute error. And that is what it's going to return for me, the loss and the mean absolute error. So I pass X test and Y test to that. I didn't want anything printed to the screen, and I'm just going to do that evaluation. And that's going to give me these 2 values, loss and mean absolute error. And I'm going to print those 2 out using this, you haven't seen this before, in R, the paste 0 function. So I have my string there, mean absolute error on test colon space, and I'm pasting this with the printf function, and that this percentage.2f means 2 decimal places, and what I want of these 2 is the mean absolute error, and that prints me out a mean absolute error. Remember, it was about 3 point something to 9 point something. A mean absolute error of 0.62, so not too bad. So there you go. In short, a regression problem. We don't often deal with regression problems, but now you know how to do it, and you know how to create that last layer of your multi-layer perceptron, your densely connected neural network, and you know which of these loss layers, the MSE mean squared error, is a good loss for that. You've also learned about all these other arguments that you can change inside of the creation of your model. Next up, we're going to start looking at convolutional neural networks.
So welcome back to this series on deep neural networks for domain experts. And we finished the first section where we just looked at the multi-layer perceptron or densely connected neural networks. And we're going to move on now to the very exciting world of convolutional neural networks. And when we talk convolutional neural networks, we're really thinking artificial intelligence, machine learning on images. It really is a type of network architecture that lends itself very well for learning to recognize images. So let's just have a quick introduction as to how we're going to go. The problem that we obviously have with densely connected neural networks, if we think of an image and we think of an image being represented as a matrix, let's go down here and just have a look at this representation. We're all familiar with pixels on a screen, those little dots of color. And if we just think of a black and white image, that just is a brightness value. Every pixel will just have a brightness value from 0 being black to, say, 255 being white, and any like gray level in between. So just a 5 by 5 representation of a pitch black little image here will just be a 5 by 5 matrix of all zeros. But if you think about a 5 by 5 pixel little image, that's tiny little corner of your screen. If you were to ramp that up just to 100 by 100 pixels, that's still a very, very, very small little image. But 100 times 100 pixels, there's 4 zeros there. That's already 10,000 data points.
So you're talking about an input vector with already 10,000 nodes just for a tiny little image. And if you do a densely connected neural network and every deep layer has 10,000 plus nodes in it, that's going to be computationally very, very expensive. So we're going to solve that problem with convolutional neural networks. And what we have to talk about then is just this convolution operation. So what you see here is two tensors, two matrices, and they're both 3 by 3, and I'm going to multiply them with each other in a very special way. And it's called, I'm going to convolve. Well, it's not the full convolutional operation. We'll get to that. But what we do is we're going to multiply each corresponding element in the two neighbors. So this one here, and this 3 here will be multiplied with each other. Then we move over to this 2, and then this 3. So it's 1 times 3, and then the 2 times 3. So we do all these 9 products, and we sum up those 9 products. So it will be 1 times 3 plus 2 times 3 plus 3 times 2 plus 4 times 1, and eventually we add all of those and we get to 61. Now, when we look at an image, and here we have a larger image, we count 1, 2, 3, 4, 5, 6, 6 by 6 little image. And now I have my 3 by 3 matrix, and I start with it at the top left, and I'm going to do that type of multiplication that we just described. So I'm going to have a value for each of these little gray blocks that I drew in here. They'll each have a value in them. And the picture at the back, the gray picture with the 6 by 6 pixels, that will have values, and I'll multiply all of them and add them. And then I'll have a number, and this number is going to form, for this first one, the top left pixel value of my new image. So I'm going to have what I'm going to call a resultant image that I'm trying to create. And the first top left pixel value is going to be this sum product over here. Then I'm going to move across 1, still with the same 9 values in my little matrix here, new values below it. I'm going to do that same process. It's going to give me a second value, a second scalar value, and that becomes the second pixel on the top of my resultant image. And so I move on and on and on across to the right hand side, drop down 1, move across to the right, drop down 1, move across to the right, till I get to the bottom. And that is the convolution operation, and it's going to build up for me a new resultant image. I'm calling it a resultant image. It's easy to understand what we mean by that. You can sort of form a visual idea of what is happening. Now, when we have this little 3 by 3 block, we call that, those 9 values, we call that a filter or a kernel. And that is 9 values, if we have a 3 by 3, which are actually weight values. And that is what our neural network is going to try and learn. It is going to try and optimize those values that have to go in there. And if it runs across an image like this once, it keeps those same values. Now we just have to think about this resultant image. What is its size going to be? Well, if we start with an n by n, that's n for November, and we have a kernel of m by m, the resultant, if we just step across 1, and we call that a stride, if we step across 1 at a time, our resultant image is going to be n minus m plus 1. So we'd had 6 minus 3 is 3, plus 1 is 4. So we're going to end up with a smaller resultant image, which is 4 by 4. Now, if we think about a color image, though, a color image has 3 channels, a red channel, a green channel, and a blue channel. And all we're going to do is we're going to have this time I've just drew 2 by 2, was just easier to draw instead of a 3 by 3. Usually we'll use 3 by 3. It's the same one that runs across all 3 of my channels. And now I'm just going to have a times p as well. So if I have a 6 by 6 image in grayscale in color, that's going to be a 6 by 6 by 3. So there's going to be these pixel values for each of my 3 channels. And the same process is just going to happen. It's going to run across all of them. And here we have an example, and you can check it out from my original pixel, monochrome, and its values. These have nothing to do with the black and the gray and the white that you see there. I just wanted to color them different just so that you can see. And try and do this for yourself and run across this whole thing, and you can see we went here from a 6x6 to a 4x4 resultant image. And at the moment it's not clear what the idea is, what is going to happen here. And I've actually got a video which I'll link in I'll show the link in the description below, and there's also a link in this document, a video on YouTube where I use Microsoft Excel and I show you what the result is and what happens here. What does this little kernel or filter that moves across, what does it achieve? And what it achieves, at least initially, in a convolutional neural network, because we're going to have many of these convolutional layers, is it starts to learn edges. So it's going to see that there's, in your picture, there's an edge, a clear distinction between one brightness value and another. If you have an image of a dark cat against a white background, there's going to be an edge, and it's going to start detecting these edges. And as it goes deeper, these kernels are going to learn how these edges fit together, how they form shapes and more complex shapes, and eventually we're going to end up with this product from which your neural network can learn. It can recognize this image. Next up is just this concept of padding. So what you can do, if you have an image and you want the resultant image to be of the same size, you can pad your original image with the zeros all the way around. Now if you run it across, and it was originally 6x6, you have drawn a 5x5 one. If you run it across, it's going to end up being exactly the same. And that's just going to be a hyperparameter that we set in our layer. What we want to do, the padding. Do we want the resultant image to be of the same size, or are we just going to allow it to get smaller as we move through? That is something we just choose. I've mentioned stride before. You can also set what the stride length is going to be here. And in this depiction here, we're jumping with our 2x2 kernel. We're jumping 2 pixels across, not just 1. So we can set that stride as well. Now there's another concept called pooling, which we can also add to our layers. And we usually would do something like 2x2 pooling. So once we have our resultant image after convolution operation, we might decide that we're going to take a little 2x2 grid like this and take the maximum value in there. And that maximum value is 78, and that becomes the first pixel there. Then we're going to move 1 across, again the stride, and if we look at that, the maximum for the next 4 is also going to be that 78. So that's 78. And then we move it across 1, and then the maximum is going to be 70, and that's 70. And that's called max pooling. We're trying to almost get the maximum information from this image. Before, there was also, some people also used average pooling, so it would be the average of those 4 values, but max pooling actually works best. Although there's no evidence really to say that there's anything better than max pooling. Max pooling is going to give you good results. The last concept just is flattening. When you've run through a few of these layers, a few convolutional layers, a few max pooling layers, eventually you're going to do a flattening layer. And what the flattening layer is going to do is, say for instance our resultant image is 9x9, it's just going to form a single vector of these. So it's just going to put them all in one, so we can have 9 nodes, for instance, 78, 78, 70, 108, 108, 88, 108, 108, 88, as one long normal vector, which we can then put through a normal densely connected neural network. And that usually happens at the end of a convolutional neural network, that we put a few densely connected layers, and during which we also have this learning process as we had before in the normal multi-layer perceptron or deep neural network. It has an added benefit that we can talk about afterwards. There are massive networks available that have already learned from images, which you can just download and then add, if you want to put your own images through that, make this convolutional part such that those weights never update, but that eventually that feeds to a normal deep neural network from which learning will take place for the images that you feed in. And we'll talk all about that in later videos. So in short, that's a summary of a convolutional neural network. the best way to go about this is just to construct one, and in the next video that's exactly what we're going to do, implementing some of these concepts that you now know of. You know they exist, you have an idea of how they work. We're going to implement them in the next video. So in this video, let's have a quick look at an example of a convolutional neural network. So we've discussed some of the types of layers that go inside of a convolutional neural network and what the idea is behind this convolutional or convolution operation, and that we're really talking about images here. Images really work well when we talk about convolutional neural networks. So we're going to use one of the data sets that is available right inside of Keras, and that's the MNIST data set. I'm quite sure you've heard of that. That's just tiny little images of handwritten digits. They're all in monochrome, in other words black and white, and they're all labeled. So someone wrote an 8 and a 7 and a 6, I suppose all sorts of people, and those were just labeled by human beings as such. So let's import that, and we're just going to assign that to a computer variable called MNIST, and what we are loading is this dataset underscore MNIST. And that dataset it's already been divided into a training and test set. So with these built-in data sets, we don't have to worry too much about that. So all we have to do is just assign 4 computer variables, and as usual I'm going to call mine x underscore train, y underscore train, x underscore test, y underscore test, and we see there that it's MNIST, and then as always with R, the little $sign, that's Shift and 4 on my keyboard, and then train, because the training set, and then the feature, which is the actual image, is x, and then it's the labels y. So we're going to do that both for the training and the test set. So if we look at the dimensions just of X train, we notice 60,000, 28, 28. So what does this mean? Certainly this is something larger than we've seen before. In other words, we usually just had the feature variable, and there were, say, 70 rows or 10,000 rows, so many columns, and the columns, those were the number of features. But this indicates that we have 60,000 samples of 28 by 28, and that is what these images look like. They're little grayscale images. They're 28 pixels by 28 pixels, so tiny little squares, and then each value is just between 0 and 255, as we saw before, and that's just the brightness value. So let's record those as computer variables. I'm going to call it img underscore rows and img underscore columns. That's just the pixel dimension. Because what we need to do, we need to reshape this as a tensor in a format that our model is going to expect. Because what is missing from this 60,000 28 is the number of channels. So we have to add that. So let's use the array underscore reshape function. So it takes xtrain as our argument. And then we have to pass in the number of rows in xtrain. So we use C function, and then the nRow function of xtrain, then image rows, image columns, comma 1. So we add that comma 1 at the end just to show that there's one channel, and we're going to do exactly the same for the test set there. And then we're just going to store input shape, because as we pass our first layer or our first data into this model, we just need to know the input shape, and the input shape is going to be 28 by 28 by 1. That is the size of the images, and comma 1 there's one channel. And this is the way it is set up. If you use other frameworks, some of them might use the 1 or the number of channels first and then the row and column size. But here inside of Keras, using TensorFlow backend, it is image width, image height, basically, comma 1 or comma 3 in case it was a color image with 3 channels. If we now look at the dimensions of xtrain, we know that it's 60,000, 28, 28, 1. Next up, we have to normalize our data sets, and because each value that's just between 0 and 255, we can just divide by the maximum, which is 255. So that's going to bring everything in this 0 to 1 range for us nicely. I'm going to create a computer variable called numClasses as 10, because I'm going to use the 2 underscore categorical to do the one hot encoding. Remember, there are 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so there are 10 classes. And the way that we use 2 categorical is we're going to pass the variable there that contains our labels, y-train and y-test, comma, the number of classes, in this instance they're 10, so that if we have a look at this first example in the training set, its label was, and it starts counting from 0, so 0, 1, 2, 3, 4, 5. So one hot encoding for the first little image being a 5. So let's create our model, and as always it's just going to be a sequential model. So we pass, we're going to create a computer variable called model. It's going to be a keras underscore model underscore sequential. We're going to pass a 2-dimensional convolutional layer next, 2D, because we have, it is a 2D image. It has 2 dimensions, in other words it has a height and a width, or width and height. And we're going to do 16 filters of 3 by 3 each. So we have these 9 values that are going to pass over our 28 by 28, but we have 16 of them. So you can imagine we're going to run through it once, and we're going to have a slightly smaller image, our resultant image that we spoke about before, but we're going to stack 16 of them behind each other if you want to visualize that. We're still going to use an activation function, the rectified linear unit, and now we put that input shape in of ours, which was 28 by 28 by 1. Next up is going to be a max pooling layer, so that's going to take a little 2 by 2 blocks, and it's just going to take the maximum value out of that. Then we're going to have some dropout. We can have dropout layers here as well, and we're going to drop a quarter of the values. And then we're going to flatten. So that 28 by 28 is just going to be flattened in the 756, just single vector, because we have to pass this to a multi-layer perceptron, a densely connected neural network at the end. So our first dense layer there is just going to have 10 units with an activation function as always ReLU. We're going to have a 50% dropout. And then another dense layer which is going to be just 10 units, because that is what we want our output. We have the number of classes is 10, and the activation there, remember, is softmax. And if we run the summary on that, we note that we have 27,320 learnable parameters, and that is really not bad if we consider the size of our input vector, 28 times 28. Now this is I'm going to say it straight off, this is a horrible model. This is not going to do, probably not going to do very well. And we definitely add a second convolutional layer there, maybe add the number of filters there, or the kernels, and then certainly have more than 10 units in my first dense layer there, if you really want to get some good accuracy. But this is just to demonstrate the different layers that we have spoken about. Compiling that, we're going to always have the loss, the categorical cross entropy. The optimizer I chose here, just for argument's sake, is the delta optimizer, and the metric is going to be accuracy. We'll make a batch size of 128, and we'll run through 12 epochs, and then pass the fit function, pass the model to the fit function, and have a validation split of 0.2. So if you download this actual code, you can run that, and you'll have a look on RStudio what the outcome is going to be. And then all I did at the end was just to create a score computer variable here. We pass the model to the evaluate function, and we pass x-test and y-test, and we concatenate this, the test loss and the score $loss. So that's one of the values that is inside of the score, and we see a test loss of 0.18, and we see a test accuracy of about 96.45%. So I encourage you to download this file or create your own convolutional neural network. As you can see, it really isn't that easy, and start your first look at at a convolutional neural network using the inbuilt image data sets. In future, I'm going to show you how you can use your own images, if they do live on your internal drive, how you can use them to pass it to, because that's quite a bit different than just using these inbuilt images. Now, there are lots of other image data sets available as well. CFAR 10, those images with 10 classes, CFAR 100. These things are all built into Keras, and I urge you to explore those.